questions we take in the gap if you have any.
Morning, Professor Mahesh. Mukesh here.
Yeah, good morning. Good morning, Mukesh. How are you?
Good, good. How are you?
Yeah, good, good.
Hello, Dr. Mukesh.
Hello.
I hope you recall we met, I think, at IISc Bangalore.
Yes. Now I see the face.
Okay, okay, right. Thank you.
How are you?
Fine, I'm doing good.
Yeah, so okay, in chat box. Okay, thank you. Tarun, yeah, Tarun, you can ask this one in between. We will allow you this one. Generally, what will happen if you will add everyone 200 in the panelist, then difficult to manage. That we have faced many times. So sometimes participants by unknowingly they unmute and then difficult getting the noise. And so that's why we put this restriction, but we will allow you this one, is not a problem. Yeah, we feel this one talk should be more interactive. So yeah, we will allow you this one. You can unmute this one.
Yes, sir. So I would also like to add that we are live on YouTube also, and participants can ask their
Okay.
questions over there also. If somebody is not able to ask or join from here, he or she can join questions over there also. We'll take questions from YouTube also.
Yeah, Nipul, can we start now?
Yes, sir. Sure.
Yeah, please start. So on the YouTube also, this is live telecast. Okay, good.
A very warm good morning to all panelists, dear participants, and students. I, Nipun Sharma, student coordinator for this event, take the opportunity of welcoming this virtual gathering to the second day of AICTE Training and Learning Academy, sponsored 5 days online workshop on nanosensors, which is being organized by Department of Electrical Engineering, IIT Jodhpur, from 5th to 9th July 2021. I feel honored and privileged to begin the morning session of second day by introducing our very first speaker, Professor Kamaljit Rangda, who is a very accomplished person, and by sharing a brief biography about him. Dr. Kamaljit Rangda did his master's degree from BITS Pilani and PhD from Department of Informatics and Telecommunication Engineering, University of Trento, Italy. At present, he is visiting professor in the Department of Electrical Engineering at IIT Jodhpur. Prior to the current assignment, he was the chief scientist and professor ACSIR at CSIR Central Electronics Engineering, Pilani. His research interests include radio frequency MEMS, material spectrization, micromachining techniques, vacuum microelectronics, and NBC sensors. He has published about 150 papers in the above areas and has led a couple of projects on radio frequency MEMS for ISRO, DRDO, and CSIR. Today, he is delivering a talk on the topic radio frequency MEMS, challenges and the opportunities. So with that, I would like to request Professor Kamaljit Rangda to please deliver today's talk. Over to you, sir.
Thank you, Nipun. It's my pleasure. And I'm thankful to Dr. Mahesh for inviting me to this exciting event. So I'll begin with my presentation and request everybody to have questions whenever they feel like. Okay, so I'm sharing my talk. I hope it is visible.
Yes, sir, it is.
Yes.
Okay. Yeah. So I can now start. Shall I switch off my video? Okay.
Yeah, depend. I think this one is fine.
Sorry.
Fine. Okay. Okay. Thank you. So let me begin with.
Can you do in the presentation mode?
Yeah. I'm just
Slides.
going to that. Yeah, sure. I'm going to that. Is it okay?
Fine.
Okay, thank you. So a very good morning again. And today we'll be talking about, in this session, we'll be talking about radio frequency MEMS, challenges and opportunities. So I'll begin with the outline itself. In general, we'll talk about MEMS for a while and electrostatic MEMS in particular, because that is the fundamental behind this RF MEMS switches. They get actuated because of the electrostatic field applied across two parallel structures. Okay, so we will also share the examples of implementation. That is basically fabrication, design, and characterization part.
Professor Bhangra.
Yeah.
Actually, your screen is very small. I don't know. Nipun, can you see this one?
Yes, sir. It's small, sir.
So
I think
Is okay.
settings.
is it? Shall I do it again? I will just check whether it's possible,
Can you
because
please?
my video will be lost then. Anyway, I'll stop
I
and
think
rejoin.
yes.
I'll stop and rejoin.
Yeah. I think better to stop video then, because that is very small video.
Exactly. So this is where I just rejoin again, or is it any better now?
Now slides are not visible.
Okay, slides I'll make visible, share.
Again.
Is it visible now?
Yeah, but size is same.
I don't know what is the problem.
Sir, can you go to the display settings? Because there might be some option for full screen mode.
Okay.
At the top of your screen.
Yeah. And display settings. Okay. I don't know. I'll just log out and come back.
Yes, sir.
Professor Kamalji.
Yes.
Okay.
Is it okay? Okay, it's not allowing me to share. Hello.
Yes, sir. I have paused on the
Yeah.
present.
Now it's allowing me to share. Is it any better now?
I think we can continue with this one.
Is it? I don't know. Display settings I can check here, but it's not doing anything. Yeah.
Professor Kamalji, is there any option where this screen is showing split in the bottom?
Yeah. It shows there are three icons basically. That's because of my own laptop. This one.
Yes.
Is it
Yeah.
okay?
Can you go to the options where
The option is for disabling your video. Please don't go to this option.
Pardon?
Maybe you
So
can
your
go to
slides
the
are
three.
visible, sir.
Can you go to three dots here, like after the screens here?
Yeah. Presenter, hide presenter view is.
Yes.
So hide presenter view.
Yeah. Click here.
Okay, just let me check. It was there. Now? No.
Yeah, it is good now.
Now it's fine. Now it's fine.
But I
Yes.
can't see any. I can't see anything.
Okay. So
Now is that visible?
yes.
Yes,
Yes.
sir.
Okay, fine. So I'm sorry for the. Okay, so now is it okay?
Yes, it's fine.
Okay, thank you so much. Sorry for the trouble.
Yes.
Hello. So shall I continue?
Yes.
Yeah,
Yes.
okay,
Yes.
thank you,
Please.
thank you. So that's where we were. So we'll be sharing some examples of design, fabrication, characterization, and obviously the moment you'd go for the development cycle, you would have lots of challenges. So some of the challenges I'll be sharing, and these are basically the stresses which develop in the structures when you try to make them through surface micromachining or bulk micromachining, and about the material selection as well. And of course, packaging is a slightly different issue in the case of RF MEMS that I also that will be also shared, and then some of the applications. Obviously, when I go through, all the things may not be in the order which I am presenting in this slide. So kindly bear with me. So I start from the very historical perspective where the miniaturization started. MEMS is enabling it's an enabling technology for making sensors and actuators and to generate systems in totality, right? So this is about all about miniaturization. Even if you go by the definition of MEMS, so I'll be using my pointer. Okay, so if you go by the definition of MEMS, it is basically enabling technology and it means micro electromechanical systems. So there are various acronyms for that, depending upon the origin earlier, but MEMS is the final one now, as I understand it. So micro stands here for the dimensions. At least one of the dimensions has to be in micron size. Others could be like larger or small. And then electro stands for actuation, and mechanical stands for the degrees of freedom a structure can have. It could tilt, rotate, bend. Okay, and system is basically should be called solutions. So using this approach, one is supposed to provide solutions in sensing and actuation. That is what the MEMS are supposed to do. The comparatively new definition could be micro is substituted by now the batch fabrication. Important is not the dimensions, but important is the batch fabrication. How do you fabricate them? So here we take the set of technologies, the basic processes straight from IC fabrication technology, and they are a little more into that. Okay, and the electromechanical primarily now stands for the conversion of energy from one domain to another. For example, it could be from mechanical, chemical, thermal, and electromagnetic into the electrical energy domain, or vice versa. So it's basically the conversion of energy which is available around us, around the environment, around the basic events. So that is to be converted into a form where it can be easily disseminated, and systems is basically again solutions. So with that definition, the miniaturization actually started with, that's what people think, that it started with one lecture by none other than R.P. Feynman, the Nobel laureate, to American Physical Society in 1959. So this is available on the net, and this is something titled as "There is plenty of room at the bottom." So out of this, the main hypothesis put forward by R.P. Feynman was that there's possibility of miniaturization of devices and systems to the extent till the physical laws and material properties impose no limit. So this hypothesis basically is now divided into two parts. One, the systems and devices and techniques with no limit on size. So you can make your devices smaller as long as the material properties and your technology and the basic laws of physics supports it. And this has evolved as, VLSI, okay, making ICs. And if you look at the technology node, these magic numbers basically again commensurate with what Moore said. Okay. So if you take this one of the dimensions, you'll find that area is reducing every time with number of devices being the same. So again, a reduction which was predicted in terms of miniaturization. And nanoelectronics, of course, where there is no size limit as such, as long as material properties and your device properties are getting the way you want them to be. The other part of it, of the hypothesis, is devices and systems where size matters. And this is what MEMS is. And these are supposed to do some sort of work. That is why it is important to have a finite size. For example, if you are to produce some gear system which will do some work, so it is supposed to have some finite size. Okay. As far as this miniaturization drive is concerned, and this technology node is concerned, you can have a look at this news item from Verdict, where they are now moving on to 2 nanometers and 1 nanometer devices, which are of course at present in R&D. So with this little background, I just want to recall how the miniaturization started happening, especially in ICs and MEMS, of course. So during this talk, Feynman put forward a few challenges. One of them was to make this normal electric motor 1 by 64th of an inch, excluding the wires. So that challenge was met within probably 1 year. And the other one was like, can we write the whole 24 volumes of Encyclopedia Britannica onto a pinhead? So it was literally, he made some calculations, and the calculation was based on the fact that if we do the reduction, say, imagine the smallest dot on I over here, if you reduce it by 1 by 25K, then the dimensions would be coming to submicrons. So given the size of the normal pinhead, he thought it is possible to write the whole Encyclopedia Britannica literally onto a normal pinhead. And the approach at that particular time he suggested is something similar to Liga, the fabrication part. So making a mold of plastic and then coating it with metals like gold. And then reading mechanism was suggested by him, the electron beam, the electron microscope, so to say. Okay. And as we understand, so this challenge particularly was met in 1985. Tom Neumann and Stanford University. Okay. So this is what we know as of now, the top-down approach, where we can make smaller and smaller patterns with electron beams with a resolution in nanometers range. There are other techniques as well. So what was demonstrated in 1985 was small writing. Literally, they wrote on a piece of silicon using electron beam lithography technology at that time, which was the beginning of technology during that time. So they were able to write some lines from some text, popular text. This is basically Tale of Two Cities. And then they were able to read it back, of course, using the electron microscope high resolution. The other part which of this prediction was starting is the bottoms up approach, as we know of this thing now. And that is through the manipulation and control of the atoms using scanning tunneling microscope tips. So this is about the miniaturization, which was predicted around 1959, a good 60 years back. And now it's well known in terms of its devices, and not only ICs, but devices which are sensors and actuators made into smaller size. So these two persons who are well known for in the field of IC technology, VLSI and MEMS, and of course he's known for his books on physics also. So the predictions made by these persons, which has come true as of now, and has resulted in two branches. One is what you call Moore's law. Okay, so the y-axis, which basically is indicated here in terms of the technology node, which has been shrinking, which has been almost reducing to half every 18 months or 2 years. And that way doubling the number of components. And the other part is which we call more than moves. That is integration of the passives, the analog and RF components, high power components, sensors and actuators onto a single chip. Now the combined effort of these two branches, that is basically leading to this fabrication of systems which interact with people and environment and produce a complete system in package. The SoC, so system on chip, for example, if you take the VLSI perspective, it would not be interacting with the environment the way sensors and actuator integration in SiP would be doing. So this is the background about miniaturization. And now I move on to the basic MEMS, electrostatic MEMS structure, how it functions for the sake of the students who are present over there. So we know that if we have two parallel plates separated by a distance, say 2 microns, okay, and the bottom plate is fixed one and the top plate is hanging with some kind of spring, and we apply voltage across it, what will happen to it? So there'll be force of attraction between the two plates, the electrostatic force, which is basically generalization of this basic function, the force of attraction between two dissimilar charges. So the moment it comes, the voltage is good enough to overtake the spring constant, the stiffness of that upper structure, the top plate can make a contact with the bottom plate. So this is electrostatic actuation. Now, if I make the use of this in a device, in a structure, which I'm presenting on this right hand side. So what I have is a cantilever, a simple cantilever, which is anchored at this point, right? And the dimensions could be 100 microns by 100 by 30 by say 2 microns. So thickness is very small. And now if I apply a voltage between these two stack parts, this is the actuation plate at the bottom with some sort of insulator on the top, or dielectric material if you want to call it, and then this yellow one is the metallic structure. So if I apply potential across these two, some voltage which is slightly more than the mechanical stiffness of the structure, it will start bending down. Okay, so as it moves, as it bends, it can make a contact at another structure over here, right? And this structure here, which is on this side, this could be a simple structure. This could be a part of transmission line. This could be a microstrip. Okay, so the moment the beam comes down, it makes a contact here. Okay, so signal now can travel from the input side to the output side. And this is nothing but a simple ohmic contact switch, where this cantilever is providing the contact between the two ends of the transmission line. Instead, if you have the transmission line complete and you have a piece of a small area which is covered with a dielectric, and you have on the top, this beam makes a contact. So what you have here now, you have metal, dielectric, and again metal. So you have generated one capacitor. Okay, so this is the fundamental of one RF MEMS switch based upon the capacitance, what we call as capacitive RF switch. Okay, so by simply having structures which could be a beam cantilever like this, or so this is fixed free. This end is free here. We can make it a beam, a bridge, where this end is also fixed. Okay, so we can realize two functions. We can generate one ohmic contact switch or capacitive switch. This is also a variable capacitor. When it was in this state, capacitance was very, very small. But the moment you make a contact, capacitance is much higher because you have reduced the distance between the two plates. Okay, so this is simple mechanism of generating ohmic and capacitive switches. You can also imagine we can also generate from this a variable capacitor, varactor for example. In that case, the movement of this cantilever has to be in a controlled fashion. We know that there is a non-linearity when it comes to electrostatic actuation. What varactor would need movement of the plate with respect to applied voltage over a range in a uniform fashion. So that would constitute a varactor. Okay, so just quickly, how do we fabricate this? So we start with a wafer. And in general, RF MEMS, the wafer particular doesn't have to be silicon only. It could be other wafers also, which are acceptable to your fab. We use silicon wafers because they are acceptable in the fabrication houses easily, and we use high resistive wafers. Okay, so on the top, then we make one electrode, which I'll call the actuation electrode. So this could be a simple rectangular shape. Then I make the part of my transmission line. So here blue represents the metal, and this red could be polysilicon. Done that, I deposit one layer of the sacrificial layer. Okay, so sacrificial layer basically could be the photoresist, it could be silicon dioxide thick layer, or it could be copper also, copper electroplating. And then you make an opening because here you would like to anchor your cantilever. And before you do electroplating, you need to have a seed layer. So you sputter some seed layer on top of this and then do electroplating. And next step is get rid of the sacrificial layer. So your cantilever is ready. So fabricating one simple cantilever is not really very tough. Okay, now coming to the electromechanical design of it. So these MEMS devices, or specifically RFM devices, they lie in two domains, electrical domain and the mechanical domain. So mechanical domain primarily will be represented by the stiffness, that means, and stiffness, the spring constant of the cantilever. So if you look at this part here, very simple expression, this correlates the stiffness or the spring constant of this cantilever to the material property coming through Young's modulus and the dimensions of the structure, width, thickness, and the length. So this is a simple paper and pencil design which can be achieved, and then you have to work out the pull-in voltage. How much voltage you should apply between this cantilever here and the actuation electrode here. Between these two structures, how much should be the voltage so that this beams start bending down and makes a contact here. So that will be function of the gap, how much gap you have, rather I should say this gap, and A stands for the overlap area. So what is the overlap area between this plate and this plate, right? So, and this is material property, of course. So one could calculate, and K is the stiffness constant in Z direction, which is coming from this equation basically. So you need to work out the mechanical part is limited up to, or the electromechanical part is limited up to finding the pull-in voltage of a structure, which should be optimized in a sense, like it should be minimum as possible, unless until the structure becomes too flexible, too compliant, so that it is vulnerable to shocks and vibrations. So that has to be taken care. The other part is the electrical properties, which is basically if it is RF MEMS, then you got to do the S parameter analysis. Here you'll try to find out what is basically the response in terms of insertion loss, okay, and the isolation provided by the switches. And next part is, of course, to go for the packaging. So in nutshell, I have already shown like how do you design the switches. So it could be, for example, up to the part of finding the pull-in voltage, one could go for a simple design where you don't need really the simulators. But nowadays simulators are available, so one could easily go to them and verify the results using this rough kind of calculations. Starting S parameters, of course, would need some sort of simulator for you, HFSS, for example. And packaging can also be done based upon the response, RF response of the cavity itself, because cavity becomes part of the device in this case. The cavity, what I mean by cavity is the structure which you use for encapsulation of these devices. So one could, the idea, this is all surface micromachining, as you would recall. This is through surface micromachining. One could use bulk micromachining as well. Okay. So now what is the advantage of making things smaller? In fact, if you recall, this cantilever based approach to generate a switch is nothing but very similar to electromechanical relay. So this is miniaturized electromechanical relay only. But what is the advantage of having these devices in general? Why we should scale down the devices at all? So this comes from the fact that if we consider a structure something like this, cantilever or a bar, for example. Now, if I represent the dimension of this bar in general, length, width, thickness, everything, if I represent it by L, okay? So the volume would be L cube, and hence mass would be, so if I reduce the dimension by 10 times, right? So my new dimension is 10 times less as compared to the original one. So how much mass would be reduced? Mass would be reduced 1,000 times. So 10 times reduction in linear dimensions leads to 1,000 times lighter object. But what happens to the stiffness, the spring constant? Spring constant is reduced only 10 times. So the first thing is smaller devices, smaller structures, beams, cantilevers, diaphragms, if they are reduced isomorphically, so they are stiffer and lighter. The best part of it comes from the fact that the sensitivity of the resonance frequency to change in mass, which is given by this kind of expression, but finally it correlates to the dimensions through this kind of expression. So what it means is 10 times scaled down device becomes 10,000 times more sensitive to resonance frequency change. Okay. So this is a device where you can measure smaller masses with a better accuracy. Pico and picograms even can be correlated. Change in the mass of the order of nano and picograms can be correlated to change in the resonance frequency. And if one is able to measure the resonance frequency change, then they can be used, these devices can be used for biomems without any mark. Okay, here you would need the level because you need to functionalize the cantilever to get the particular antigen which attaches to the cantilever. Okay, or this could be used for other purposes also. For example, explosive detections. So even if few molecules of this material stick to this cantilever, there would be change in its resonance frequency. So this becomes a very good detector where mass change can be found very easily. And now this was the positive side. If you look at slightly the negative side of it, how much is the reduction in electrostatic force if you do the scaling part? So from this simple correlation, which is the force between two parallel plates, if you just look at it, we say the force is proportional to L square, the dimensions. L stands for the dimensions here. Okay, so you can work out from this place. So if there is 10 time reduction in the dimensions, these plates are becoming smaller. That's what it means. So the electrostatic force goes down by 100 by 100. Looks bad, But if you compare it with electromagnetic forces, then you feel slightly better. Okay, so just to have a look, the force, electromagnetic force on a small element here on this wire W2, in which current I2 is flowing because of the wire W1, which has current I1 flowing through this, and the distance between two is X. So this force will be given by this kind of expression. Okay. Here, if you look at the terms in this expression, we have I1 and I2. The rest of the terms do not matter really, in the sense like they cancel out dimensionally. Okay, this is dimension, this is dimension, so this becomes a dimensionless term. Okay, so the force primarily is a function of the current flowing through wire 1 and wire 2, and current, as we know, is proportional to the area of cross section. So area of cross section, I can represent it by L square again, the dimensions which I was considering. Okay, so L squared term is the dominating one. So if I do a 10-time reduction in this case, this leads to 10,000 times of reduction in electromagnetic force. So with scaling down, electromagnetic forces, they do not augur well. Reason is you need to put a large coil to get any actuation, whereas in electrostatic, this is slightly better. This was 100-time reduction for a 10-time reduction in the dimensions. So electrostatic is preferred over electromagnetic because of the reason that it occupies less space and it can be easily implemented. This is one example, not from our work, but from other places. We have this. So I don't know if it works or not. I'm not able to get this functioning. Anyway, this is basically a motor which can rotate very easily. Okay, so this is one example of this is electrostatic motor actually. So I'm not able to get the video done, but here the dimensions are diameter is around 200 microns. And this rotates. The other examples, there are plenty of examples of electrostatic actuation. We have talked about the switch as such, if you remember. And then we can talk of tweezers, and there's plenty of examples available in the literature of this electrostatic actuation. One is it's not really electrostatic actuation, but just want to highlight that you can integrate a pressure sensor onto a contact lens to measure the pressure of the eyeball. But my main aim is to highlight the role of these small cantilevers. Again, one application which works as a sensor for measuring the glucose content in the tears. Okay. This was basically originated by Google. And actually the structure is nothing but a simple cantilever. So if you see this one, the sky blue color here, this is a cantilever. And then there is basically here a layer, permalloy kind of layer here, the red one. And this whole structure is inside a cavity. The yellow one is what we call dextran concavalin A, or con A simply. Okay. This solution is biocompatible, and this whole structure is fitted onto the contact lens. That's why I've shown the earlier slide of contact lens, where we have the pressure sensor integrated in the contact lens itself. So here now, depending upon the viscosity of this fluid, con A, you would have the amplitude of vibrations or some parameters of the cantilever, which you'll be measuring in terms of the vibration parameters. Now, if the glucose from the eye permeates into this cavity, so we have here a semi-permeable membrane. Okay, if glucose if the amount of glucose increases in tears, so viscosity of this fluid will change. The moment viscosity changes, so cantilever vibration parameters will also change. So comparing the two sets, when you had no glucose or glucose concentration was X, compared to the scenario where you have now glucose concentration X2. So one could check that change in concentration through the measurements of the frequency of vibrations. So this is yet another example of simple, humble cantilever, which can be used as a sensor for mass detection or concentration detection. Now, just before I go to the actual devices and the actual technology, I just want to give you why these RFM switches are better. We have seen the cantilever, which can work as a RFM switch. I'll give you the examples further, which are the actual designs. But before that, just if we do the comparison, so we have RF MEMS, and comparison could be done with electromechanical relays. Because in terms of the isolation, electromechanical relays provide a very good isolation as compared to any other devices, if I'm showing it here. Okay, and then you can compare it with FET. So the power consumption by the switch itself, we know that switches consume power by themselves. So it happens to be the best in this case as compared to this relays. Relay consume lots of power, and so the pin FETs, the pin diodes, and the FETs also, they consume power. Okay, so here scenario is quite good, comparable to FETs. Okay, switching time, of course, it's difficult to compare because these are mechanical switches. RF MEMS are mechanical switches. So the on-off time depends upon how quickly the beam, which was bent by electrostatic force, how quickly it restores back to its original position. And that is purely a mechanical phenomena. Depends upon the stiffness of the structure. So speed is no comparison. We cannot compare speed. They are much slower as compared to these devices, but they have their own niche applications. If you compare the isolation, they provide very good isolation as compared to any other devices here. The reason is, in this case, we don't have any metal semiconductor junctions. We have simply two metal structures which are separated by microns of distance. Whereas in this case, the source and drain, they are quite closer to each other. The channel resistance and the channel capacitance, they're quite small in this case, whereas these are the mechanical structures here. So there's a huge separation between the transmission line, the gap itself. Okay, so they provide good isolation, and again, insertion loss is also pretty small. Okay, insertion loss is one of the best because here again you have two metal pieces coming together, coming in contact. So this is the contact resistance as compared to on this side where you have the resistance coming from the channel itself. Okay. When it comes to power handling, there's quite a there are actually, this point is something which is which requires further research. Power handling is one issue as of now with this RFM switches, and this has a close tie-up with the life of the switch itself. Okay, so we'll discuss it as we go along. Cost is not a problem because if the technology goes cheaper, this can be managed. Lifetime is given in terms of number of cycles, the on-off cycles a switch can make. So people have already demonstrated this can be pretty high. Okay, so now coming to the actual devices, I just wanted to share with you. Our flagship device has been the RFM switches themselves. So in this, we had SPSTs, SPDTs, SP4Ts. I'm sharing some pictures here, and then the switch matrix. So this happens to be the T-type switch matrix over here. This is ohmic contact switch, and these are capacitive switches here, put in the form of SP4T. Okay, and as a spin-off, we were also designing inductors and interdigitated capacitors handling the packaging part of it. And then, as I said, when it comes to the process and fabrication, so there would be lots of problems. Stress is one problem. So we have been talking about the stress characterization as well. And of late, the set of technologies which we developed for this in terms of single and double bridge, metallic surface micromachining, and bulk micromachining, we were rather also into, I'm not part of that group now, except that I have PhD students again. So digital micro mirror arrays, quadrupole mass analyzer, and DMTL bio MEMS. These are the parts, these are the devices which we have been working. So coming back to the switch, typically, how do you define a switch? So since these projects were closely correlated to the user agencies, so we start with the definition, the specification part of it. So frequency range, we have been covering ranges from your C band to the cow band, and giving this frequency range for us. Insertion loss, what we intended was 0.2 to 2 dB. This is measured one. We have achieved up to that point. And actuation voltage were 5 to 15 volts. Okay, power handling is something which we are not able to go more than a watt. This is one issue still pending. And packaging, I'll share the packaging part, which is basically epoxy kind of packaging with silicon cavity. Okay. And switching speed, so far the best is not more than 20 microseconds. Now, if you compare it with the application part, if I put it, say the application is 5G requirements, this pretty well meets most of the requirements. Okay, even the latency part, which is 1 millisecond to 10 milliseconds, we are having speed more than less than 20 microseconds. So application part is, I'm not dwelling into it, but wherever you have the power crunch, these are the devices because they consume very small power and they are compact as compared to other electromechanical devices. So mobile pico satellites, wherever you have power crunch, of course, in 5G, lots of them, lots of applications has been projected as the potential applications for RF MEMS. So again, the same slide is getting repeated. So any space-bound terrestrial communication systems where power is a constraint. The one example here I want to give is the redundancy switch matrix for satellites, which as of now weighs more than 500 grams. So using RF MEMS approach, this can be reduced to a couple of grams, the whole switch matrix. This is one of the advantage. And of course, smart munition missiles, they have space limitation as well as power resource limitation. So that's where these devices fit into the scheme. Using these RF MEMS switches, one could generate phase shifters, and these phase shifters are part of these all devices. Of course, switch matrices for automated test equipment. That's also one of the applications. Now the problems associated with RF MEMS, plenty of problems over there. If you compare it with VLSI, then here we have one device, one fabrication process, and again a unique package. This itself calls for lots of efforts in terms of designing the fabrication process, the packaging, and of course design has to be unique. Okay, so I'm sharing one slide from literature again, where you could integrate the RF components, which could be a varactor, a switch, a filter, inductor coil, and then there has to be the control electronics somewhere on the wafer itself, if it is to be a monolithic integration. So monolithic integration itself becomes a very tough job because all the front end processes cannot be done. So at one part, you have to generate your LSI, that means your ICs. And the other hand, you would have to generate these mechanical components. So monolithic integration presents a complex design in terms of managing the thermal budget. So hybrid integration is what people had been preferring. And now coming to the other side of the challenge, RFMs was supposed to be a hype. It took almost 25 years plus to have good devices. I'll show that slide. But what is the real problem? If you look at the classes of MEMS, there could be MEMS where there are no moving parts or movement is very small. For example, if you have an inkjet printer, this is one of the first MEMS devices, right? Or accelerometers. Accelerometer would vibrate only once when your vehicle deaccelerates very fast. Okay, so typically there is movement or there's very little movement. There's no movement or there's very little movement. So we call it no moving parts. Then there could be MEMS. For example, I'm showing here these COM drives, which could be a part of accelerometer, gyro, and structures like that. So here again, they slide into each other. They don't touch, no rubbing, still better. The next class is, it could be moving parts with impacting surfaces. Think of the here, the micro pump. So these valves, they'll be banging onto the surface. Okay. So pumps, valves, DMD, digital micro mirrors, these structures are where there's wear and tear, strong wear and tear, and strong reliability issues are involved wherever you have impacting surfaces. The next class is where you have almost everything, moving parts, impacting, rubbing surfaces. And these are shutters, scanners, optical switches, locks, mechanical locks. Okay. So this makes the fabrication still a difficult issue in terms of the reliability of the devices. RFMs would have everything plus the higher current density because these are switches. So the moment there is a contact, so this is my other side of the output, this is my input side, and these two would make a contact through these bumps underneath. Okay, and this contact has to be elastic one. That means that there should be no deformation of the bump itself, but the combination of the pull-in force and the current flowing through the structure deforms the bumps very fast. And that basically is a very strong factor which undermines the reliability of the devices because contact resistance would be changing after a few hundred cycles even. So this is what we call hot switching, when you flow current through these wires through these bumps or through these strips. So that undermines the reliability pretty severely. And that's why the switches, so the hype curve, which we know as Gartner's curve also, the moment these devices were introduced, there were lots of popularity, lots of visibility. People hopped onto this. They started doing RF MEMS. Companies also started doing that. But within 2 years, they fall onto this stuff of disillusionment. Okay. People were not happy with the technology. Again, most of them closed down, the startups closed down, and people kept on doing the incremental R&D work. And around somewhere here, again, 2008, there were lots of investments. Next part, I'm showing it here. Again, there was this disillusionment. And around this area somewhere, GE, General Electric, and this Cavendish Kinetic, they started investing money. And finally, in 2017, Cavendish Kinetic has come out with a chip, Smart Tuner, which basically demonstrates that RF MEMS can be done. So I'll share that later. In terms of the difficulty and what we are doing in R&D labs. Okay, so we end up here, technology readiness level. Mostly we end up here. We validate in lab environment, the typical devices, and we are not switching over to this reliability part. We are not really able to cross this because this is the engineering part of it. Either the startups or the industry has to do it. By this time, your student has already submitted his thesis This is done, papers are done, and that's where you close it. So funding also becomes scarce after this level. Okay, and after this level, the difficulty level is this type, slope is negative now. So you have to exert more. So this is the state of affairs which has happened with, typically, if I'm to share my experience, this is how our devices has fared. Okay, and now I'm sharing the opportunity part, which is demonstrated by Cavendish kinetic. So what they have done, in summary, they were using this SPXT, that means switches, DPDT, SPNT, to tune this main antenna and the diversity antenna. And of course, the switching between transmit and receive sections, that is also done through these RFM switches. Okay, so done through this, what is the advantage? In nutshell, the advantage is they are able to get higher antenna efficiency from one antenna by tuning it over desired frequency ranges. In general, if you look at the broadband antenna, this will be highly inefficient for some given frequency range. Now, if you can tune it to a particular frequency by using the varactors, the RF MEMS switches, then the efficiency can be increased. And that's what they have demonstrated. And this chip, Smart Tune, basically claims that they are almost effectively doubling the RF frequency, 3 dB improvement they have claimed over these frequency bands. So this typical chip has demonstrated that RF MEMS are worth it. So now I'll take a few examples. I think still we have time, right? Okay.
Yes, sir.
Yeah. Okay. So so now I'll take a few case studies. So one of the first and simplest switches, if you look for RF MEMS, is the one shown here, the classical switch, and this happens to be our first device. So in this case, a device itself is very simple. We have a metallic beam here, a bridge. Now we call it a bridge because this bridge has underneath it the transmission line, which is shown here. Okay, in and outside. And then we have two actuation electrodes, 1 and 2. Both are shorted together. So I'm showing it here, 1 and 2, they're shorted together. So now when the beam is in its normal state, up state, right, signal can easily pass through. There's no problem because capacitance here is pretty small. And this gap could be 2 to 3 microns. The moment you apply actuation voltage between this one and the bridge, this one, okay, so the beam would come down. It makes a contact. So here you have generated a capacitor, right? And this capacitor would shunt the signal to ground. And that's how the isolation happens. Okay. So the fundamental here is a ratio of these two capacitances. When it is in this state, so we call it C up, and when it is in down state, the C down capacitance. So in a sense, the figure of merit will depend upon the ratio of these two capacitances. So optimization of these capacitances is the ultimate goal in classical capacitive RF MEMS switches. Ohmic contact already I have demonstrated. So we have the transmission line here, which is with a gap over here. The moment this cantilever is bent down and makes a contact, so the signal can pass from the input end to the output side. Here important is what is the contact resistance over here and what are the parasitic, of course, parasitic resistance and the parasitic capacitance will also be important. So as I mentioned in the beginning, the switches, they lie in two domains, electrical and mechanical. So mechanical domain to some extent I have discussed. So what we need to do is need to find the pull-in voltage. How much voltage should I apply here to make a contact on this structure over here? Because here it's here where I'll be generating a capacitor. right? So pull-in voltage, and that will be in terms of the stiffness of the bridge or the cantilever, which in turn depends upon the material properties and the dimensions. And primarily, if I talk of the stiffness, it will depend upon how do you anchor these. So you could go for flexible springs, different kind of springs. So here I have this U shape called meander. And primarily it is for tailoring the spring constant part of it. Okay, G happens to be the gap, okay, and A happens to be the overlap area. So overlap area between these two plates. This is the actuation plate 1 and the second here. This will give us the capacitance part. Okay, so C up and C down. These two capacitance has to be optimized in terms of, so this is the mechanical design part of it. The stiffness, the pull-in voltage, and the capacitance ratios. Okay, and typically you got to design it in such a way that any contact you make, that is elastic contact, it doesn't deform any of the surfaces. Otherwise, there would be change in contact resistance when you switch it over a few number of cycles. So that is the primary consideration, and next consideration is the electrical part of it. So electrically, you can model the structure, the mechanical structure you had, that can be electrically modeled as this kind of structure over here. So this represents here the transmission line itself, the properties of transmission line. It would have its own inductance, it would have its resistance as well, even though they are metals. Now coming to this part, so this is a CPW basically, coplanar waveguide implementation. Switches can be implemented through microstrips as well. Okay, CPW is typically used because this provides easy access to the ground plane. So this is ground plane on this side. This is the signal line actually. Okay, so this mechanical structure, the overhang over here between ground and the transmission line gives you the inductance part. So I'm representing inductance here, and this bridge itself would have, even if it is metal, it would have finite resistance. So R is represented here, and then you generated a capacitor on purpose. So this is transmission line, metal, dielectric, and metal. Okay, so this is a variable capacitor. It stays in two states, okay, up and down. So this is the electrical model. And then if you think over the parasitics, there would be lots of parasitics. I'm not dwelling into that, but parasitics can be lumped into a capacitance and resistance, which could be from the substrate itself. That is why we use substrate with high resistivity. Okay, so the impedance of the switch basically can be represented by this kind of equation, where CS stands for the capacitance in two states, up and down state. And resonance frequency will be, of course, given by a general expression, which is well known to us. So in this case, what you have to really optimize is the S parameters. So you have to see S parameters. That means the insertion loss and the isolation. S21 in up state, S21 in down state. So that will give you the isolation and the insertion of the switch when it is the capacitive switch. Okay, now coming to the mechanical part of it, the various designs are possible. One of the designs I'm sharing with you here, this could be a thin membrane, actually 2-micron thick perforated one. Why there are perforations over here, why these holes are there, I'll come to that part. Okay, so now simulations show that you could get a very good capacitance here. The overlap is perfect as far as simulations. This is simulation part of it. So this is making a nice kind of contact over here. But actually beams do not bend like this. They bend with a curvature like this. Okay, and that shifts the frequency. So you simulated it to be somewhere here, but actually your capacitance is less. So experimentally, smaller capacitance shifts the response to higher frequency side. Okay, so remedy for this could be reinforce this membrane. Yellow one here, this was the thin membrane which we used earlier. Now this brown one is a thick reinforcing ribs. Okay, so it's like a kite, on a thin paper, you're putting those reinforcing ribs on the sides. So this makes a structure which is rigid, but otherwise light. Okay, so this gives you good capacitance, full capacitance as designed by you after fabrication. This is fabricated device. Okay, these ribs can also be used to fine tune the frequencies because these ribs ultimately give you the inductance part L. Okay, so you can fine tune the resonance frequency as well. The next part is, as I said, the figure of merit would be this ratio C down by C up. And this typically becomes very small because of the stress and other things involved. And where it comes from? It comes from this place. Up straight means this should be straight, and this is the up straight capacitance. When it makes a contact at the bottom here, if the contact is not appropriate or there is any deformation, then C down is not what you intended it to have. So what we did is earlier design, if you had you noticed it on this oxide, so metal, oxide, and that's it. And then top this beam was making the other part of the capacitor, metal, dielectric, and metal. That's how the capacitor was made in earlier design. Now we put a floating metal layer here. We call it floating because it is right on the dielectric here. So metal, dielectric, and metal, but the top end is still floating. When this beam is actuated, it makes a contact here. So that way, the full designed capacitance can be utilized. And this also necessitates that we need not have now this full overlap here, because overlap problem, so this is the overlap over here, full. So this overlap problem is now transferred to a simple contact. So switch size also becomes much smaller. So this is a switch without floating metal, classical one, where this layer was not there. So to have a good capacitance, we need to have a good overlap. So this structure, if now is replaced by this floating metal, we have a thin structure. So there is around 50% change in the size of the switch. The other part which you have seen, I'll quickly cover it, that is about the perforations. So these perforations take care of the damping as well. We are not bothered about damping because we are providing the perforations on the top structure. Otherwise, damping will introduce its own kind of complexity into switch design. Also, these holes are, they help in etching because your etchants can perforate it, they pass through when you want to remove the layer. I'll come to the fabrication part. It will be more clear there. So these perforations basically help you in etching the underlying layers, the sacrificial layers, more efficiently. Okay. Also, these perforations, they are known to reduce the stress generated in the structures. And this is given by this kind of expression, basically. So this depends upon what is the size of hole, what is this dimension. But side effect here is the fringing field capacitance or dielectric or the electrostatic field will reduce because of the perforations. So one has to strike a balance between the gap between the top beam and the actuation electrode underneath and the type of holes you are producing. Okay, and we are using, as I said, coplanar waveguides for easy access to ground and reduced dispersion, of course. Okay, the other part of the switches which I shared with you was ohmic contact switch. So this is the actual ohmic contact switch. Now the crux of problem here is, okay, by the way, functioning part is you have transmission line here, the input side, the output end. The connection between these two is made by this plunger. And this plunger is further highlighted. So this is the part actually, which makes a contact. If you look at again the sketch, so this part, this part, or this part, either way, this is nothing but a flexible membrane, this one, making a contact on the bump. Okay, So now when they're not making a contact, so situation is like this. You have capacitance, right? Here, this one and this one. This is because of the gap and this is because of the parasitics one. Okay. Now, the moment you pull it down, you make a contact here. So the contact resistance is the main issue in this case. And the force with which the contact should be made, it should be in elastic regime so that there's no deformation of this bump. So if you optimize the geometries of bump, you'll find that hemispherical structure is the best one, right? And this has to be stiff enough to reduce the contact resistance and compliant or flexible enough. These two are contrary statements, not to damage the bump itself. And that situation is more complicated when the current is flowing through this and temperature rises. So electromigration becomes one issue. So material selection here becomes very important. So I'm not getting to the details of this, but different materials has been tried. Molybdenum, tungsten, okay, so to generate this bump so that the switch parameters, switch resistance, insertion loss, power handling, and above all, the reliability could be improved by typical selection of the materials or the bump shapes. Okay, and this typical sketch shows how the switch functions, ohmic context, which I'm talking about as of now. So this is the input signal. It has to pass through and reach here, and this depends upon the contact. Okay, so gate, typically gate is the actuation voltage, if you allow me to call like that. Okay, so that's how depending upon what is the frequency over here, you can have your output signal, right? If the signal is not there, you are just actuating it on and off, then we have completed, this is called cold switching without any signal flowing through this for testing purposes. So a billion cycle can be done. We have done billions of cycles in this case. And then if you increase the signal amplitude, that is where the problem starts coming in. Depending upon the current density flowing through this current density over here, that will be function of the input signal or the input signal wattage. Okay, that's where the problem comes in. And as the RF power increases, if you look at this curve, this life of the switch, number of cycles it can do, drastically goes down. This problem still remains in most of the switches, except by GE, which are using technology which they are not disclosing, but they mention it as the materials being used for avionics. Okay. So we don't know as of now what are the materials they're using, but reliability of the ohmic contact switches still remain a problem in terms of the life cycle of the switch. Okay. So this is yet another device done by our group where we are taking care of some of the problems. If you remember what we were doing, we had a bridge like this, classical bridge, simple. This structure was not there, this side. We had simple structure like this much only. So now once it is actuated, once you apply voltage between this one and the upper bridge, makes a contact, say for example, because of moisture and all, there's a adhesion of this thin membrane to the bottom electrode, or there's charging. Charging also happens because you have dielectrics over there. So because of the charging or adhesive forces, this is possible that beam is stuck here. So switch is stuck on permanently. Right? Classical switches, they face this problem. So we provided another extension over there. And now once the cycle is done, on cycle is done, we now go for applying voltage across this electrode. There's one here also. Okay. So this snaps it open. This will pull it like this, upper portion. Yet another advantage is, if you remember, the upstate capacitance is a function of this gap, and upstate capacitance should be smaller as possible. Now pulling it upwards, we have generated the gap, which is twice the normal gap, 2G, G plus G, G0 plus G0. So upstate capacitance is also reduced. So that improves the figure of merit of the switch, right? There are plenty of other advantages, but just mentioning the two. And then this can be implemented as a capacitive switch, ohmic contact switch, and typical frequency ranges. So this has been tested for 1,000,000 cycle plus, and the best capacitance ratio, the figure of merit we had 48 and I think 70 as well. I'll show. So these are the measured graphs. So I'm not getting into it, but simply it is showing isolation over a particular frequency range of 11 gigahertz, which was the given target for us, is minus 60 dB. Insertion loss is 0.64 dB. Okay, 0.68 dB and 0.64 dB. So these are pretty well behaved devices. I think I can skip it off, but this simply shows the simulation part of it when device is. So this is when device is in off state. It's a huge capacitance over here because down state, and you can pull it up. So gap is doubled. That's what we wanted to demonstrate in this case. So gap doubles up, okay, improving the insertion loss. There's yet another advantage. We can tailor these structures here. The connecting lever that can be dimensions of this basically allows you to fine tune the switches over a frequency range. Okay, these are certain devices, different variants of that, the same structure which I've shown earlier. Here, this is the classical one. In this case, the dielectric material was silicon dioxide. Okay, now if you switch over to hafnium oxide, which has certain properties better than silicon dioxide, okay, dielectric strength is better, and dielectric constant is also 15 to 20, depending upon the process. Okay, so this makes possible to make the devices compact. We had a device this big over here. This is a huge one. So we can finally come to almost half of it here, right? And the whole device would also shrink. And this is primarily because of the fact that capacitance depends upon the dielectric being used. So here the dielectric constant, you have increased it almost 15 times, almost 5 times. So 15 to 20, whereas silicon would have 3 to 3.6 or something around that. So devices can be made smaller. And probably this is one of the best results. This on-off ratio is 77. Okay, and then 48, depends upon device to device. And this is the variation is primarily because of the problems associated, stress related problems associated with the devices. Okay, I'm not repeating this, but this is the actual snapshot from the VNA. Then these devices, the switches, they form the basic component of phase shifters. So this is one attempt to generate a distributed MEMS transmission line phase shifter, right? Coming to the ohmic contact switches. So basic, we have seen, we have implemented lots of them. SPDTs. So this is SPST, simple SPST, SPDT, SP4T, and this is hybrid SPDT. Okay. The crux of the problem, as I have explained, is the number of cycles, what you can do, and how much is the on and off time. So with a very small signal, milliwatts, we have done around 725 million cycles for this device. Of course, this is not tested at minus 55, but this has been tested at room temperature and around 50 degrees, 50 to 70 degrees. It has been tested and it works pretty well. Okay, so this is the measured response of the device, giving good isolation over a frequency range up to 10 gigahertz. After that, isolation is poorer and insertion loss is a little higher. Okay, it's more than 1.5 dB in some of the cases. And this shows basically the rise time of the switch, how it actuates. Using this switch, we have implemented what you call the T-type switch matrix. This is part of the redundancy switch matrix used by space people. Okay, so the whole aim is in case one device fails, how to switch on to other one quickly without any reconfiguration. So this is the part of it. Then we have quite a few variants of the switches. This one is what we call toggle switch, aimed to have minimum actuation voltage. So it's like a seesaw mechanism, no? This is almost anchored here. Anchoring point is not touching, it is free. So like a seesaw, it can tilt by itself. So it has to be clamped on one side with actuation pad on this side, right? And when it is to be on, you have to just release that voltage. So you need a very small voltage for this. High isolation hybrid switch, where you have this, the one I have shown earlier, the switch is here, ohmic contact, and this gives you a good response, good isolation over a higher frequency range. Okay, up to this one. Say up to this one, you have the isolation is more than 50 dB. Okay, then how do we fabricate? So how the devices are being fabricated, that's what I just want to cover. You start with a silicon wafer, do the thermal oxidation, generate your actuation pads. So this is now the polysilicon being deposited and patterned. Done that, you grow the best oxide you can grow. Okay, because this will provide you the isolation. Okay, and same thing, underpass. This is the transmission line part of it. Okay, so transmission line and then again oxide. So transmission line, metal, oxide. So half the capacitor you have made already, right? Forget this area. This I'm not interested at present. Just this part. So I have the actuation electrodes done, 1 and 2, with the top insulation, dielectric, and I put floating metal. So metal, this part is metal, purple, and green was your dielectric. And then again, you put metal here. So capacitor with top and floating is already done. Now we put the sacrificial layer. That is basically photoresist, thick photoresist. Okay, do the seed layer and electroplating. You can reinforce it, as I mentioned, selectively you can reinforce the bridge and then get rid of your photoresist. Your bridge is ready. That's how you make bridges. So in terms of lithography, you would need, if somebody, I mean, students, I'm just trying to focus on to the students. If they know lithography, then you would say you would need all kind of slopes over here. The straightforward for patterning metal interconnects, for example. This is for patterning the anchors with positive slope, and this is for lift off. Okay, so lithography becomes a little complex job here. Now this I'm showing one of the steps where the full device is ready, except that you have to remove the sacrificial layer. So this is the photoresist here, brown one, right? If you can see, this brown one is photoresist, and this metallic steel kind of structure, this is the actual metal. Okay, here also the metal structure, underneath is the sacrificial layer, the photoresist. We need to remove this. And if you do it normal dry etching process, sometimes this is what happens. The whole device, which you took almost 9 months to 12 months to fabricate, is gone in one process. Okay, so better results we could obtain was through the wet etching process. Wet etching process, instead of going to dry etching, wet etching coupled with the CPD, okay, critical point dryer. Okay, so this is the process trick which also eliminates the stress. Now I'm coming to one of the problems, which is stress. So the structures, the bridges, the cantilevers, the beams which you wanted to have straight, they may not be straight. They may be having curvature like this. So net result is the response that will shift in terms of frequency, because capacitance is smaller now than what you intended. And stress, you know what stress can do. This is a normal example of clay drying on the road. Okay, and same thing happens in your structures as well. They delaminate, also they curl up because of the residual stress left in the structures. And where does this residual stress come from? So this residual stress may come from the fact that you may be using films which are having different thermal expansion coefficients. One. Another is this could also be coming from the growth mechanism, the lattice mismatch, a substitutional or interstitial impurities, grain size of the structure. So this may be coming from that place also, right? The net result is, if you see this structure here, it's the underlying layer here that starts delaminating, that may break. So one has to find the stress generated. So generated stress can be measured by different set of structures. So I'm not getting into all of them. So you could have fixed bridge arrays, cantilevers, you could have Google rings, or you could have symmetric lancet, which can be used to measure the stress generated in a film. So we take one example of symmetric lancet only. So what we have a structure here. These are interdigit capacitances, right? So the fingers slide into each other, changing the capacitance. The whole idea here was to measure the stress by reading the capacitance change, right? Anyways, looking at the basic principle, what is happening? So wherever you find this anchor, this is on the wafer. So the structure is anchored onto the wafer, and these beams, they are floating. This is also floating. This is freely hanging. Okay, so again here anchored, and this whole structure is freely hanging. So now what happens? Imagine this structure is having some stress, say tensile stress, these two beams put together, right? Again, these two beams. So these beams are attached to this driving bar. So if these are under stress, for example, tensile, the moment you release the structure from the sacrificial layer, this will be pulled back. The moment it starts pulling back, this will put force on this pointer. Same thing would happen here. They'll be trying to pull back this beam, this pointer beam. Now, because of a trick which we are using here, there's slight displacement. This pointer will be rotating depending upon how much force was exerted by these beams, right? So stress, which was basically in these beams, is translated to rotation of this structure. So one could measure it directly with the help of this vernier over here, or by measuring the change in capacitance. Okay, so you can find out. So symmetric lancet you can use to measure the, I'm not getting details of this, but you can measure the stress in this. Now, next is the stress control. You could have different mechanisms, right? One could go for different materials. Instead of, why should we use metal lines only? Why should we have metal bridges only? One could use polysilicon as well, okay, which is very low stress material versus gold. Okay, this is what has been done by GE, but it makes life a little complex in terms of providing the connections. Okay, or one could go for composite materials, tensile, compressive, tensile, sandwich structures, which is again lots of patterning, lots of lithography, and lots of deposition. These are the two things which we have adopted, easier ones. One is the growth mechanisms. Ensure that grain size in control. The roughness and grain size of the electroplated layers are also known to have different stresses. So you tune your electroplating accordingly. Next is, how do you release? How do you get rid of your sacrificial layer? What process you use? If you use dry etching, I've shown the example earlier, RIE, which this is basically etching. Okay, so you are having plasma. So thin membrane subjected to high temperature. What will happen to that? Thin membrane means 2 to 3 micron thick gold electroplated structures. So you can guess from aluminum foil, the normal household foil, if you heat it, normally it is plain simple. If you heat it, it crumbles up. And that's because of the stress release. Okay, same happens to the structures also. So if you adopt this, the other mechanism of release where you don't change the temperature, your structures will be planar ones. So I'm just giving you a comparison between this tip deflection for this test structure. This is our test structure. Okay. So depending upon how it is released. So tip deflection with a reference to CPD, critical point dryer, which is a cold process. And these are the plasma processes, high temperature processes. So tip deflection can be minimized. Okay, this is what I'm showing here. And finally, you could have structures where stress is minimal. Okay, compare the earlier one with this new one. So stress is very, very small in this case. There is some stress still, but structures are more or less planar. Okay, so my structures are coming out planar, and this is a highly compliant structure. This is also planar. Otherwise, this would deform very drastically. Okay, next is the packaging part. So packaging is the homegrown packages, and we adopt a very simple approach. Approach is here is a cantilever. You generate a silicon cavity over here, and you simply glue it. Okay, non-conducting glue. So you fix it. So only thing you got to do is optimize this cavity height, cavity dimensions with respect to the frequency of your switches. Okay, that care has to be taken. So that way this structure has to be optimized. So I'm showing here the cantilever, the switch here, then you invert a cavity. So these connections are available outside. Now, this is CPW basically. So signal line is available here. Now the next part is how to convert this into BNC, triax. Okay, so that can be in an aluminum package. Or that could be if it is a ohmic contact switch, then this is not that critical. It's not must to have BNC, because if you're operating in a low frequency regime. So this is what we have done. This is in-house package switches. Yeah, two of them more. DP, this is SPDT, and this is SP4T. Okay, and then spin-off of the devices could be in terms of, since now we are able to produce cantilevers, interdigitated capacitors, inductors. So one could go for bio devices as well. Okay. So the fundamental here is the LC resonance of, so we have a capacitor here, interdigitated capacitor and inductor coil over here, right? The fundamental principle is if you change the dielectric of this interdigitated capacitor, response will change. The S parameter response of the structure would change. So if you have, for example, healthy blood poured onto this, the response would be something like this, normal blood in S parameters, right? If you have unhealthy blood, infected one, then S parameters would change. Okay, so this is left up to the simulation only, though we designed, but we couldn't make any measurements because this involves lots of other things which are beyond our kind of approach. Another spin-off of the processes we were doing is digital micromirror arrays. And fundamentally, this is nothing but a top plane surface which can reflect light which falls onto this. And this can be reflected by tilting this one. Okay, so this whole thing is tilting mechanism, right? So we have lots of them, and I don't know whether this functions. Just a minute, so let me try. Yeah, so this is the basic function. So it has to tilt, right? And by tilting, this can generate aperture. Okay, so there are many smaller structures over here which can be tilted on demand, right? Okay, you can see this is the fabricated one. So this tilt, and this is another mechanism which goes up and down. So the main application in this case is the in space applications. ISRO needs it for their multi-object spectroscopy. Okay. So with this, I end my talk, and I have here the team which is responsible for this work. Lots of PhD students from my previous place. And here in IIT, we are trying to establish the fabrication facilities. Once they're done, as of now, we are on to design only. Thank you. So now I look forward to the questions.
Thank you very much, Professor Rangra. Nipun, can you take questions from chat box, or you can allow
Yes.
to participants?
So first of all, we'll take questions from chat box and then I will allow.
Yeah.
The first question is from Anshuman Sahai. He's asking, MEMS are really tiny in structure and more critical in operations as shown by some contact bump geometry.
Yeah.
I really wanted to know how MEMS are packed for the final product so that they handle all the jerk, high temperatures and moistures.
Yeah. Okay. The first thing is, like, as far as the moisture is concerned, you have to have hermetic packaging, right? So there's nothing new in that. There's standard techniques where you have to pack it hermetically so no moisture penetrates inside. Next is the temperature. So a temperature is one critical issue, and when you're designing your structure, you have to have that range of temperature. The operating range has to be taken into care. Otherwise, they may deform. Okay. So typically 100 to 120 degrees, you have to take care, like your structure should not deform to that range. Okay. Now is what is that? The packaging part, vibrations, right?
Yes, sir.
Next part was the vibrations part. So whenever you're doing this kind of structures, you will be given specifications in terms of the G, gravitational pull, right? So equivalent of that gravitational pull, you have to build into your structures. So when I say that, what I mean is the structure has to be stiff enough. Structure has, if you talk of a cantilever, the structure has to be stiff enough so that it is not actuated, it is not disturbed by the normal vibrations. Of course, if you just bang it with a hammer, that would be a different case, right? Does it answer the question?
So I hope Anshuman has got his answer. He's saying he's clear now.
Okay.
Next question we do have from himself again. Like, why do we need high resistive silicon substrates? What high resistance has to do with circuitry above?
Okay, if you remember, I have shown the electrical equivalent of the circuit, right? This is basically the silicon wafer as such will add parasitics, right? If he remembers the electrical equivalent I have shown, there I was showing the resistance, which is because of the substrate. If that component is smaller, right, this will limit the response of your structure at high frequencies. Any parasitics? Now, we use typically 5 kilo ohm wafers, right? And that basically limits your parasitic resistance, which I have shown, if you remember, I've shown in the equivalent circuit. Okay. In fact, substrate is part of your structure. Substrate is part of your structure in the sense that it adds parasitics, right? And at high frequency, this becomes more important. Yeah.
Yes, sir. He's satisfied with your answer. The next question is from Dr. Bharti Patil. He's asking how much time is required to design a switch and at what stage you come to know that it is going to come out correct or it has failed.
Okay, this is something which depends upon the expertise of the team, but in general, what happens is, given the scenario, Indian context, most of the fabrication houses, designing could be easier. One could design it and tape out, make the masks. Fabrication may take maybe typically say 3 months to 4 months, right? So until you fabricate it abroad, again, the foundries, they ask you for 3 months time. Indian context, it could be 3 to 6 months. That's how I put it. Then is the actual measurements. There you would know, apart from the simulations, actual test is when you fabricate those structures. So put it 9 months very easily.
Thank you, sir. There is one more question from Amit. He's asking what we do to reduce stress in the device fabrication.
Stress reduction is a very, very different challenge. Okay, to eliminate totally is very difficult, but I have shared 3-4 techniques. One is you could go for composite structure. That means tensile, compressive, tensile. That is one approach, right?
Okay.
So structures which are inherently having, for example, gold, it will be tensile stress metals. So you could go for dielectrics, which would have the compressive stress, right? So you could generate the composite structures. Another is when it comes to releasing the structure. There also you can avoid it. Okay. Another is the electroplating. How do you electroplate? How thick are your structures? So these all things add to your stress generation.
Sir is also asking like why we are not talking about pico technology.
Which technology?
Pico technology.
Well, I'm sorry, I don't know what is pico technology actually. I mean, if it is about the dimensions.
Yes,
right?
sir. He's asking. Yes, sir. We can skip this. We have one more question from Miti. He's asking, is any non-contact pressure or proximity MEMS transducers available?
Proximity transducers.
Proximity and pressure MEMS transducers.
Yeah, they are available. They are available in the market. Definitely, yes. I mean, none of the devices which I mentioned are kind of which are not available. Everything is available as of now. Okay.
Okay.
Depends upon the application. Typically depends upon the application. For example, redundancy switch matrices, the one I was talking about, there are the phase shifters. They are still not available so freely. Okay. Especially to the defense sector and others, strategic sector.
Okay.
Yeah.
The next question is from Sumit. He's asking, what is the role of bridging and networking atoms in SiO2 structure formation?
Well, this is something deep into materials, right? Bridging and non-bridging, that will decide the quality, no? What is the crystalline structure coming up, isn't it? So,
yes,
right, impurity, introduction, amorphous, right, crystalline structure. So bridging, more it's into crystalline shape. Yeah.
Yes, sir. The next question is from Nidhi Rani. She's asking, does proof stress affect construction?
Proof stress, I couldn't follow like what she's really asking for. Proof stress means proof stress.
Yeah, she has not elaborated it. She's just asking, does proof stress affect construction? Maybe we can skip this question.
I think this should be the proof mass basically.
Proof mass basically, yeah. Yeah.
Yes, no.
Yeah, not proof. Yeah. Okay. If that is so, I mean the whole mass of the structure, right? That will definitely have some impact on this, right? You can make structure thicker, so it will be less deformation, right?
Yes, sir.
Yeah.
One more question, which was asked initially, maybe you have answered it in your slides. Like, which method is used to remove the sacrificial layer, as stiction can be an issue?
Okay.
And how do we overcome the residual stresses?
Yeah. So as far as stiction is concerned, if you go for, typically this is the problem students face. Okay. It's like a stiction basically, what you're dealing with is thin membranes. In all MEM structures, you are dealing with thin membranes. And when I say thin membranes, I would just like to remind you of shaving blades, old shaving blades, 7 o'clock. If you have two of them, put them together in water, right? Make them wet, and now try to separate. So it's very difficult to separate those because of the layer of water in between. Same happens with these membranes. The moment you do try to remove, so basically sacrificial layer removal is, it could be wet etching also.
Right.
You have to dissolve the photoresist in some sort of chemical. It could be developer, concentrated developer, right? Okay. So the moment you do that, then you put in DI water. Now, if you dry by just taking out from DI water, they will never be separated.
Yes, right.
So one way out is you take this structure, don't bring it out, keep it in DI water and take it to what we call CPD, critical point dryer.
Yes, sir.
Okay, so there actually this works on the triple point of this alcohol carbon dioxide, liquid carbon dioxide, right? So under particular temperature and pressure, you evaporate the fluid. You had DI water. Now instead of DI water, you can change it to alcohol and then change to CO2, right? Liquid CO2 without any time being exposed to the dry ambient, right? So now inside the machine, at a particular combination of temperature and pressure, you evaporate this liquid carbon dioxide, okay?
Yes, sir.
And that is where you can separate them out,
Okay.
okay? So this is one method. Another is of course dry etching,
Right, sir. Right, sir.
right? I've shown both of them.
Yeah, I think we are running late now. So
Okay.
thank you very much, Professor. Yeah, Nipun, you can pick up now.
Okay, so one more participant was there, Tarun. He has raised his hand. Maybe we can take his question. Or...
Yes, you take his question and then close. Yeah, unmute him.
Tarun, I have unmuted you. You can ask your question.
Hello, am I audible?
Yeah, Tarun.
Yes,
Go ahead.
yes.
Yeah, sir, I wanted to ask if we can make a magnetic actuator. Like I was interested in some energy harvesters using a nickel foil and a PZT layer over it, a bimorph kind of cantilever. Can we actuate them in plane and out of plane? If you could provide some idea.
Yeah, actuation, see, if it is a magnetic structure, no, externally you can actuate it, isn't it?
Yes, sir.
Externally you can actuate. Now in which plane you want to actuate, how you want to control it, is that the question?
Yeah, actually, I was trying to actuate in both way, in plane and out of plane, by applying two magnetic fields.
Okay.
One using proof mass, and one say in plane using another magnetic
Got it.
pole systems.
Got it. So
Yeah.
basically the problem boils down to how do you anchor your structure, right?
Okay.
How do you provide the maximum area over which your field could interact?
Okay.
Right? So anchoring problem, this is basically an anchoring problem. If you want to have both the things in plane, so if it is say for example Z actuation around Z axis, it's much easier, right? It's much easier for a cantilever made on a simple silicon wafer, right?
Yes.
But if it is to be in plane, then it could be a little tough. That's what my personal hunch is.
Okay, because this kind of structures are based on magnetoelectric effect. Probably you might be aware of that. And thing is that I have to apply two fields simultaneously, one DC
So
and one AC, to
if
lift
it
the
is
time reversal symmetry.
Excellent, got it. But see, the point is, if you want to do it externally or internally, external deflection could be little difficult to manage. Internally, it could be a little easier. There you can manipulate, you can generate the mechanism. Say if it is to be electromagnetic, no, right?
Yes, sir.
So
Yeah.
electromagnetic coils can be put inside.
Okay.
But externally, so you can, so the arrangement could be in such a way that it does both the functions, Z as well as X, Y. That's what you want, no?
Yes, yes, yes.
You want Z as well as you want X and Y.
Yes, sir. Yes.
Okay, so in my opinion, this is both for a single structure, both the things for a single structure represents a higher level of complexity. It will be the anchoring. How do you anchor? How do you make it the anchor parts, right? And how do you fit in the actuation mechanism?
Okay. Okay, sir. Yeah. Thank you very much, sir.
Thank you, Tarun. Thank you, sir, for your such a nice talk. Moving on to our next speaker, I really feel delighted to welcome Professor Mukesh Kumar, who is an assistant professor in the Department of Physics, IIT Ropar. He did his MTech and PhD in physics from IIT Delhi. He then worked as a postdoctoral fellow at National Renewable Energy Laboratory, USA, and South Dakota State University, USA, from 2010 to 2013 on nanoscale charge transport of organic solar cells and flexible thin films for next generation flexible optoelectronic devices. Before joining IIT Ropar, Dr. Kumar was working for Hizitron, Minnesota, USA. Dr. Kumar has received many awards like Young Scientist Research Award from Department of Atomic Energy, Board of Research in Nuclear Sciences, Bhaskar won Solar Energy Fellowship from Indo-US Science Technology Forum, Young Achievers Award from Bhopal Atomic Research Center, Government of India, Faculty Research and Innovation Award 2019 from IIT Ropar. Dr. Kumar was also selected as a member of Indian National Young Academy of Sciences and National Academy of Sciences India. Recently, he received the prestigious Fulbright Nehru Academic and Professional Excellence Fellowship from United States India Education Foundation. He was also the recipient of Research Foundation Fellowship to work as a visiting faculty at Binghamton University, State University at New York. So with this, I would like to request Professor Kumar to kindly deliver today's talk.
Thank you very much for kind introduction, and thank you very much for Professor Mahesh Kumar for his kind invitation.
Professor, yeah, Professor Mukesh, you are not audible. Can you bring this microphone here too?
Sure, sure.
Your volume is low.
The screen is visible.
Yes,
Right
yes.
now.
Yeah, now it's.
Okay, okay.
Hmm.
Okay, so good morning, everyone. And thank you very much, Professor Mahesh, for kind invitation. So today I will discuss about the ultra-wide bandgap materials for solar blind photodetector application. So if you want to know more about our laboratory at IIT Ropar, what we are doing, please do scan this and it will redirect you to our laboratory. Okay, so IIT Ropar, so we total have 23 IITs, and all of you know, and Ropar is here, and it is about 300 kilometers from Delhi, and IIT Jodhpur is here. So IIT Ropar is having a very green campus. It's newly built campus, and it is on the bank of Satluj River. Okay, so you can see this Satluj River forms a wetland. So I would like to start with an acknowledgement. So I sincerely acknowledge IIT Ropar and Solar Energy Research Initiative, Department of Science and Technology, and Board of Research and Nuclear Sciences, Department of Atomic Energy, and DRDO for their funding that help us to establish functional and renewable energy materials laboratory at IIT Ropar. So what we are doing in IIT Ropar, so we are working on functional and renewable energy materials. So we are working on flexible and indium free transparent conducting oxide thin films. These are the special functional materials which has high band gap, which is more than 3 electron volt, and high conductivity like metals. The carrier concentration in these materials can go up to 10 to power 20. Okay, so and also the mobility is very good, about 50 or 20 to 50 or even 100, more than 100 centimeters square per volt second. So these materials can transmit the light entirely from the visible region, and also they have the good electrical conductivity. So these materials have lots of application for solar cells and photodetectors and all optoelectronic properties where you need to transmit the light through these materials, and simultaneously these contact work as a transparent. So these materials has a property of insulator as well as metal. Now on the other side, we are also working on earth abundant CGTS solar cell. Okay, so these solar cells, you can have these solar cells like we have CGTS and then CDS, and then this is a top layer. So I told you these materials can be used in a solar cells. So what we are doing, we are optimizing these materials in the lab and then utilizing that in the different application like solar cell as one of the transparent window or in other applications. So here you shine the light from the top. Okay, the light goes through these layers, and then it is absorbed in copper zinc tin sulfide here, this solar cell. Okay, and then carrier is separated out, and then you can collect electron and holes at the two electrode, and this start to convert the sunlight into electricity. Now the other side, we are also working on 2D materials. Is a lot of attraction in the recent time because of their high surface to volume ratio and their stability. There is no dangling bond, so you can have miniaturize the devices at very small scale. So we are working on 2D material based gas sensors and photodetector. Because of their tunability band gap, you can go all the way from like UV region to NIR region. So today I will discuss about this section where we are working on solar blind photodetector and what are the solar blind photodetector and what are their application for civil and militaries. So these are the facilities available in IIT Ropar. So that is available in the lab. So this is a multi-sputtering system where we have 3 guns. So 1, 2, 3. So that system actually simultaneously sputter 3 targets. So you can make a alloy as well as you can also make a multi-layers one by one. And this is the system where we have the 2 chamber interconnected. Okay, so you can make this system we are using for solar cell fabrication. So here you make a different layers and then transfer this sample to the another chamber where you are making a another layers and then finally making a metal contact. This is a chemical vapor deposition system that we are having in a lab that is being used for growth of 2D materials. And these are the characterization facilities. That is a low temperature Hall measurement, and this is like broad source. You can have with the monochromator. You can have different wavelengths. So that is being used for solar cell fabrication, solar cell characterization, as well as photodetector characterization. And these are for the electrical characterization facilities available in the lab. So today I will discuss about the solar blind photodetector. So first I will discuss about what are the solar blind photodetectors, how they are special in contrast to the general photodetectors, what are the current challenges, and why we are discussing about the beta gallium oxide solar blind photodetector. And then I will discuss some of our recent results and then conclusion. So what are solar blind photodetectors? So as you know, the photodetector is a device that converts the light signal that you are signing to the electrical pulse. So once you are signing a photon, so it is exciting and creating an electron hole pair in semiconductor that is separated out at the end electrode, and then you say that we have detected this photon. So why this solar blind photodetector coming special? So if you are considering about the solar radiation, then we are saying that is going from like all the way to IR or even beyond IR, then visible light, UVA, UVB, and UVC. So if we consider IR like that is from 700 to 3000 nanometer, and the visible from 400 to 700 nanometer, the UV is divided into 3 parts: the UVA, UVB, and UVC. So all this radiation is going through this naturally provided protective ozone layer. So this IR is going, visible is passing through, UVA and UVB is also passing through, but UVC is blocked by this ozone layer because this UVC light is hazardous to the humankind. So it creates like change in our DNA and cause the skin cancer also. So this UVC radiation is not present in the Earth atmosphere. So then why we are worried about this radiation and making this photodetector? Because you can have the artificial radiation on Earth that may be created by using a fire or a plume of your missile. So any small creation of this radiation can be detected very easily. That's why this photodetector that is working in this region is known as solar blind photodetector. So these photodetectors are extremely, this UVC light is extremely dangerous. Okay, so we can, any small portion is available on Earth can be easily detected even in the under the intense sunlight because there is no background radiation available. So based on that, what are the applications of the soluble ion photodetector? So you can have this ozone hole monitoring. So this UVC radiation will pass through wherever we have the big holes in the ozone layer, and you might heard that there is a once we have the big hole in ozone layer, then all this radiation is coming on Earth's surface, and that is creating many diseases, including skin cancers. This UVC light can be utilized for UV sterilization. And recently, like coronavirus is everywhere. Okay, but initially, if you remember, in up last year in March or April, there was a solution to kill this virus by using the UVC light. But if there is a UVC light and it is little bit leak, okay, then it can also harm the human being. So we need a UVC photodetector to give a foolproof protection. We can have the missile tracking application. So this photodetector can easily track this missile because the plume of this missile emit all sort of radiation, including UVC radiation. We can have the flame detection, space exploration, and non-line of sight communication. One of the example is flame detection is like you can have this hydrogen flame that is incompletely invisible to naked eye, or propane flame that is visible. But if you see that since it is emitting all the radiation, so that is also emitting UVC radiation. So we can easily detect that, and that will be helpful for next generation hydrogen fuels for the safety application. So UVC, as I was mentioning, that UVC for COVID-19, so you can have this UVC which is like peaked at 260 to 270 nanometer. Okay, and there are like available kind of an oven available in the market. Okay, that is designed by DRDO, like different laboratory, IITs, and other universities, and that is easily available. But these have the like compact detector just to avoid any leakage of this UVC light. And we have seen last year that is UVC light is being utilized for sterilization of big compartment or hospital accessories during this pandemic. So what are the characterization for the photodetector? How to characterize whether this photodetector is working efficiently or not? So just like like other sensors, there are different parameters. Okay. The first parameter is responsivity. Now, since you shining the light, it is creating a current. So how much current is creating? How much current you are creating and collected divided by the incident power. Okay, so you are shining some power and then creating a current. So it will be IPH by P0, and then this will be like efficiency and then charge divided by the photon H nu energy. Okay, so that will be the responsivity that will have the unit in ampere per watt or ampere per milliampere per watt, like that. Now we have the external quantum efficiency. What is external quantum efficiency? That is number of electron hole pairs generated and collected divided by the number of incident photons. So this is the external quantum efficiency. There are other different parameters like linear dynamic range, dark current, impulse response, and persistent photoconductivity. So persistent photoconductivity means like if you shine a light pulse and then it is creating an electron and hole pair. But if there are defects, okay, so what will happen? These defects will trap these carriers and they will slowly release these. Now suppose you are shining a pulse and after 2 seconds you shine another pulse, but slowly they are emitting these carriers for a 2 minutes or 3 minutes. Then the second pulse that you are shining after 2 seconds will not be detected by the material because of the persistent photoconductivity. So we do not want this persistent photoconductivity to be happen in the material. Okay. So there are 6 S requirements for a photodetector to be working perfectly: high sensitivity, high signal current to dark ratio, spectral selectivity means the photodetectors should be specifically sensitive only to UVC light, okay, and should not be sensitive to any other light. It should be very high speed, it should be stable, and it should be self-powered. So if you can have the self-powered function, then we can operate that at remote locations. The another general characteristic parameters are the dark current. So the dark current, as we already mentioned, that the current that is created, okay, when there is no light shine on the photodetector. So we want that this dark current should be as low as possible, so that when we shine the light, okay, then the amplitude of the generated current is very large. Response time. So once we are shining the light, okay, it's just like a gas sensor. Now you have a very good background because of the like excellent talk. So now the response time is similarly defined as a gas sensor. So the change from the base value to the saturated value, and then time required to change from 10% to 90%, that is a response time, and then decay time, like from 90% to 10% is the decay time. Okay, so that response time critically depends on what are the type of the quality of the film, what are the defects present in the film, and so on. There is a specific detectivity that is characterized how well a weak signal can be detected by a photodetector. Okay, that depends on these parameters, where A is the effective area under the illumination, this is a dark current, and R is the responsivity. Okay, the reverse of that is the noise equivalent power. Okay, so that tells how weak signal a photodetector can detect. So these are the parameters which characterize, which tells how good our photodetector is working. Now, what are the material challenges at present? Now, you might heard that there are varieties of photodetector reported in literature. What about silicon? Silicon is the most studied element in the periodic table. Okay, but the problem with the silicon is that it has a band gap of 1.1 electron volt. So it will absorb all the light shorter than 1100 nanometer. Okay, so one issue is that. Second issue is that silicon is an indirect band gap material. So it required a thicker layer, okay, to absorb the complete spectrum. So, and also it generates a high dark current, so it required a cooling. But the selectivity issue can be solved by putting in a filter, wood filter, that will filter out all the radiation and will pass through only UVC. Okay, but the problem is that once you are putting this filter, then the device is no longer a small device. Okay, that requires the force is going up, and the device is not miniaturized at a small scale. Now the second solution is that we can alloy the materials. So we know that if we have a two materials, okay, of a nearly same lattice parameter and different like band gap, we can alloy them to tune their band gap, like aluminum nitride and gallium nitride. So we can tune their band gap from 3.4 electron volt to 6 electron volt by adding more and more aluminium. But putting more aluminium, more than 40%, to tune their band gap in UVC region creates a lot of defects and strain inside the material, which creates a lot of defect and instability of the material. Second thing, we can have maybe zinc manganese oxide, because you can have the band gap tuned from 3 electron volt, that is corresponding to zinc oxide, to more than 7 electron volt, that is corresponds to manganese oxide. But the amount of manganese oxide that you have to infuse with the zinc, then it is kind of a phase segregated. So if you have the zinc oxide and manganese oxide, and you try to tune the concentration to tune their band gap, then they are phase segregated, and then the device performance is compromised. Diamond is another choice, but that has a band gap of 5.5 electron volt. So the cutoff wavelength is even shorter than the UVC light. And also the problem is growing the diamond on a larger scale is another challenge. And that's why actually is a high cost. So provided all these, we have another challenge, which is a suitable substrate selection. So all these devices that the literature reported, they are reported on sapphire substrate, okay, silicon carbide, or gallium oxide. So all these substrates are very expensive, okay, and they are not yet matured. Even gallium oxide, if you are talking about gallium oxide as substrate, although you can have 2-inch, 3-inch wafer available, but it's only one source from Japan that is available. So we have to be a bit careful. So why we are not optimizing this already on mature technology like silicon? Okay, that can easily go to already mature technology. Okay, and the wafer is available from 6 to 12 inch. It's less expensive. But the problem is there is a high lattice mismatch between silicon and gallium oxide. Okay, so as a material for UVC photoretractor, we can have the gallium oxide. So gallium oxide, why gallium oxide? Because it is a direct band gap, so it required a very thin layer to absorb the complete spectrum. It is intrinsically solar blind, which corresponds to band gap like 4.9 electron volt. Ideally, spectral selectivity because of its band gap, high thermal stability, high chemical stability, and high breakdown field, which is about 8 million volt per centimeter. All these properties makes the gallium oxide suitable, okay, for UVC photodetector. Beta gallium oxide. Let's go into a little bit more detail about gallium oxide. So the gallium oxide had a different polymorphs, okay, like it is a stable polymorph, which is a beta gallium oxide, which is monoclinic in nature, it having a metastable phases like alpha, epsilon, okay, and gamma, or it has a unstable phase which is cubic in nature, which is delta. So all these phase, if we are heating at high temperature about 500 to 600 degrees centigrade, they convert to monoclinic, which is beta gallium oxide. So we can have like different phase mixing and different multi layers of these, okay, for the design of the better efficiency solar blind photodetector. What are the open challenges for gallium oxide? The open challenges for gallium oxide is it is absence in the p-type doping. Okay, because if you want to design a photodetector, you can have the p-n junction where you create a carrier, an electron hole pair with a selective incident radiation, and because of the infield electric field, the generated carriers will be separated out. Okay, and then it will start working good. However, in gallium oxide, there is absence of p-type doping. Also, it is poor thermal conductivity, okay, which is very small, which is 11 to 27 watt per meter Kelvin. And there is always trade-off between the responsivity and response time. Let us look at what are the solutions possible. Now, since there is absence of p-type doping in gallium oxide, so there is no bipolar devices. What we can do actually, we can make it by unipolar devices and then charge carrier separation via other methods. What could be the other methods available? So we can have a photoconductor type of a device. That means if you shine the light and then it will change its conductivity. Okay, and then we can measure that change in the conductivity by making an ohmic contact on the material beta gallium oxide, and then the device will start to work. But the problem is that now since we have the ohmic contact, okay, the carrier can go easily, so the dark current will be very high, and then the response will be very slow for this type of the devices. So what are the other possible solution available? So other possible solution is that we can make a Schottky barrier. So we can select a metal contact to the gallium oxide, which can make a Schottky barrier contact, so that the carrier going from one electrode to another materials and then electrode, this you can reduce drastically. So the dark current will reduce drastically in this type of the devices. You can make a MSM, metal semiconductor metal type of a contact. Okay, so you can make like say titanium, aluminum, and then titanium, aluminum. So there is a barrier is formation here, and then this they like at dark current there is a very less carriers is going through that, maybe through the tunneling, but dark current drastically reduced. Or you can have the heterostructures. So the heterostructure with another materials of p-type nature. So all these solutions people are being explored to have the high efficiency UVC photodetectors. Poor thermal conductivity in gallium oxide, how is affecting the performance? So the thermal conductivity, as already mentioned, is very poor. Okay, in contrast to gallium nitride, or even if you are talking about the diamond, which has a very, very high thermal conductivity. Okay, so the gallium oxide, it can be grown on a high thermal conductivity substrate. Okay, so these are few, or you can have thin down the materials so that there is a phonon boundary scattering results in the better thermal transport. So these are the suggestions, and these are the direction that people are exploring to design these photodetector working in like UVC region. These are the literature, recent literature we have collected, and just to see their performance. So if you can see that these are the gallium oxide based solar blind photodetector, and this is the responsivity I discussed. So this is ampere per watt, and this is the rise time. Okay, so we required, like if you are talking about a silicon, so the silicon is having a performance like a response time in nanosecond, but the responsivity is somewhere in like somewhere here. So it is in milliampere per watt in UVC region. Okay. However, if you are talking about a respective number like microsecond, and the responsivity as high as 1000, so still in gallium oxide we do not have a single point in this region. Okay, even if you are talking about heterostructures. So this region actually is a desired region that need to be pushed in this direction. Okay, so there is always trade-off between the responsivity and the response time for the photodetector application. So what we are using, so the material is fixed, so the gallium oxide. Now how we are growing this gallium oxide in the lab? So we are growing the gallium oxide in the lab by using the RF sputtering. Okay, so this is a glow actually is taken in the lab. So this is the RF sputtering. Okay, and then you can see this is the plasma. And just for the sake of students, so this is how this sputtering gun look like. Okay, so this is RF magnetron sputtering. So they are magnets. Okay, so these are the magnets, and in the center they are like NS in such a way that you concentrate the electrons just near to the target. Okay, and then just to increase the ionization of the argon ion that is being used inside the chamber. Okay, and this is one of the target you can see. So this is like this ring is created because of this more sputtered region from a particular area. Okay, so this is the gun that we are using inside the lab. So this is the RF sputtering. So in RF sputtering is the capabilities. Again, this is for the students. So the RF sputtering, this is a radio frequency. So generally we use 13.6 megahertz signal. Okay, and why it is capable to sputter the even insulator target? So just to understand that, so we have a sputtering system where we have the target, and then which is capacitively coupled with a matching network. So you can understand that if we have the RF signal, okay, and then in a positive and negative cycles, and the plasma is created. So in the negative cycle, okay, negative cycle, we have the positive, it attract the positive ions, okay, towards the target. And since because their mass is very, very large in contrast to the electrons, so we have very small ion current. However, if we have the positive cycle, during the positive cycle, it goes very high electron current. But since this is capacitively coupled, okay, there is no current flows. So this cycle that you are applying, it automatically shift towards the negative voltage just to make this current positive during the positive negative cycle zero, so that the self bias is achieved, and this technique is capable to sputter even an insulator target. And because gallium oxide is kind of insulator, so that's how actually we are able to sputter, control sputter of these targets, and we can make a film starting from few nanometers to up to micron. So during the sputtering, not only like if you can have the different growth parameters, like you can have substrate temperature, growth pressure, sputtering power, many parameters you can have. But once you are varying, suppose one of the parameters, suppose you are varying a sputtering power, and you are observing some parameters like stress and conductivity. Suppose these are the two parameters you are observing, and you change the sputtering power from 25 to 50 watt, and suppose your stress is reduced, and you are correlating the sputtering power change results in the stress, that may not completely right. Okay, so you can have, generally you should, if you want to deconvolute the growth space, you should generally apply a design of experiment approach where you need to discuss about the interaction of the growth parameters. Like suppose sputtering power and growth pressure might be interacting, and there is a two-way interaction is more effective, that is enhancing or reducing the residual stress. So that is true actually for any system. If you are changing some one parameter out of few parameters, and you are saying that any change in your device or any change in your measurement is because of that, may not be true. So you have to go back and check, is there any interaction between the growth parameter might be responsible for that. So this is the system that we are utilizing for the growth of gallium oxide in the laboratory. So you have the three system, and then we are also associated with a residual gas analyzer that is continuously monitoring the gas, the plasma gas, the ratio of argon, oxygen, nitrogen, hydrogen, all these gases with time, how their variation is changing. Because suppose you have inserted the oxygen, okay, inside, because target is gallium oxide, and this is a gallium and oxygen, and the sputtering depends on the maximum momentum transfer by the sputtered gas, which is argon. So the argon is not having like similar mass with gallium and oxygen, so there will be not be a maximum momentum transfer. However, there will be a difference in the sputtering of gallium and oxygen from the target. Okay, so you have to monitor the gas, how they are changing with the sputtering from the system. So it keeps the like system check and consistency. Once you grow next time the thin film, then you know how much pressure was there for the oxygen. Okay, so now I will discuss few case studies. Okay, so that is based on this the papers that we published. So first one is a seed layer assisted growth of gallium oxide on cost-effective silicon. So if you remember, the one of the big challenge was to use the silicon as a substrate for gallium oxide, but there wasn't a like difference in this lattice parameter of gallium oxide. So what we have utilized is, these are the different temperature cycle for the growth of gallium oxide. Okay, and then like suppose this case we heat it up to 650 degrees centigrade, and then this is substrate annealing. This is gallium oxide that you are depositing at this cycle at 650 degrees centigrade, and then we are annealing it. However, in the other cycle, what we have done, we heat it up to 650 degrees centigrade. This is the substrate annealing, just to reconstruction of the surface, and then we heat it up to 700 degrees centigrade. Okay, and then grown a seed layer of gallium oxide on silicon, and then come down to lower temperature about 650 degrees centigrade, and then we post annihilate the layer whatever we have deposited seed layer, and then next is the growth of gallium oxide thin film, and then post anneal and then come down. So these are the different temperature cycle, just to see what parameter is controlling the performance of our thin film. So if you compare here the different samples, and then this is the power, like we are varying the power, and then this is the growth pressure, this is the substrate heating, and this is seed layer, whether we have seed layer or not. So we realize that if we are having a seed layer on silicon substrate, then the quality of the thin film is better, which is polycrystalline in nature. Otherwise, in other cases, the quality of the film is not as good as when we are using a seed layer. And most of the cases, the film is amorphous in nature. So the initial growth parameter critically affect the quality of thin film, and then we will see that how the performance is controlled by these growth parameters. So let's compare the polycrystalline two extreme samples. Like this is a polycrystalline sample, gallium oxide, and this is the amorphous film. So you can see that this is atomic force microscopy just to get a 3D views about this 3D information about the gallium oxide film. So this film is amorphous in nature and is quite smooth. However, the film grown with a high temperature seed layer is having bigger particles. So further we confirmed by XRD, like you can see that XRD which has a bigger crystallite size. And the RMS roughness, if you are concerned about, so this is a quite smooth amorphous film, which is quite expected. And then this polycrystalline film is having a high surface roughness, which is about 11 nanometer. Now these are the device made finally. So we made a contact on top of the gallium oxide, and then just to characterize these samples, and these are with all these details. So we coated aluminum and chrome and aluminum for addition and this metal contact. Okay, so that is a before measurement. We also heat the device for the better addition of the metal contact. Now these are the characterization of these devices. So you can have this dark current. Okay, so the dark current with high temperature seed layer and without high temperature seed layer. So that means this one is the polycrystalline and this is amorphous. So it's quite expected that is showing a higher dark current, and that is high dark current is not good for the performance of the photodetector. This is the photocurrent, that means actually it is with the wavelength, and this is the photocurrent minus dark current for this with wavelength, and this is the photo to dark current ratio of the photodetector at 250 nanometer wavelength. So from all these results, it is confirmed that the photodetector which was grown with a high temperature seed layer, okay, on the silicon, is showing a better performance. Now, as we discussed the two important parameters, the responsivity, okay, response time I will discuss in the next few slides. So the responsivity is coming out to be like about 96 ampere per watt for this solar blind photodetector. And you can see actually this photodetector is quite responsive only in the UVC region. Okay, and thus like visible to solar blind like UVC light is having more than 1000 like ratio. So the responsivity is nearly 100 at 250 nanometer, and external quantum efficiency, you can see that it is very large. Okay, and that is because of the internal gain, which is tau 1 by tau 2, and where tau 2 is the transit time, which depends on the this d square channel length, voltage applied, and the carrier mobility. Okay, so if you want to increase more and more gain, so what you can do, you can increase the lifetime of the carrier, which is tau 1, and then tau 2 is the transit time, so that you can short this channel, and you can increase the mobility of the carrier. So these are the parameters that people played to enhance the performance of the device. Now let us see how fast this photodetector can respond. So we compare the at zero bias, we compare the performance. Okay, so that if you are signing on and off this UVC light, so where we off and then yellow actually is on. So when we on the light, so the current is continuously increasing, but it is consistently increasing its base. Okay, what is happening now is that it is continuously increasing. So that means this sample has a lot of defects and persistent photoconductivity. However, if you are talking about the polycrystalline one, there is a digitized 0 1 kind of a signal. Okay, and you can see that this photodetector is the performance of single cycle, which shows the performance is in milliseconds. So this means actually this photodetector, which is grown with the seed layer, is quite fast. Now you can see that the performance stability. The third parameter is the performance stability. So we have checked initially, it is like more than a year. The photodetector we found is quite stable. Okay, and as I mentioned that on-off ratio is more than 1000 in the high temperature seed layer, and dark current is very low. So that is the mechanism actually that we propose. So you can have like the gold contact you can have, and then there are some defects and the dangling bonds on the film that is result in the like difference in the Schottky barrier height, and that is resulting in the like cell power performance. There are oxygen vacancies also, which is like suppose you are shining the UVC light, and then this UVC light creating electron hole pair. So some of the electrons are captured by these oxygen vacancies, and then they are slowly releasing that. That is responsible for their persistent photoconductivity. That is continuously increasing their signal. However, for seed layer, we have quite less defects, okay, and that is responsible for lower the current, okay, and then higher performance. There is less persistent photoconductivity. That's how we are having a better performance of these photodetectors. So then we again actually compare the data with the literature. Okay, so in contrast to the cost-effective substrate, the performance is also better in contrast to the other photodetector reported in literature. So graphically we can understand better. So there is a rejection ratio here multiplied by 1000 and the response time, and x-axis we have the dark current. So you can see that rejection ratio is high, it should be very high, and the dark current is very low, and the response time and dark current is coming here. So that is response time is also very low, which is in millisecond, and the dark current is very low. So that means this photodetector is performing very well. Now, if we compare this photodetector with this already available in the market, like Thor Lab and all these, so the silicon photodetector people use, first disadvantage that photodetector can work in 200, 2000 nanometer, but the problem is it is not selective in nature. So if you want to only detect UVC light, that will not work. And also in UVC region, the responsivity of the silicon photodetector is much less than the gallium oxide photodetector. But gallium oxide photodetector, the disadvantage still we have is the lack of p-type. So that means the carrier is not separated out very efficiently or very swiftly. So the response time the silicon has in nanoseconds. However, for gallium oxide, it is reported in like in milliseconds only. So that is the problem, and that's why actually this is the area of research that lots of people are working on that. Now, the next thing I'm going to discuss about is spectrally selective solar blind photodetector. Now, if you are talking about like human eyes, let's discuss something about the plasmonics first. So what we have done actually in this work, we have used plasmonics like silver nanoparticle. Okay, so silver nanoparticle is helping us to enhance the light absorption beyond the fundamental limit of the material. So we know that the material has a fundamental limit for the light absorption, okay, but it can be enhanced by using different means, and the plasmonics is one of that. So we are using plasmonics, and for that, if you see that human eyes, okay, the conventional photodetector, the problem is it can detect all the wavelength shorter than their band gap. That means any energy greater than their band gap, this semiconductor will detect. But photodetector will not distinguish if suppose silicon, if you shine a light or yellow light or a blue light or a green light, silicon photodetector will not tell you what is the wavelength, okay, because it will only detect and tell you that yes, there is a photon coming, but what is the wavelength of photon, what is the color, no. But you see the nature, the human eye, we can distinguish the visible, and where is the sensitivity, we can distinguish what is the color, and even in the literature it is reported that the human eye can detect a single photon. Okay, so in that direction we try to see can we distinguish two different wavelengths, at least two wavelengths. But what is the problem? The problem is that suppose you want to design a photodetector that can distinguish two photons of a different wavelengths, then we have to have the two different materials of different band gaps. Okay, then the complexity in designing and then putting these materials is again a challenge. So for that, what we have done, we utilize already optimized gallium oxide thin film, Okay, and then what we have done, we coated with the silver nanoparticle, which was grown specifically by using a clad technique, just for their uniformity. And then we have made finally a device. And here, this is the light absorption graph for this complete film that is coated with the silver nanoparticles. And you can see that this absorption graph, this blue one, is showing the enhanced absorption in UVA region. So that means the UVA light getting enhancedly absorbed in the gallium oxide. So that will help us to create a dual nature. Like it will, the photodetector will also respond in UVC as well as in UVA region. So let us see what the results are saying. So these are the currents, and you can see that the signal strength, this is UVC, which is a 44 nanowatt per centimeter square, which is very weak signal, and UVA signal, which is 167 nanowatt per centimeter square. And the black one is a gallium oxide, bare gallium oxide in dark, and this is gallium oxide when you shine the UVA light, and this one is gallium oxide when you shine the UVC light. The photodetector shows some response. Okay, now here this is the current for once you deposited the nanoparticle on the photodetector. You can see that how enhanced the performance of a photodetector is. Okay, just to see the important parameters like responsivity. So the responsivity enhanced from usual about 100 ampere per watt to around 250 ampere per watt. And also we start to see another signal in UVA light. Okay, so that is again actually is very good signature that the photodetector is working in two bands. This is the EQE, again it is very high EQE. The enhanced EQE is observed for bare gallium oxide and coated with the nanoparticle. This is detectivity and this is linear dynamic ratio. So all these results shows that the performance of the photodetector is not only enhanced, but it also start to show the response in the UVA and UVC region. Now the next parameter is the cyclability. Let us see how the photodetector is working in two different regions. So when we have the bare gallium oxide and then you shine the UVC light, that means this is corresponding to the band gap of the gallium oxide. So once as soon as you are shining the light, it is showing the current generated in the system. Once you off the light, it is going to the background current of the system. But if you shine UVA light on bare gallium oxide, that is no silver nanoparticle, then you can see there is no response. However, if you shine the UVC light on gallium oxide coated with the silver nanoparticle, then you see the response. And once you shine the UVA light, then again you are showing the response. Okay, so that means the silver nanoparticle make functional to this gallium oxide and which is making a performance in UVA and UVC region. Let us try to understand what is happening. So in bare gallium oxide, once you are shining this UVC light, what is happening? It is this energy is capable for the band-to-band transition in gallium oxide. So this electron hole pair is generated and then it is being collected by this end electrode. So it is like you are shining, electron hole pair generated and this electron is coming here and then the current is flowing inside the system. But once you shine the UVA light, what is happening? This light is not capable for band-to-band transition. However, the hot electrons generated in the gallium silver nanoparticles is injected into the gallium oxide. Then you can see these carriers is being injected and which is responsible for the reverse flow of the current. And then you can see, you can distinguish UVA and UVC light by using these photodetectors. So this is really a unique properties of this photodetector that you can distinguish two different wavelengths by using this photodetector and this plasmonics. Now the next I will discuss about flexible photodetectors. So the flexible photodetectors, have lot of application. Like if you are going out and then you want to have the dynamic change of a UVC light, it's a UVC light you are being exposed, then you can have this photodetector on your skin, okay? And then through your mobile, that can keep tracking how much dose of UVC light you are being exposed. Okay, so for that we need a cost-effective photodetector and flexible. For what we have done for that, we have taken this PET substrate, okay, and then we coated that gallium oxide. Since it is a completely transparent, so you will not be able to see that, okay. And what we have done, this is a XRD of the gallium oxide, which shows that it's an amorphous in nature. And instead of conventional metal, what we have done, we deposited indium zinc oxide. Okay, if you remember, initially I discussed that indium zinc oxide is a transparent conducting oxide. So it can be used as an electrode for different devices. So we use that in gallium oxide. So since it is oxide, so the device will be completely invisible. Okay, and oxide will have the better adhesion with the oxide. So just to keep that in mind, we have deposited this IZ on gallium oxide, and then you can see that the device is completely transparent. Okay. Now this is the performance that shows the responsivity, that is ampere per watt, okay, and the wavelength, okay, and then this is the PET and gallium oxide, and then these are the interdisted IGO electrode. Just to compare their performance, we also deposited silver electrode. And then this, you can see actually this is the performance. So this is once you are bending it, okay. So what you are doing, you are bending it, okay, and then doing a bending test. So once you are bending at 30 centimeter, okay, 20 centimeter or 10 centimeter was radius of curvature, how their performance is changing. So initially, after bending, you can see that the performance a little bit degraded, but after that the performance is consistent. While for metal electrode, that intersects actually this insert shows the damage, completely damage of this metal electrode, and you can see from this graph, this so you can see that this is the control device, and after the bending at 10 centimeter and 20 centimeter, that 20 centimeter is the device is completely failed. So that means the metal electrode is not suitable for flexible devices, or we need to have some kind of engineering with the metal electrode to be useful for the flexible devices. Now, these were the single cycle test, but now at 30 centimeter radius of curvature, what we have done, we repeated that 200 cycle, 200 cycle, and 500 cycle. Okay, so then we found that the performance initially degraded, but after that the performance is consistent. So that means this IGU electrode is quite stable for flexible devices. Now, one step further, what we have done, we utilize a paper, the normal paper that you write in the laboratory for printing. Okay, what we have done, this is a scanning electron microscopy of a microfibrous paper, and then what we have done, so we made a bottom electrode by hand. So this is by graphite with a pencil, and then silver electrode. So we have the two different type of metal, so that will help us to separate the carriers efficiently. Okay, and then this is what we have done. After that, we put this substrate inside the sputtering system, and then put it gallium oxide film at room temperature. Okay, so that is amorphous gallium oxide. After that, the device is ready. Okay, now you can bend it, twist it, on that device actually still works. So this is a performance after some time. So even we found that the device was working after 2 months, and we have done something unique that I will discuss. And once you are utilize that, you can burn it and then mix to the soil. So there is no harm, there is no kind of a waste. Okay, so the device you utilize, burn it, and then just you are done. So this is the scanning electron microscopy images. So this is a gallium oxide of grown on a paper, and these are the like bottom electrodes. So you can see that the gallium oxide on silver electrode side, and this is graphite electrode side, and this is the bare gallium oxide on paper. And then we have done this mapping, elemental mapping, that's silver, gallium, carbon, and oxygen. And then we found actually it's quite uniform. We have also utilized, not only that, we have utilized a different type of paper like butter paper and different type of the pencil, okay, just to optimize that. And we found that the paper is most suitable because it is highly rough, and the gallium oxide and this electrode actually is kind of a uh, like this because of this high roughness, it is helping the better performance of these photodetectors. Now this is the performance of the photodetector. You can see that this is zero bias. So we have not applied any bias because of this different work function of the material. The bottom electrode, it is helping out to separate the carriers. And then this is a single. You can see the single cycle, and then the performance you can is coming out to be respective numbers. And with the different intensity, you can see that with different intensity of the light, it is working well. Not only that, so in this picture, you can see that we have tested this performance up to 100 volt, and we found this photodetector working perfectly fine. So there is no problem of this photodetector. And this is the bending and the twisting test. So you can see, like, if you are bending at a different radius of curvature, okay, initially the performance is degraded, but after that it is quite stable. So this is bending test, and this is a twisting test. So we achieve a quite like good photodetector working in that region on this paper substrate. This is performance on a different cycle at a extreme bending. So we found that up to 500 cycles is quite stable. Now there is a one more thing that is coming to be in your mind, that since it is a paper, okay, and then if it is a paper, then even a single drop of water can damage this. So what we have to do? So what we have done? So we painted that, okay, just like a packaging of the device. So in the crude way, what we have done, we put an animal paint on that, okay, which is a UV transparent, and then this is the contact angle measurement on the device without any paint. So you can see a few like about 1 minute, the water is absorbed inside the paper, and then the performance is degraded, like the contact angle is reduced. However, if you are painted that paper on both sides with this paint, then the contact angle remains same, and then you can see that the performance of the device without and with paint, and so there is no difference. And then you can see that it's a burning test. So after that 1 second and then 3 seconds is completely burned, and then there is a weight difference of this. So the most of the things actually is already converted, and then we have very small remnants of this photodetector material, so it's completely kind of a green. And then this is the mechanism actually that we propose. So since there is a bottom electrode of a different function, so we found a different Schottky barrier height that is helping us to separate the carriers in the photodetector. Now, finally, I will discuss about the extreme environment of this photodetector. Now, all these photodetector is promised to be used in extreme environment, like for space exploration on nuclear detectors, or where we have high energetic ions and different radiations. So we try to we initiate the study in this direction. So we try to see how this gallium oxide is performing under the extreme environment. So this, like already mentioned, that is soluble photodetector can be used for nuclear infrastructures and space exploration that require the material to be immune or partially immune to these damage. So if these radiation are present, then it should not happen that your photodetector once exposed to this radiation, then it stop working. Okay, so we have to have environment testing of this photodetector to be done. So what we have done, we sign this photodetector with shift heavy ion radiation, that is an extreme heavy ion with an energy of 100 MeV, okay, with a high dose at Inter University Accelerator Center, New Delhi. So what we have done, so this is a silicon wafer, and then we grown amorphous and polycrystalline. Just want to see that what is the performance changes on polycrystalline and amorphous material, and then we irradiate that samples with a silver 7 plus ions at energy of 100 MeV. Okay, and then we irradiate that, and then finally made a MSM contact, and then test the device. So these are the XRD measurements of these samples. So amorphous, the sample that we grown at room temperature is showing the amorphous nature. However, the sample grown with the polycrystalline is showing a polycrystalline nature. However, after radiation, both the samples is recrystallized and then showing only one peak, which is little bit shift. That is maybe because of the strain inside the film after the irradiation. This is the surface morphology. You can see that. So this is a surface morphology of controlled gallium oxide amorphous sample, and this is a polycrystalline. And now this is B actually is the radiated amorphous sample, and D is the radiated polycrystalline sample. So you can see that there is a huge change in the morphology of a gallium oxide, and this sample, amorphous sample, start to show some kind of a pinholes. Okay, and then is this polycrystalline is kind of a hammer down. So this roughness is drastically reduced. However, in this one, the roughness is increased that we measure by using atomic force microscopy. So you can see that the control polycrystalline and amorphous roughness is amorphous was showing 1.68 and 5.43 nanometer. The agglomeration that is inside these samples, agglomeration of the grains and the formation of nanopore structures in irradiated amorphous sample, this one is observed. So the change in that, and we also observe there is no change, no change in the optical property, like the band gap of the film was remains same, the composition was same after radiation, and that all this radiation was done at liquid nitrogen temperature. So what are the changes happening? Why these changes are happening? So these changes actually is happening because of this energy loss by the incident ion inside the film. So if we have this incoming ions, the silver ions, okay, so which can have the electronic energy loss and nuclear energy loss. So the electronic energy loss, where this incoming ions is coming very swiftly and then only interacting with the electronic system in a very small time scale. So this when this it is interacting with this electronic subsystem, it is giving their energy to that, and then finally it is giving their energy to the lattice system, and then locally it is assumed that the temperature is going very high, and then there is a recrystallization, melting, and then freezing immediately to this subsection, and then that's why there is a recrystallization of the material observed and the change in the morphology of the system. The 2 points are very important here, that the entire thickness of a sample is about 300 to 400 nanometer, and during that region, okay, so the dominant energy loss is the electronic energy loss. Also, the range of this silver ion, that is more than 8 microns, so which is much more than the thickness of the film. That means the silver ion is not embedded inside the film. Okay, there is no silver ion in the gallium oxide. However, this silver ion is getting an embedded inside the silicon somewhere, which is not affecting the performance of our photodetector. So that the more detail actually you can find in a thermal spike model. It's a quite well-established model that help us to study, to investigate how and what changes is like in the material after this swift heavy ion radiation. Now this is the performance of the photodetector. So you can see that how the current are changing in the controlled dark and the amorphous control, okay, at 250 nanometer, and then amorphous irradiated in dark and amorphous irradiated at 250 nanometer. So all this, the most important parameter is responsivity. So you can see that the responsivity of the photodetector is very large, okay, and after radiation, the performance decreased. Okay, so that means the like the material is not 100% immune to this radiation. There is a change in the performance, like the decrease in the performance of the photodetector once it is exposed to this kind of radiation. Okay, so this is the again like once we shine the light on and off, then it shows quite stable performance even after radiation. But even like the performance decreases after the this shift heaven radiation. So this is the responsivity and like for this amorphous and polycrystalline film. And then you can see that this is the control sample. And after radiation, the performance decrease from 6.6 to 1.6. And then this is the self-anneal. So what we have done, we have annealed self-anneal. That means we kept the sample without anything for 3,600 hours in the lab, just to see whether the defects generated inside these films is self-annealed or not, whether the performance is improved automatically or not. So we observe this slightly increase in the performance for amorphous film. However, the polycrystalline, the performance even further reduced. After that, we start to heat the sample for 100 degrees centigrade, 175 and 250 degrees centigrade. And at up to this temperature, there is no change in gallium oxide. That means amorphous gallium oxide will remain amorphous, okay? And polycrystalline will remain polycrystalline. So there is no change in the phase of the gallium oxide. However, we observe the drastic enhancement in the performance of the photodetector once we heat at 250 degrees centigrade at 90 minutes. And that may be because of this nanopores in the gallium oxide, amorphous gallium oxide, and the gold is diffusing out, and that is maybe responsible for that. Now, this type of the work, actually, there is a detailed investigation is further required. Whatever the defects are generated, okay, and how these defects are responsible for reducing the performance and enhancing the performance after annealing and all this process. So this is the initial studies, and more studies, the more work actually is coming up in this direction. So with that, I would like to summarize. So we optimize the photodetector fabrication on cost-effective silicon substrate, and we have also done a photoelectron using silver nanoparticles utilized for polarity switching, and unique negative photoconductance was observed. And ultra flexible colorblind photodetector on even paper substrate was observed, and radiation hardness on gallium oxide photodetector was investigated. So this work actually is done by Damanpreet Kaur, the PhD student, and Kanika Arora. So I would like to thank all of my students from the lab. And thank you very much. And thank you again, Professor Mahesh, for kind invitation. And if you want to know more details about our laboratory at IIT Ropar, please do scan that, and it will redirect you to the lab homepage. Thank you very much, and I'll be happy to answer the questions.
Yeah, excellent talk, Professor Rakesh Kumar. So, yeah, Nipun, are you there? Can you take the questions from chat box?
Yes, sir. Thank you, sir. Thank you for such an informative session. The first question is from Shashikant Sharma. He is asking, can we grow gallium oxide over silicon substrates to fabricate photodetectors and other device structures? What substrates do you suggest over which we should gallium oxide to get desired performance? And second question is that from Shashikant again, can we grow gallium oxide using thermal evaporation also?
Okay, so first question, which substrate is suitable? So you can grow gallium oxide on silicon substrate, and I have observed that the performance is very good. So if you can do some kind of engineering, then the performance of the gallium oxide grown on silicon substrate is very, very good. Regarding to your second question, can we grow the gallium oxide using thermal evaporation? You cannot grow thermal gallium oxide using thermal evaporation because of its high melting temperature. But yes, you can do electron beam evaporation for this gallium oxide. But you can try maybe gallium by using gallium and then you creating a oxygen plasma. So that is known as the activated reactive evaporation. So you can use a gallium source and then you can use a plasma, oxygen plasma. So the gallium will evaporate and then mix with the oxygen and can make gallium oxide on substrate. So partially you have to modify it if you already have the thermal evaporation system, but yes, you can use.
Thank you, sir. The next question is from Ashok Kumar. He's asking, can we do p-type doping in beta gallium oxide? Or
Actually, it is a open challenge. So if you nobody has succeeded yet, but people are trying. The problem is that the top of the valence band is made of a is kind of a flat, okay, and also whatever the doping you are doing is kind of a it's not in gallium oxide it is not succeeded yet. Many people are trying to dope it with p-type, but there is no success yet. Theoretical papers are there, but there is no experimental evidence of p-type doping in gallium oxide.
okay, thank you, sir. Again, there's one more question from him. He's asking, how can we change the phase of gallium oxide after RF sputtering deposition?
So there are different phases available, and by using a sputtering, if you grow it, it's very difficult. There are people report that by using MOCVD, and controlling the phase is not very easy for gallium oxide. So you can have maybe chemical process you can try, but sputtering you have the amorphous, and then as soon as you will hit that, it will convert to directly to beta gallium oxide. There is intermediately converting to alpha or another phase is very difficult by using the sputtering.
Okay, thank you, sir. There is one more question from Amit. He's asking, can retention time for a particular compound change when detected at various wavelengths?
Can you please repeat that?
Yes, sure, sir. He's asking, can retention time for a particular compound changes when detected at various wavelengths?
I'm not getting.
So he's asking about the retention time for a particular compound. Does it change if we detect at various wavelengths? Yes.
Okay. No, yes, actually, these are the metastable phases. Okay, so if there is no detailed investigation on gallium oxide. These are the least studied material, gallium oxide, if you see in literature. Okay, so the research actually started maybe it's not very quite mature technology, and the majority of the issues are because of their open challenges like there is no p-type doping and thermal conductivity is very poor. Okay, carrier mobility is also not as good as like nitride materials, but their strength like bigger substrates are available. So it really attracts people now to work on that. But yes, if you have the different phases and if you keep it that, so there is no detailed investigation whether they are converting back to beta gallium oxide. So I can give you one example, like if you have a tin doped indium oxide, if you grow it amorphous, it at room temperature, with time it try to convert to the polycrystalline one.
Okay, right, sir. Uh, there is one more question from Sumit. He's asking, is there any difference between photoconductive and photovoltaic mode in photo detectors?
Yes, so there is a big change actually. So the one is like if you are talking about photoconducting, that means there is no inbuilt electric field there. It is changing the conductivity of photo detector, and you are detecting that the change in the is kind of a conductivity. However, in photovoltaic, what you are doing, you are establishing an electric field inside that is helping to separate these carriers.
Okay, okay, sir. Sir, Ashok is again asking one more doubt. Like, can we do annealing at higher temperatures?
Yes, yes, you can do annealing up to like 1000 degree or even more than that. But even less temperature, about 600, 700 degrees centigrade, all the in metastable phase will convert to beta gallium oxide. So further annealing may improve the polycrystallinity, but the phase will remain same.
Okay, thank you, sir. There is one request from Dr. Neha Goyal. She is requesting you to please show one previous slide before your summary slide. Maybe she wants to ask something.
Yeah, you can mute when she is asking some question.
Yeah, so sir, before summary slide, can you is it visible?
Yes, sir, it is visible, but Dr. Neha, can you hear me? Dr. Neha, I have unmuted you.
No questions, sir. Thank you.
Okay, sir. I guess she just wanted to see this slide, sir. Maybe she. Thank you, sir. So, with this, sir, we are done with the. Just a second, sir. We are done with the question answer session. May I request Professor?
Yeah.
Sir, yes, sir.
Yeah, Professor Mukesh, very excellent talk. I have one small doubt because I have seen this current is in the nano ampere. So
Mhm.
how to connect this with the readout circuit? Because mostly readout circuit you need in the milliamperes.
Yes.
How to make the complete system?
Yeah, actually, this prototype device we are working currently with Sri Pilani just to make that. But this since it is current is in very small, so we have to make kind of converter that can convert this nanoampere to volt immediately at the device scale. Otherwise, it is very difficult to flow this current in the circuit.
Okay, okay. Yeah, thank you very much. So yeah, very excellent talk, and yeah, thank you for accepting our invitation and delivering this nice talk. I hope this one participants they got the new ideas in the area of the detectors, basically how to make the detector, and you have very well explained from the basic concept this one from the definitions. So thank you very much.
Yeah, thank you very much,
And
Professor Mahesh, for invitation. I really enjoyed.
yeah. Thank you. Yeah. So now, yeah, participants, we can meet after lunch, 2 o'clock. And next talk is by Professor Chandrasekhar Sharma from IIT Hyderabad. So yeah, thank you. Thank you, Professor Mukesh, and all the participants for attending this talk.
Thank you, sir.
Thank you.
Yeah, good afternoon, Chandrasekhar. Hi, good afternoon. Can you hear me? I think you are muted.
Yes, sorry. Yeah.
Yeah,
Hi,
yeah.
good afternoon, Mahesh.
Yeah, good afternoon.
Good afternoon, sir.
Hi, good afternoon.
So may I request you to share your presentation? Meanwhile, we can.
Okay, yeah, sure.
We shall be beginning formally at 2 p.m.
Okay, yeah. Can you see the slides?
Yes, sir. Absolutely.
Is that okay?
Yes, sir. It's fine, sir.
Okay, perfect.
Yes, Nipul, we can start.
A very good afternoon to all panelists and participants again in the afternoon session. I, Nipun Sharma, welcome you all to the AICT Training and Learning Academy sponsored 5 days online workshop on nanosensors. In the morning session, we had really nice talks from Professor Kamaljit Rangra and Professor Mukesh Kumar, who gave us the detailed conceptual insights of their research work. So moving on, I would now like to welcome and introduce our next speaker to the audience, Professor Chandrasekhar Sharma, who is currently Associate Professor in the Department of Chemical Engineering at IIT Hyderabad and is also Chairperson of Indian National Young Academy of Sciences, INYAS. As Chair, INYAS, Dr. Chandra has been instrumental in taking several initiatives for the capacity building and gender inclusiveness in science technology. Dr. Chandra has received several awards and recognitions at national and international level, including the recent honor of prestigious DST Swarn Jayanti Fellowship in Engineering Sciences. He is also serving as a PAC member of various SIR and DST committees, including Technology Development Program and Waste Management Technologies. His research interests are carbon MEMS, polymers, carbon nanomaterials for energy, environmental, healthcare, and sensor applications, nature-inspired functional surfaces, and waste management. He focuses on translational aspects of his research. He has more than 100 international peer-reviewed journal publications to his credit and guided 11 PhD students so far. He has filed 14 national and international patents so far, out of which 2 international patents have been granted. Very recently, Dr. Sharma was recently in news for developing oral formulation of amphotericin B drug, which is used to treat plaque fungus, where he is trying to partner with a suitable pharma industry to take this work to the clinical trials and commercialization. With this, I again welcome and request Professor Chandrasekhar Sharma sir to please deliver today's talk. Thank you, sir.
Thank you. Thanks a lot, Nipun, for nice introduction. And I would like to thank Dr. Mahesh, who is the main coordinator for organizing this workshop on nanosensors as a part of this ATAL AICT training. So as you mentioned, we will be talking about the electrospun polymer and carbon nanofibers as ultra-sensitive nanobiosensor platform. So I'm sure you must have heard the various talks in last 1.5 days, including today before lunch session. Maybe this will be slightly different because we'll be talking about the electrospun fibers uh, as a platform to develop various kinds of nanobiosensors in our lab. So before I go into the topic, let me just briefly tell you about our group at IIT Hyderabad. We call our group as a Carbon Laboratory, which stands for Creative and Advanced Research based on the nanomaterials. So we primarily work with these three major areas, nanostructured carbon materials and carbon MEMS. So we do the we start with the polymers, we do the patterning of the polymers, then we make 3D polymer structures and then convert them into the carbon structure. Some of these things I will touch upon in today's lecture, that how we can convert the polymers into the carbon. Then we also work with the biomass derived carbon and multi-scale carbon. Our group has really pioneered in a very exciting precursor of carbon, which is a candle soot or any kind of soot. And we have demonstrated the use of this soot, candle soot carbon, for energy storage devices. And basically, we work with both kind of carbon, hard carbons and graphitized carbon. And some of the applications of these carbon materials are in energy storage devices, for example, lithium ion, lithium sulfur, battery anodes, or recently we have moved to the supercapacitors also. We also work with these materials, carbon materials, for novel adsorbents, and also some of them are using in the sensors, which I will discuss briefly today. We also work with the nature-inspired functional surfaces, where we take the inspiration from the nature and try to replicate those features which are found in the natural surfaces using the techniques like soft lithography. And by doing that, we create superhydrophobic and self-cleaning surfaces, anti-reflective surfaces like that. And third major area which I'm going to cover today is electrospun polymer and carbon nanofibers. And again, here we work with a wide variety of polymers, including the block copolymers, and we make the nanofibers by electrospinning. I will tell in detail what is electrospinning. And we provide the structural functionality, not the chemical functionality, structural functionality in these nanofibers. For example, we can make the porous fibers, we can make hollow fibers, we can align the fibers in a particular direction. We can also address single nanowire. And some of the applications of these polymer and carbon nanofibers are in energy as electrode materials, in the environment for air and water filtration, in healthcare like drug delivery, and also in sensors, which I will touch upon today. So in another way, if you really look area-wise, then we work in the energy, mainly in the energy storage devices. And there we use nanostructured carbon materials, as well as inorganic nanomaterials like metal oxides for developing the electrode materials for batteries and supercapacitors. Environmental aspects, we have worked with the nanofibers based adsorbents, biomass derived carbon as adsorbents, and also our lab has developed a technique in which we can recycling the polystyrene directly using the citrus peel extracts. And third major area for us in terms of application is the healthcare, where we use the nanofibers for controlled drug delivery vehicle. And also we have demonstrated the use of these nanofibers for feminine hygiene. And today's topic, the use of these nanofibers for ultra-sensitive biosensing platform. Okay, so let me touch upon the sensors. Of course, I'm not going into the details, which is, I'm sure you might have come across these basic things about the sensors in previous talks. And also, I'm sure that your interest in this workshop is because of the fact that you know something or you want to know something about sensors. So sensors, basically, we can say that these are the some devices, some systems where the whole purpose is to detect the change in the environment. Change, we can sense the change. That's why you sensor. And that information of the change of the environment is sent to you as in terms of electronics or something by computer processing. And there are various kinds of sensors. Of course, right now, everything, many of the things are in the smartphone. So smartphone sensors, again, there are different kinds of sensors. And one thing we have to mention that all the living organisms, including the human being, they have the biological sensors. We see the change in our, we realize, we feel it. So sensing is something inherent ability of living organisms. Now, when we talk about the sensors, then there are different kinds of sensors. So for example, chemical sensors, biosensors, nanosensors, and they are different because of the different sensing mechanism. So for example, chemical sensors, they transform the chemical information, for example, composition or concentration or chemical activity, partial pressure, into a useful signal which can be read, which can be interpreted. Biosensors, where we detect the analyte, and that is having basically a biological component, and that's a physiochemical detector is used. And these biosensors, there are different kinds of analytes like tissue, microorganisms, cells, enzymes, cell receptors, etc. Nanosensors, basically we are having the nanomaterials as an active element for the sensor. And because of the high surface area, as we know about the nanomaterials, we achieve the higher sensitivity using the nanosensors. And when we combine the biosensing and the nanosensing, then we call it as a bio-nanosensors also. And well, I need not to go into the detail again, but I am just telling you that how important this area is. So in the medicine, biotechnology, sensors, they are used in day-to-day life. Okay, many of us, we use them without realizing that, what kind of mechanism is there behind these tools. So these are all commercial applications of these sensors, including the thermal or including the chemical or electrochemical for diabetes, temperature, pregnancy test, nowadays COVID test, rapid antigen test, and all this. This is all based on sensors. Now, as I mentioned, that sensors plays a very vital role in all aspects of healthcare, and not only in healthcare, but in other fields. Given the current situation, the healthcare is something, one of the utmost important area. And there are various kinds of sensors which are used to prevent, diagnose, or monitoring and treatment monitoring. So various sensor systems have been developed for that. However, there are challenges as well as opportunities for the scientific community. What are the challenges? They are listed here. Like one is called SSS, sensitivity, selectivity, and stability. Okay, that's always a challenge, that how to enhance the sensitivity, how to increase the selectivity, or how to increase the stability of your system. It should be compact, wireless. Nowadays, everything on your smartphone. You can do the real-time detection from far distance. These should be implantable, especially in the healthcare inside the body. Point of care, extreme point of care, where especially in the rural areas where you do not have very sophisticated instruments, sophisticated facilities. Even in those harsh environments also, your sensor platform should be able to work. That is a challenge and opportunity. Now, extreme point of care, especially which is now critical global challenge, and WHO requirements for these extreme point of care diagnostics, which is basically tells us about the assured criteria. Assured means affordable, sensitive. So it should be affordable because you are talking about the rural environment. It should be sensitive enough, specific, user friendly, so that you do not have enough skill set required to use that system. Rapid and robust, equipment free, minimum instrumentation, that is a minimum requirement for epoch or extreme point of care diagnosis, and deliverables to the end users. Okay, so these are some of the requirements for extreme point of care diagnosis, where we talk about the sensors for EPOC. Well, with this brief introduction about the sensors, there are various technologies for epoch, like calorimetric, electrochemical, optical, and all. I think there are various talks in different strategy, different technology in this workshop. And mainly, I will also be talking about the electrochemical sensing technology, which is definitely low cost and compact, with enhanced sensitivity and the limit of detection, as we will see today in the talk. So coming to the electrochemical sensor, as I mentioned, I will be briefly talking about the electrochemical sensor. So electrochemical sensor is nothing but a device or freestanding consolidated device that uses an electrochemical transducer, okay, to provide the real-time analytical information. And if the transduction element is in the direct contact with the biological recognition element, so I'm talking about the electrochemical biosensors, and then we call it as electrochemical biosensor. And the information usually refers to the concentration of the target species, and the target species in this terminology is called analyte. Okay, so if you see this figure, that tells about the basic component of electrochemical sensor. It includes a receptor, a transducer, and function of the receptor, which is to capture the analyte, which is a target species from its environment. And then receptor interacts with the analyte in a very selective manner. That's how you determine the selectivity. Of course, the selectivity depends on the affinity of the analyte to bind with that receptor. And then this recognition element, they are having receptor sites, and these sites are integrated with the recognition element. And sometimes, so that's called the labeling. In certain cases, there may be no distinct recognition site. Still, the element can interact with the analyte. And that is the good thing about the label-free sensing. Okay. So then basically the sensing, these electrical signals, which are converted by the transduction element, they are now very small, and they are basically amplified using the amplifier. And later this information is processed by the computer, what we generally see. So that is basic component and mechanism of an electrochemical sensor. Now here, if you see the electrochemical sensors, there are various types of transduction methods for the sensing mechanism. Okay, electrochemical is of course one, optical, resistive, capacitive. So, or broadly, we can see there are two types: physical and chemical transduction. Physical transduction is based upon the change in properties such as like electrical conductivity, dielectric properties, refractive index, or mass of the recognition element, like that. While in chemical transduction, it is change in the chemical composition. Okay, so for example, let's say optical it's based on the emission or absorption of the light due to the change in energy level of transduction element in the presence of analyte. When we go for capacitive and resistive transduction, here the interaction of the analyte with the materials cause the change in the dielectric properties. Mechanical transduction, mechanical effects, it is based upon the change in the mass of the transduction element when it is binded with the analyte. Similarly, thermometric transduction is based on the change in temperature of the transduction element due to the absorption or liberation of the heat upon the conjunction with the analyte. So electrochemical biosensor, as I was mentioning, the advantage includes like label-free approach is possible. High sensitivity you can approach. It's quite rapid and simple instrumentation. Sorry. Now, when we talk about electrochemical sensors or electrochemical transduction, it includes a range of electroanalytical techniques, okay, that are used for the purpose of this transduction. So there are some of these techniques listed here. For example, chronopotentiometry, amperometry, chronoamperometry, voltammetry, where current is measured by varying the potential, electrochemical impedance spectroscopy, where we measure the dielectric property as a function of frequency. Okay, so the most widely used transduction mechanism is amperometry. That includes the whole range of techniques where current is measured as a function of an independent variable. That is sometimes typically the electric potential or the time. Chronoamperometry, when it is measured as a function of time. And voltammetry, which is a kind of subcategory of amperometry where current is measured as a function of potential. Mainly this amperometry is widely used in the enzymatic sensors. It is also used along with the affinity recognition with the analyte. When analyte is electroactive or electroactive label is attached to the analyte. And similarly, electrical impedance spectroscopy that measures the change in the impedance of the electrochemical cell as a function of the frequency of applied AC perturbation. So these are the various techniques which are used in the electrochemical transduction. Now, there are various applications of these electrochemical sensors in the environmental area, healthcare, food industry, defense, and whatnot. Okay, some of them are listed here. I'm not going into the detail, these are self-explanatory. Now, why, so coming to the very focused topic like nanofibers. So why we are interested in nanofibers and what are the implications of morphology of your platform? This picture is here, which is basically nothing but time versus response time versus the initial analyte concentration. And if you see this plot, the planar surface as compared to the nanoparticles, nanofibers, they are having higher response time. And so nanomaterials, especially the nanoparticles, nanofibers, because of the higher surface area, the sensitivity or the response time that increases, that is enhanced a bit, okay, because it is now mainly diffusion based phenomena. So basically, I mean, this plot is based on this equation for an ideal receptor where T is the time, and naught is the the concentration, number of molecules captured, and rho is the initial analyte concentration, and df, that's the interesting thing I will talk about it. That's a fractal dimension. Okay, so for different kinds of morphology, you have different fractal dimensions. Sometimes it's 0 to 1, 1 to 2, depending on surface fractal, mass fractal. So these are all parameters which play an important role in determining the response time, sensitivity, and all that. And when we see this plot, we see that these nanomaterials like nanoparticles, nanodots, nanofibers, they carry a certain advantage over the planar surface. However, when we compare with the nanofibers and nanoparticles, of course, nanoparticles are a little better, but the margin is so less. And if you compare it with the synthesis process, maybe it might be difficult to synthesize very uniform quantum dots, nanodots, and as compared to nanofibers. So without losing much in terms of sensitivity or in terms of response time, you can still work with the nanofibers rather than nanoparticles. Now, when we talk about the nanofibers, something which we need to know for this particular talk is electrospinning. So electrospinning is a technique that is used to produce these nanofibers, whether it's a polymer nanofibers or carbon nanofibers. You have to start with electrospinning. So let me explain the technique electrospinning in a couple of minutes. So you have typical this medical syringe, okay, which is having this metallic needle attached to it, and you fill the polymer solution by from which you want to produce the nanofibers, and you push this syringe so that this polymer solution comes out through this needle at a predetermined rate. Okay, sometimes there is a controlled spinner rate which pushes it very uniformly and very slowly, like few microliter per minute. And this needle is connected to a high voltage power supply. Okay, when I say high voltage power supply, it's really high voltage, something of the order of 10 kV, 20 kV, like that. And then there is a collector screen on which you try to collect the nanofibers, and which is grounded to make the circuit complete. Okay, so now what happens when you push the polymer solution, and a closed schematic at what happens at the metallic needle is shown here. So when you push the polymer solution comes out from the needle, and initially it forms a spherical droplet. Why? Because of the surface tension. The surface tension always try to minimize the polymer, always try to minimize the surface, and the spherical surface is the minimized volume. And since it is connected to the high voltage supply, this drop is charged, positively charged. When you push the solution further, and you are increasing the voltage also simultaneously, what happens? Because of the electrostatic forces, now they try to act against the surface tension force. And as a result, this spherical shape of the droplet starts distorting in terms of elongation. Okay, as you can see in the figure B. Now, you increase the voltage further beyond a threshold voltage. What happens? You are further elongating this, and finally it is elongating and forming a jet. And as soon as it starts forming jet and and it starts traveling towards this, because the circuit electrostatic forces are working between needle and this. Now what happens? Each of these jet is positively charged. So what happens? Multiple jet starts erupting, and each of these multiple jet is positively charged. So what happens? They start repelling each other. And that's why if you see the path, it is not simple, straightforward. They go into a very tortuous path. Okay, they cover a lot more distance than the actual distance. And what happens in this process when they are traveling from the needle to the collector, which is a distance of around, let's say, 8 to 10 centimeter actually, they cover much longer. And while they're traveling, the solvent inside the solution, because of this nano thinning, it starts evaporating. So what is happening? They are traveling, solvent is evaporating, so they are further becoming thinner and thinner and thinner. So by the time they start depositing on the surface, most of the solvent is evaporated. And that's how you get ultra thin nanofibers without solvent. So that is what the electrospinning process is. So what are the advantage of this electrospinning technique? It is cost effective, very cost effective. In just few lakhs, you can start with electrospinning. You can produce long and continuous nanofibers. You can really make the nanofibers from a wide variety of polymers. Okay, there are of course certain parameters which you need to look into, but otherwise there are hundreds of polymers which can be spun into the nanofibers. Each of fiber deposition variety of nanofibers can be constructed like here, or maybe I will show in the later slides, and it has the potential for industrial processing. So in overall this process, there are various parameters. Okay, like for example, polymer solution itself. So as I mentioned, almost all the polymers can be electrospun. So there is a certain parameters. For example, how much is the polymer concentration, what solvent you are using to make the solution of the polymer, what is the conductivity, surface tension, dielectric constant, volatility, molecular weight, because ultimately you are basically stretching the polymer chains, okay, to convert them into the nanofibers. So if your molecular weight is not really very high, then you will not end up, you cannot stretch it further. So there should be a certain molecular weight, there should be a certain range of conductivity, dielectric constant, because ultimately it's an electrostatic force which are acting upon it against the surface tension. So it should be dielectric and it should be conducting enough. But as I mentioned, there are wide variety of polymers which satisfy some of these criteria, and they can be electrospun easily. Then there are certain process parameters like how much voltage you are applying, how much is the polarity of the tip, how much is the feed rate you are pushing this. Then what is the distance between this needle and collector? What is the collector geometry? Whether it's a straight plate like shown here or a rotating drum, that all depends. That all determines the final morphology. And finally, the certain extra environmental parameters. For example, how much is the temperature, humidity, and all that. Because as I mentioned, while the jet is traveling from the needle to collector, it starts evaporating the solvent. So the rate of evaporation of the solvent will depend on temperature and humidity and all these parameters and volatility of the solvent. So what I mean to say is that here you are having certain all these parameters with you, okay, with which you can play and control the nanofibers morphology. And that's why I am saying that this particular technique is able to give you a wide range of nanofibers with different kinds of structural functionality that I will show in next few slides, that how that can be utilized for enhancing the sensitivity of a sensor. So let me start with the first case, polystyrene block PMMA, PS block PMMA, that is block copolymer derived electrospun mesoporous nanofibers. So I will tell you how we can generate the mesoporosity in the nanofibers, and then I will explain how this mesoporosity is utilized to enhance the sensitivity for a given system. So here, so let me try to very briefly tell you about the block copolymers. We have heard polymers, now there is something called block copolymers. So generally the polymer is a macromolecule consisting of repeating units, as we know, which are called as a monomer. And if it is a single type of monomer, then it's called homopolymer. And if it consists of more than one monomer, then it is called copolymer. Now, block copolymers, they are formed when there are two chemically different polymer segments. Okay, we call it as block. So for example, in this case, there is a block of styrene, there is another block of methyl acrylate. So that's why it is called polystyrene block PMMA. Okay, PS block PMMA. So block copolymers, they are basically self-assembled materials. And when you allow them for the microphase separation, based on the different blocks, okay, when you allow them these blocks to distance apart in the self-assembled manner, you get periodic nanostructures. Some of them are shown here, that how you can control the different kinds of nanostructures. by microphase separation in these blocks. Why microphase separation? Because if you see this thing here, this is one phase, this is second phase, which you have made as a block, and now you are allowing the microphase separation. How we do that, I will tell you. But when you allow this separation, that creates the gap, nano gap. And there are various parameters which you can control to determine the different kinds of ordered mesoporous nanostructures using these microphase separation. Okay. So in this particular case, we have taken the PS block PMMA, and that is basically available in 3 different molecular weight combinations, as I mentioned here. PS 57K, B PMMA 25K. What does it mean? Polystyrene polystyrene block is 57,000, PMMA block is 25,000. Similarly, PS PMMA, this one, it is having 96.5 thousand molecular weight, it is 35.5. And this one is 280 and 290. As I mentioned, the molecular weight is an important parameter to determine the electrospinability of your solution. Okay. So then what we have done, we have made this PSPMM solution, 3 different solutions like 18%, 20%, 14, 16, and 3 and 4 and 5. And we have optimized the electrospinning parameters. So as I mentioned, you push the polymer solution, start the high voltage power supply. Here in this case, like shown, it is a rotating drum rather than a flat screen for the collecting the fibers. And that's how you deposit the fibers. Let me show you how this jet starts and coming out in a multiple jets from the needle. So we have optimized and finally we have figured it out that this particular polymer with 5-8% solution, PS PMMA 280 290 combination with 5-8% solution, that gives you very nice nanofibers without any beads or without any continuous fibers, 0% beads. There is no particle or there is no impurity in the nanofibers. With the average fiber diameter around 336 nanometers. Now, what we have done after making these nanofibers, that's what mesoporous nanofibers. So basically, we have created the porosity in these fibers, and that is done basically here. So here, if you see, we have done the annealing of these nanofibers. The annealing basically gives you the allow use the microphase separation. As I mentioned, you have to allow the microphase separation so that these blocks they are now distant apart, and that creates the nanodomains, which is basically the mesoporosity. So for that, we have done the thermal annealing. In literature, this particular block of polymer has been used especially in the thin films, not in the nanofibers. We were the first to produce the nanofibers from this block of polymer. So we had to optimize these annealing conditions because the conditions for the film is different for the annealing conditions for the nanofibers. Generally, for the thin films, it has been reported the thermal annealing is done around 170 degrees Celsius to allow this macrophase separation. But when we did it for the nanofibers, because nanofibers are even thinner and having more surface area than the films, so that condition did not remain valid. So we optimized. So thermal annealing was done at finally 135 degrees Celsius to achieve the glass transition temperature beyond which you can do the microphase separation. And then we did the UV exposure. So UV exposure was done to degrade one of the phase. So initially, just understand, initially you are having a combined phase of PS and PMMA. Now you do the annealing. So PS and PMMA are now separated, microphase separation. After that, you have did the exposure. So PMMA, which is now separated, that is now degraded. And then you did the acid etching, typical acetic acid wash. So after this acetic acid washing, or which is called etching, this degraded PMMA is now phased out, okay, at least partially. And because of that, you are having now these kind of special porosity in your nanofibers, which you can see in this figure. So these are the FEFM images of edge spun fibers. You can see this from different molecular weights. And then you can see after etching and UV exposure, you can see the different kinds of porosity. Okay, so this nice porosity is created by the mesophase by the mesophase separation in these block copolymer nanofibers. In fact, we can also vary we can control this porosity. So the next question will be, can we control the porosity? Yes, we can control the porosity. So for doing that, one of the ways you can vary the solvent in which you are doing the electrospinning. So we did this electrospinning. We prepared this polystyrene polymethyl methacrylate solution in different solvent ratios of DMF and THF. Like 1:0 means only DMF, 0:1 only THF, and these are the three different other ratios. And we can see that, based on the different ratios, you can control the different kinds of porosity in these nanofibers. Okay. Also, the fiber diameter is little bit changed when we go for different solvent ratio. Why? Because every solvent is having a different volatility. Okay, so their relative vapor pressure is also different. So in a given condition, one solvent will be evaporated faster than the another one, and that creates a different kinds of porosity. Okay, so that's what the reason for controlling the porosity using the different solvent. And what we have shown here, not in this particular figure, but I have mentioned that there is a 6 to 8 time enhancement in the surface area after this acid etching, after getting this extra porosity in these nanofibers. Yeah, I think I have mentioned here. So when we did the porosity characteristics measurement, then we have seen that there are different kinds of isotherms. I'm not really going into the detail in the interest of time, but what we can see, there's isotherms for edge spun nanofibers, means without any annealing, without acid etching. They were like type 2A isotherm, which is a non-porous material. Okay, because by doing this BET surface area measurement, you can get a fair idea about what kind of pores you have generated. When you do the spinning with the THF solvent only, you get type 2B isotherm that is associated with the slit-shaped pores. And when you do the annealing, acid etching, then you do the nanofibers which are so-called porous. And when we treat them and when we check their isotherm, they are now type 4 isotherms, which is having the H1 hysteresis loop. That is nothing but characteristics of the mesoporous material. So basically what I want to say is that by changing by allowing the microphase separation in these nanofibers, you are generating this porosity, mesoporosity, that has been reflected in the BET surface area measurements, and that also changes the pore volume, pore size, and all that. And we did a lot of further characterization using small angle X-ray scattering, because this small angle X-ray scattering gives you, because BET sometimes when you work with the micropores and mesoporous materials, BET does not give you a correct picture. The reason is when you use the BET, you use a particular gas, for example, nitrogen generally used. So nitrogen molecule, if your pores are small enough, there might be a chance that these nitrogen molecules, they are not adsorbed on the surface properly. Okay, so that the data which you are getting from the BET may not be accurate. So for that, we further did the small angle X-ray scattering, and we did a lot of geometrical structural determination using the small scattering analysis. And what we have seen that this linear analysis for the scattering curve, that gives the radius of gyration, and linear regression was done in the gyre region, this particular region. This you can see the linear regression, and that gives you the idea about the radius of gyration. Finally, we have also done the pore diameter from this radius of gyration and column height used from this. And then basically we have matched the data with the small angle scattering and BET as in this table, if you see. And what we can see that there is a, of course, there is a same trend in terms of BET and small angle X-ray data. And like, for example, edge spun nanofibers are surface fractal, and while the mesoporous nanofibers are mass fractal. And as I mentioned, if you see that response time and analyte concentration, that changes the, that is dependent on the fractal dimension. So that's why we have done this fractal dimension analysis. And what we have seen that by generating this porosity, not only we are creating the high surface area and extra porosity, we are also changing the fractal dimension, which will ultimately affect your response time. So we can see that there is a drastic increase in the so edge spun nanofibers. Let's say, for example, in this case, 18.18 meters square per gram, while they were treated, annealed, and porosity was generated. There is a 136 meters square per gram. So there is around 6 to 8 time increase in the surface area of these PS block PMMA nanofibers after acid etching. Okay. We can see that we have generated higher surface area structures, which are having different kinds of pore volume, pore density, as well as fractal dimension. And now we have used these nanofibers for the sensing. And for that, what we have done, as shown in this schematic, so we have taken these nanofibers, grounded to a fine powder, dispersed into the water by ultrasonation with some concentration 1 milligram per ml. And then that dispersion was drop casted into this glassy carbon electrode surface, like shown here. And then basically, of course, the glassy carbon electrode was polished before drop casting. And then basically we have modified this electrode. So ANF, we call it ANF. If you see here, PNF and ANF. ANF means edge spun nanofiber without porosity. PNF means porous nanofibers. So these electrodes were then modified for the comparison. We have taken the porous nanofibers as well as non-porous nanofibers. And finally, we have checked the cyclic voltammetry. And what we see, if you see these figures, first figure, let's say cyclic voltammetry, there are 4 different curves: bare DC, and then porous, and then basically it is compared with the different kinds of concentration. So what we see that this current response, it decreases significantly when the nanofibers are loaded from the bare electrode surface to 5 micron to 10 microliter. But the change in the current is negligible upon further loading. Okay, so 10 to 20 is not very much change. So what we hypothesize from here that current decreases mainly due to the nanofibers, which are in immediate contact with the electrode surface. Then basically what we then we did the biofunctionalization by this biotinization using the very famous EDC NHS chemistry, and that is done. And after that, these non-specific sites of biotinized electrodes were blocked using the BSA. And then we did this electrochemical testing in the presence of stabilizing and redox couple of this ferrocyanide. Okay. So these all measurements were done in the 3 electrode cell, where AgCl was used as a reference electrode, platinum via counter electrode, and these glassy carbon electrode, which is functionalized with used nanofibers, that was used as a working electrode. Okay. And if you see now the results, the DPV, digital pulse voltammetry, and so that was used to characterize the functional groups on the surface. So that is shown here, basically in the figure BCD. So what we see here is that in the figure C, what we see that when we use the porous nanofibers by varying the applied voltage from 0 to 1, and when we change the pH, okay, so the peak current is significantly high at the lower pH value as compared to the higher pH. In contrast, there was no significant change in the peak current when the FCDM was used as a redox probe. Okay, and then basically we see further here also. So we can see that the dependence of this oxidation current of the charge redox on the pH, like this here, that shows basically that there are certain functional groups on your surface. Okay, and at lower pH, nanofiber surface remains uncharged, and that allows the unrestricted movement of these negatively charged ferrocyanide molecules. But at the high pH value, there is a deprotonation, and because of the carboxyl groups present on your nanofibers. So this range of the pH, which causes this reduction in the oxidation current, that suggests the presence of carboxyl CWH group on the fiber surface. That has also been confirmed further with the FTIR, of course. Okay, and the greater decrease in this current at higher pH in case of porous nanofibers as compared to the edges per nanofibers, that may be due to the presence of more functional groups on the surface because of the higher surface area. So if you compare this B and A, you can see there is a much more change in the current or greater degrees in the current in case of porous nanofibers as compared to the edges per nanofibers. What we also did, basically the CV to characterize this working electrode, and then we have performance, and then we evaluated the performance using the redox couple, using the scan rate of 50 millivolt per second. And again, we can see that decrease in the current is more at each stage of the modification of this electrode. So, well, without going further into this, let me just see this DPB and the CV curves. So here you can see basically that for ANF, which is edges per nanofibers, IP value decreases from, let's say, 30 microampere to its 27% in the presence of 1 microgram per ml of stratobidin. For example, which is basically 14% decrease in terms of porous nanofibers. So that shows the effect of these porosity on these CV curves. And what we have also varied this stratobidin solution concentration from 1 microgram to 1 femtogram per ml, and that is shown here that how the current response is changing while you change the concentration of these analyte. So we did the response is recorded by varying this concentration from 1 microgram to 1 femtogram, and we can see the increase in the stratobidin concentration, redox current from the probe decreases. Okay, and this can be attributed to the formation of the insulating layer of biotin and stratobidin complex at the electrolyte interface, which basically hinders the charge transfer. Okay, so this further we have done the interference study, because in this effect of interference is important for the immunosensors, and for that we have done this interference study in the presence of non-specific proteins like human cerebral albumin (HSA), which is commonly found in the human blood, and myoglobin found in the muscle tissue. And what we have done, 10 nanogram per ml of interference and myoglobin was used in the presence of a target analyte, which is stratobidin, which is again also 10 nanogram per ml. And then we mixture of all the 3 species of the different concentration we have used, and later we did the DPB in the 0 to 1 volt versus the reference electrode of AgCl, the redox couple ferrocyanide with the target protein and the interference. And what we can see that variation in the peak current is about 2% to 3% in the presence of HSA, myoglobin, and HSA plus myoglobin. Okay, that shows basically the very good selectivity of this particular sensing platform. So then also from these curves, we have calculated the limit of detection, which is measured as 0.2 femtogram per ml from this slope of this linear curve. And finally, what we can summarize from this work is that, of course, we have shown that how we can control the porosity in these nanofibers. We can increase the surface area, and then we can do the biofunctionalization very easily, which is because of the presence of COOH groups. And because of this extra porosity and extra surface area, we see there is a 6 times increase in the sensitivity, and limit of detection which is achieved is around 0.2 femtogram per ml with the negligible interference. So basically this work demonstrates the effect of porosity and the surface area on the sensing properties, and basically it's a general approach for the improvement of the sensitivity and detection limit of the nanofibers based immunosensors. And that eventually can lead to the development of better point of care diagnostic devices. Next, let me move to the, so because if you see in the beginning, when we compared the, when we have shown the effect of morphology to nanofibers to nanoparticles, so let me touch upon the another aspect of the nanomaterials, which is nanofilm, slightly different from the nanofibers. But here we have used a different polymer system, polyethylene oxide and block PMMA. Okay, PEO, block PMMA, or derived ordered mesoporous thin film that has been used as an electrochemical sensor. So for that, basically, this block copolymer is not available commercially. We have synthesized, I mean, we have synthesized means one of our collaborator from Polymer Source, Canada. They have synthesized it diblock copolymer, PEO with the PMMA. Okay, by atom transfer radical polymerization. I'm not going into that because that's something not of not the work done by us. So with this particular block copolymer, we have synthesized, and then basically we have prepared the solution of it, and then do the spin coating to prepare the thin films on the silicon wafer. And after that thin film, basically what we have done, these thin films on a substrate that was annealed. If you remember annealing, right? Earlier we have done the thermal annealing at 135 degrees Celsius. Here in case of thin film, we have done the direct immersion annealing. That is even much more simpler than the thermal annealing. Okay, it is done at room temperature. So what we have done here, we have immersed these films which were coated on the silicon wafer of this polymer PEO block PMMA and put them into the toluene versus N-heptane mixture of 0.57, 0.4 for 20 minutes. That is called direct immersion annealing. What is the principle? That this toluene and N-heptane, this mixture is basically PEO is soluble and PMO is almost soluble in the toluene. Okay, and in the N-heptane, PEO and PMMA both are insoluble. So basically, it's a combination of solvent and non-solvent in a given for a particular block copolymer. And because of that, there is a difference in the solubility parameter. There is a microphase separation between the two blocks. So that is called direct immersion annealing. Earlier, we have achieved the microphase separation by thermal treatment. Here, by immersing the blocks into a solvent and non-solvent combination. Okay, so this phase separation that allows us to form the vertically aligned nano cylinders with the ordered mesoporous structure. And finally, we have washed the structure with the methanol and water mixture so that the water soluble PO phase is dissolved, and that gives you the highly uniform monodisperse and tightly packed pores of PMMA matrix. Okay, so that is what is shown here in this AFN figure. So first ABC are the edge casted film, and after direct immersion annealing and the washing, you can see DEF. And finally in the figure F, you can see how the nice ordered dense structure has been prepared in this thin film. And this thin film is now used as for the sensing. And this is just a TEM figure to show how the porosity is generated. Now remember, this film is on the silicon wafer. So if you want to use it for the sensing as a freestanding sensing platform, we have to detach this film from the silicon, and where basically we use the technique waste transfer, which is basically from one side you put a cut and put it into a solution so that it comes out, float on the solution, and then you put it on your electrode on which you want to do the electrochemical sensing or electrochemical measurements. So why this is important, and that's how I want to introduce here recessed nanodisk array electrode for the sensing, okay, as a platform. So if you see the electrochemical system, the size of the working electrode, that plays a very crucial role in the analytical performance of the device. Okay, so the ultra small electrodes, which we generally call micro electrodes or ultra micro electrodes, they also, because of this, they have the very distinct advantage when compared to the conventional electrodes. Okay, so this ultra macro electrode means the electrode whose size is of the order of diffusion layer. And in such a system, there is a dominance of radial diffusion that leads to the enhanced mass transfer to the electrode surface. And that's how you get the high Faradic to charging current ratio. So to take this approach further, we have reduced the size of the individual electrode in the nanometer range by developing this RNE, recessed nanodisk electrode. Okay, so this basically further scaled down, and this basically makes it possible to study even the faster chemical and electrochemical reaction. And here the reduction in the size of the initial electrode makes it possible basically to accommodate the massive number of electrodes with the same footprint of the electrode. So that is basically very useful for the sensing application. So for the electrochemical studies, this system is basically transferred onto the glassy carbon electrode by the base transfer technique, as I just mentioned. And then basically this block copolymer porous thin film like this that has been transferred onto the glassy. So each of these nanopores is working as an electrode. That is called recessed nanodisk array electrode. So your electrode size is nothing but reduced to a few tens of nanometers. So this particular approach is something very unique, in which we have used the block copolymer derived ordered mesoporous nanostructure as the recessed nanodisk array RNE system. Okay, so after that, once it is transferred on the glassy carbon electrode, this is exposed to the UV radiation, okay, to create these carboxyl groups by the hydrolysis of PMMA, followed by functionalization like biotinylation. Then we did the cyclic voltammetry, and in the presence of model analyte, again same streptobidine is used as a model analyte. So basically, this streptobidine is near neutral under the physiological condition, and that's why it avoids any non-specific interaction, and it is having a very high biotin binding affinity, and that's why it is used as a model analyte. And this is something which is first study under review currently, in which we have used the block copolymer based RNE to study the sensing properties. So let me go into the CV results as I have shown here. So CV was carried out in the 2 millimolar solution in the PBS, and first we have done the CV with the bare glassy carbon electrode by varying the scan rate from 5 millivolt to 1 millivolt per 1 volt per second. And we can see that there is no variation in the peak position. Okay, and then later we see with this kind of electrode, RNE electrode, that anodic peak current varies linearly as a square root of the scan root. That basically shows that whole process is diffusion controlled. Okay, then basically what we have done, we have used this Randall-Sedgwick equation further, and that is basically used to determine the actual surface area versus the electrochemically active area. From that, we can also calculate the diffusion coefficient. So all these parameters have been studied so for the different phases of this PEO removal of the from the PMMA phase. Then we also varied after that. Let me show the next slide. So again, here, if you see, this is the cyclic voltammetry at the different stages of modification of the glassy carbon electrode that I was mentioning here. And yeah, so this is something I wanted to mention here, that at different concentration of the streptobidine, for this modified electrode, the CV curve is shown here, and respect to the calibration curve is also shown here. And what we can also visualize, what we can also figure it out here is that this, when CV is done at different concentration to calculate. So sensitivity is of course calculated using the slope of this calibration curve, and that is coming out around 58 nanoampere per gram per ml. And also we have done the interference studies again in the presence of human serum albumin, HSA, and myoglobin, like we have done last time. Okay, and so we 10 nanogram per ml of HSA was detected in the presence of this. Sorry, 10 nanogram ml of streptovidin analyte is detected in the presence of 10 nanogram per ml of HAS plus 10 nanogram of myoglobin. And in all these three cases, we can see that there is significant decrease in the redox current in the presence of this streptovidin. And when we compare it to the blank, we see that there is no significant change in the current with respect to streptovidin plus HSA plus myoglobin. So that again indicates the excellent selectivity of this PEO versus block PMMA based RNA immunosensors with the limit of detection around 0.15 femtogram per ml. So here, to summarize this particular work, we have done the direct immersion annealing as a technique to allow the microphase separation in the nanofibers so that we can generate the porosity. Wedge transfer technique is used so that we can transfer this porous film onto the desired electrode, like glassy carbon electrode. And then, as usual, we have done the biofunctionalization, which is done using the, sorry. Yeah, so we have done the facile biofunctionalization as we have explained in the last problem also. And then we have determined the linear range from 1 femtogram per ml to 10 microgram per ml, which shows the diffusion controlled reaction. And with that, we have also determined the ultra low limit of detection with negligible interference or excellent stability of the platform. Now, next, let me move to the electrospin carbon nanofibers. So far we have used the polymer or block copolymer nanofiber system, where the focus was on to generate the porosity in the films or the nanofibers. And because of this extra porosity or use of these pores as a single electrode in RNA, we have shown that how we can achieve the very, very high level of sensitivity. Now let me move to the carbon nanofibers. And when I talk about the carbon nanofibers, let me first touch upon why we are interested in carbon at all. So carbon is, if you see, as a material, okay, there are various advantages of the carbon. I'm not going into the detail because of interest of time. And also with respect to sensing application, especially carbon is important because it shows the wide electrochemical stability. Okay, other than the various other regions as listed here. So other than the cost, chemical inertness, various form, polymerization, and all that, what is important for the sensing is carbon material shows the high electrochemical, wide electrochemical stability window. And that is what is important for us. So if you see carbon, how to make these carbon structures, basically what you do, carbon MEMS. But you generally take the polymers, do whatever you want to do with the polymers, microfabrication, nanofabrication, what we have seen, and then convert them into carbon by the process called pyrolysis. Okay, so polymers are patterned or whatever micro nanofabrication, then pyrolyzed in the inert environment to yield the carbon structures. So this pyrolysis is done generally at very high temperature, something around 900 degrees Celsius minimum. Okay, and while doing that, we see that these polymers are converted into the carbon structure without losing its integrity, and it is done in the inert atmosphere. So this is shown here. You can make any kinds of carbon polymer structures, nanofibers or any other structure, and then you do the pyrolysis from this to this, and you can make them into the carbon from this to this. And for that, we have shown there are different kinds of polymers which can be converted into the carbon nanofibers depending on different yield of the polymer. So in our group, we have worked with the different kinds of polymers like PEN, PS, PMMA, SU8 photoresist, gels, block copolymers also. So I will touch upon an example of one particular block of polymer, PEN-PMMA, because PEN generally gives you the high carbon yield. And that is the reason we have chosen this particular block of polymer to make the nanoporous carbon fibers. And these are used for the hydrogen detection. This work has been done in collaboration with Dr. Mahesh at IIT Jodhpur. So what we did here, we have taken the PEN, which is a homopolymer, 8% of it with the molecular weight of 150 K, and mixed it with the PEN block PMMA block copolymer. And the reason of mixing the homopolymer is because if you take only the block copolymer, the molecular weight is not sufficient, 1.1 and 11 K. And as I mentioned in the beginning, if you remember, the molecular weight plays an important role in the electrospinability. So if the molecular weight is not very high, you cannot really electrospin the only block copolymer of PEN-PEN. And that is the reason we have added the homopolymer also into it. This particular combination has been optimized. Okay, so it takes a long time. But finally, we have done the electrospinning of 8% of PEN in DMS and 12% of PEN PMMA block copolymer in DMS in 1:1 ratio. Then did the electrospinning. And as I mentioned, we want to achieve the nanoporous carbon nanofibers. So we did the annealing, and this time annealing condition is different at 180 degrees Celsius in vacuum. Again, all these are optimized parameters after a lot of work in the lab, which takes almost 1.5 years. And then finally, we go for the stabilization step and then pyrolysis at 900 degrees Celsius to finally get the carbon nanofibers, which is around 35% yield. Okay, so this is the process to generate the PEN PMMA derived nanoporous carbon nanofibers. So first you create the porosity in these nanofibers, adjustment nanofibers by annealing, and then you do the carbonization at the inert atmosphere at 900 degrees Celsius. This is further characterized that what kind of carbon material we are getting, because that is important to know when you are really want to explain your sensing properties also. So we have shown that Raman spectra, XRD spectra, that generally shows that there is an interlayer spacing of 3.42 angstrom, and mainly you can see this D band, which is a characteristic amorphous carbon with some G band and G dash band also. So it's amorphous carbon with nanographitic structure, because PEN is conducting enough. So PEN gives you the graphitic structure, while PMMA derived carbon gives you the amorphous carbon. So it's basically amorphous carbon with nanographitic structure. It's a combination of both the things. And now these PEN PMMA derived nanoporous carbon, they have been used for the hydrogen detection by using the zinc oxide nanostructures. So what we have done, zinc oxide nanostructures, they were grown on the p-doped silicon substrate by RF magnetron sputtering system at IIT Jodhpur. And then what is done basically to develop the system, if you see this particular system here, there is a carbon nanofibers, which are basically carbon nanofibers. They are mixed in the IPA solution, and then that solution was sonicated to prepare the homogeneous solution of the dispersed nanofibers, and then different concentration of these carbon nanofibers that was loaded on this patterned zinc oxide nanostructure by drop casting. Okay, so different concentration from 0.5, 0.1 to 0.58% has been used on this gold-coated ID pattern of zinc oxide nanostructures. So what we see that basically when we change the concentration of these carbon nanofibers from 0.1 to 0.5, there is a network-like structure which is formed between the two electrodes, and that has been further utilized to sense the hydrogen. Okay, let me come back to the slide a little later. So what we can, what I can show here in this plot is, Right. So if you see this particular plot A and plot B, we are seeing only zinc oxide. So the results are compared with the only zinc oxide and then varying concentration of 0.1 to 0.5 of carbon nanofibers in zinc oxide. Okay, and what we can see that current decreases till 0.28% of CNF loading, and that basically confirms the formation of PMHU junction. And high current for carbon nanofiber silicon as compared to the bare silicon, that also confirm the high conductivity of the CNF. So if you see this particular only for silicon, bare silicon, and this is for the red one is for the carbon nanofibers on silicon. That shows that current response shows the high conductivity of these carbon nanofibers. And then basically what we are seeing here is that at very further loading of CNF beyond 0.28%, current increases due to the network formation of between the IDs. Okay. Then we also calculated the relative response. Okay, so relative response plot is shown in this figure C, and then, I mean, overall, if you see at what we can see that current conduction is basically depending on the loading amount of CNF over the zinc oxide nanostructures. Okay. And this is not linear. Basically, it first increases up to 0.8% at 3-volt forward bias, and then it starts decreasing. So we have optimized the concentration at 0.28% of CNF versus CNF and zinc oxide. And relative response is also calculated. And if you see the relative response is higher, which is 73.5, that is also for this pink light 0.28% of CNF. So this 0.28% of CNF and zinc oxide, that has been optimized in terms of relative response. Finally, we have done this dynamic sensing response of CNF and zinc oxide nanostructure and CNF zinc oxide nanostructure with a varying concentration of CNF again for 100 ppm at 150 degrees Celsius. Okay, and here we can see the relative response of CNF and zinc oxide nanostructures was around 3% and 45%. Okay, so this is around 3% CNF, and this is around 45% for 0.5. And this peak relative response is increasing when the concentration rises to 0.28% again. If you see here, this is 0.28%, and further, so 73.4% is the exact one. And when you further increase the loading to 3.3 to 0.4 to 0.5, it further reduces to 45% at 0.5. So in overall, we can see maximum relative response is achieved at 0.28% of CNF GNO nanostructures as compared to the pure CNF or pure zinc oxide nanostructure. Then with that particular 0.28% CNF zinc oxide at 150 degrees Celsius, we have done the response and recovery time analysis as shown here. So response time is known as the time required to reach 90% of the sensor response. Okay, that is called the response time. And here, if you see from this plot, the response and recovery time for this 0.28% carbon nanofiber zinc oxide nanostructures, they are calculated as around 28 seconds and recovery time around 340 seconds, which is quite good. Okay. So and this sensor based on this carbon nanofiber 0.28% of carbon nanofiber zinc oxide nanostructure is operated at 1.6 milliwatt, and that makes it satisfying the basically the predominant condition of low operating power, which is basically essential for any excellent gas sensor. We have also checked this relative response with respect to the different concentration from 1 to 100 ppm. And again, we can see that response enhances with the increasing concentration of hydrogen gas. 1 to 100 ppm we have checked. So behavior of all these three sensing response cycles that reveals the good repeatability under the same condition. So what we can summarize from all this is that these block copolymers, they are highly versatile and tunable. And PMMA nanofibers based super sensing we have shown. Further, PEO PMMA derived mesoporous thin films, they can be used as a RNA recessed nanodiscare electrode. And these last case pan PMMA derived nanoporous carbon nanofibers, when they are loaded on the zinc oxide nanostructures, they improve the sensing performance. Okay, and basically PEO PMMA mesoporous film can also be used as a template for the fabrication of molecular imprinting nanoelectrode array, which I am not covering into the today's talk. So let me just very quickly go through this last part of my talk. That is integration of electrospin nanofibers with the carbon MEMS to develop the ultra sensitive electrode. So what we have seen in the nanofibers, whether it's a block copolymer nanofibers or carbon nanofibers, now we want to integrate this with carbon MEMS system. And let's see some of the examples here. So integration means what? So electrospinning we have seen. Now, second thing is the lithography, which is used to create the 3D structures, like I have shown previously. Yes. So you have a thin film, which is of photosensitive material. Then you expose it to the UV, to which this light is sensitive, and this exposure is selectively. So selectively, this light is exposed so that the material which is exposed, that remains there, and an unexposed part is removed. That is how you develop the 3D structures. And this is called MEMS, carbon MEMS. And when you convert them into the carbon by pyrolysis, it is called carbon MEMS platform. So we integrated this carbon MEMS platform with the electrospinning. Okay, that is what the integration of nanofibers to carbon MEMS platform. So what we did, we have taken this 3D structures as made by the soft lithography, photolithography, and then did the electrospinning on top of that. Okay, so rather than using a planar substrate, you have now taken the 3D structures. On those 3D structures, you did the electrospinning. And what we get very nicely is this. So you can individually hang the nanofibers on the 3D structures. Okay, there are different kinds of, this is SU8 carbon nanofibers between the carbon 3D post. This is pen derived carbon nanofibers. So you can use different kinds of polymers, convert them finally into carbon. So what is happening here? This is your carbon 3D structures, and between the 3D carbon post, you are now hanging the single nanofibers. So basically the idea is to address the single nanowire. Earlier it was a nanofabric, right? It's a full fabric. Now here it is a single nanowire, and that is how the system is a bit different. So this is, there are various techniques people have used to make these hanging nanofibers after our demonstration in 2011. Then there was a paper in nanoletters in which they have used the near field electrospinning. There is a little variation, but it's again the same thing. Using the electrospinning and the CMEMS structure, you can precisely control the positioning of these nanofibers. And then we have used these for the ultra sensitive level 3 nanobiosensor platform. So here, as I mentioned, in this particular case, we have taken the copper, deposited the copper selectively, and between these copper electrodes, we have hanged the individual nanofibers, which is further functionalized by same EDC-NHS chemistry for myoglobin antibody immobilization on these targeted nanofibers. And then we have used these for the detection of myoglobin under the different conditions. This is just, I mean, before doing that, in fact, what we have also done, we have increased the conductivity of these individual nanofibers. So for that, we have added the multi-wall carbon nanotube in the polymer, then did the electrospinning. And then basically what you have is the electrospin nanofiber, which is carbon nanofiber, and which is having the multi-wall carbon nanotube inside into it. And that shows the enhanced conductivity while using it as a sensing platform. This is just a schematic to show that how it has been used by drop casting on the glassy carbon electrode, and then the antigen has been attached to that particular target sites. And as I mentioned, to maximize the conductivity of the nanofibers, 13 weight percent of the molecular multi-volt CNTs were added. This also is optimized. We have checked. I'm not going to the detail, but this also we have checked here. 8% to 9 to 11, 13. Every time we have seen the conductivity, we have measured the conductivity between the two nanowires, and we have found that 13 weight percent of CNT is giving you the highest conductivity, and that's why we have used it for the sensing platform in the suspended nanowire form. This is shown here. I'm not going to explain that. So basically, when you go from 8 to 13 weight percent, the conductive nature of nanofibers it increases. And I'm sorry, 11 weight percent has been found the maximum conductivity, not 13. We have varied from 8 to 13. 11 weight percent it has been found maximum conductivity. And that basically is explained here that the conductive paths, basically this 11 weight percent is kind of percolation threshold. After that, it starts decreasing further. So conductive paths in the percolating medium can be described with a network of resistors, and that is how it has been explained. So this system has been used further, and upon the binding of the myoglobin, surface stress on the nanofiber increases, and that basically increases the mobility of the charge carriers in the multi-volt CNTs. That is reason to increase the conductivity. And then basically using the chemiresistor technique, we have used it for the detection of myoglobin. These are some of the results. If you see how the conductivity is changing with respect to the different myo antigen concentration, 100 picogram per ml, and then it is basically at that conductance is minimized. And finally, we have also calculated the detection limit, which is 6 femtogram per ml, using the same standard sigmoidal binding curve analysis. And to ensure the stability, these functionalized nanofibers, they were stored under 4 degrees Celsius. And again, we have repeated the experiment, and we have checked the results. That was within the experimental error of the measurement. So basically, they are quite stable platform for the biosensing. This is just a comparison of this myoglobin biomarker for different kinds of transduction platform and detection range. And we can see that the chemiresistive transduction, which has been used in our case, that gives you a very high level of detection range, 20 to 70 femtogram per ml, with the limit of detection 6 piogram per ml. This has been further used for the creatine, creatine kinase MB. And again, you can see the different kinds of linearity and detection limit has been confirmed. So for this particular biomarker, it is found to be 20 femtogram per ml with a linearity range of 30 to 100 femtogram per ml. This is another biomarker, cardiac troponin 1, that has also been used. And here in this case, minimum detection limit was found to be 50 femtogram per ml with a linearity range of 50 to 100 femtogram per ml. This is reproducibility analysis. As I mentioned, we have a fixed analyte concentration of 100 picogram per ml. And with respect to different time period, 1, 2, 3, 4 months, we have checked that there is almost negligible change in the conductivity over the period of duration of the study. That shows basically the durability and the longevity of this proposed platform, which is kind of quite generic, that can be used for a number of biomarkers, as we have shown. So to summarize this, basically, we have developed level-free, ultra-sensitive and selective nanowire sensor platform for various cardiac biomarkers, as we have seen. Minimum limit of detection achieved is 6 femtogram per ml. And as I mentioned, it is quite generic in nature, okay, as we have shown already with the 3 different kinds of biomarkers, and it can be extended to any other immunoassay-based detection methodology and to the ultra-low concentration. These are some of the papers based on these. with this, I would like to summarize and acknowledge the various students and the funding agency which have supported us to carry out these works. Thank you.
Yeah, thank you very much, Chandrasekhar. It's excellent talk. Nipun, can you take questions from the chat box?
Yes, sir. Thank you, sir, for your such a nice and elaborative talk. The first question.
Yes, Nipun, are you there? Nipun, can you hear me?
No,
I think
I think it's not there.
Hello.
Yeah, Nipun.
Yes, sir. So actually, there is some problem with that host ID. I would like to ask question. Like Miss Sonam is asking during the fabrication of carbon nanotubes, how zigzag or armchair or chiral structures are found?
Sorry, Nipun, there's some echo. Can you repeat your question?
So excuse me, sir.
Can you hear me now, sir?
Yes.
Yes, sir. So she is asking during the fabrication of carbon nanotubes, how zigzag or armchair or chiral structures are formed? I mean, which type of structures are formed during the fabrication of carbon nanotubes? She is asking.
Okay, let me explain. So, see, I'm not sure that which part of the talk she is referring. So, we have used multi-volt CNTs in the last part of the work, where we have mixed these multi-volt CNTs in the polymer SU8 photoresist to make the composite nanofibers. And so, in none of the work, we have synthesized the CNTs. That is one clarity I would like to have. So in the last part, we have added the multi-volt CNTs directly into the electrodes, into the polymer nanofibers, and then converted into carbon nanofibers. And other places where I talk to the carbon nanofibers, so let me clarify, carbon nanofibers, they are different, entirely different with the carbon nanotubes. Okay, so carbon nanotubes, even in terms of dimension, so dimensions of carbon nanofiber is something around 100 to 200 nanometers. Okay, but carbon nanotubes, when we talk about the carbon nanotubes, they are basically 10 to 30, 20 to 30 nanometer. So they are entirely different. So at none in nowhere we have synthesized the CNT. So we have no comment on the configuration of the CNT in terms of zigzag or armchair. Okay. Only place where we have used the CNT is the last part where we have used the multi-volt CNTs as it is without synthesizing the other commercial ones.
Thank you, sir. Thank you for your response. We have another question from Mr. Pechai. He's asking to explain more about the direct immersion annealing of MTF films.
Yeah, so direct immersion annealing, it's basically one of the simplest technique for the annealing. So basically, see, annealing means you have to allow the microphase separation. Now, there are various types of annealing. One is called thermal annealing, solvent annealing, then this is direct immersion annealing. So it is done in, so basically the ultimate aim is you have to vary the condition for that polymers so that you can raise the you can achieve the glass transition temperature of the polymer where it starts melting. Okay, and that's how it allows the microphase separation. So when we do the thermal annealing, we heat the system and we achieve the glass transition temperature so that one particular block of the polymer is melted and taking it out, which allows the microphase separation. In the solvent vapor annealing, what we do, we expose the polymer or nanofibers or film to the solvent vapors. So when we increase when we and when we do the solvent vapor annealing, the temperature is normal, but because of the change in the vapor pressure, you are achieving the glass transition temperature there. Okay. Similarly, here, rather than exposing it to the solvent vapors, what we did, we have used the non-solvent. This is called non-solvent induced phase separation. if you read more about the phase separation, there are two different kinds of phase separation. One is called thermal induced phase separation, TIPS. Another is called non-solvent induced phase separation, NIPS. So this direct immersion handling is based on the non-solvent induced phase separation. So when you put your polymer solution, which is in a solvent, which is actually a non-solvent for a particular polymer system, then this non-solvent tries to push the solvent, and that creates the phase separation. So that is called non-solvent induced phase separation. So the trick here is you need to choose a particular solvent that acts as a solvent for one block of the polymer, but acts as a non-solvent for another block of the polymer. So that you can dissolve selectively one phase out of it. And this is done basically more scientifically. If you want to know about it, you have to choose the solubility parameter. Okay, so to define that which is a good solvent, which is a bad solvent, which is a non-solvent. So accordingly, you have to choose your solvent non-solvent system to allow this phase separation.
Thank you, sir. There is another question from Mr. Shahnawaz. He's asking how can we use carbon quantum dot space sensors in drug delivery and imaging?
Yeah, I mean, this is something which there are a lot of groups working in carbon quantum dots. We have not done in our group. But carbon quantum dots, again, as I mentioned, not just with respect to carbon quantum dots, but in general, the quantum dots, they of course carry a certain advantage over the other nanomaterials. But if you remember one of my slides in the beginning, I have mentioned where there is a change in the morphology and how it affects the response time. So there, if you see, there is very narrow gap in the response time with respect to the nano dots and the nano films and the nano fibers. So, of course, as I mentioned, there is a little advantage, but the kind of difficulty in synthesizing the nano dots is also to be taken care. So overall, when you want to develop a commercial system, commercial sensor, where the cost is also involved, not just science. So there you have to optimize with respect to your synthesis process, with respect to your end material. And that's where we have shown that nanofibers or the thin films, they carry a lot of advantage over the quantum dots.
Thank you, sir. We are done with questions from the audience, but I do have one personal basic question, sir. Like
Sure.
while electrospinning, do we have some kind of ideal needles which we are using for smooth electrospinning, or we just use whatever available commercially?
Yeah, I mean, it's a good question. So needle diameter also plays an important role in the final morphology. Okay, so if it is too wide, which is basically, by the way, needle diameter should not be confused with the needle gauge size, because that's opposite. Higher the gauge size, narrower is the diameter. Okay, so generally it comes in the 18 gauge, 20 gauge, 22 gauge, 24 gauge. So when I say 24 gauge needle diameter, its opening is minimum. When it is 18 gauge, the opening is wider. So it's the opposite. Well, so the question is, this needle diameter, yes, it indeed plays a very important role in the final morphology, because when it is a too wide, you are pushing a lot of polymer solution through it. Okay, so you may end up with a thicker fibers. If it is too thin, then it will be difficult to come out to take out the solution. So somewhere generally, of course, this is another parameter to optimize in the whole electrospinning process, but generally people use 20, 22, 23, 24 gauge. This is generally the opening diameter of the needles which are used.
Okay, thank you, sir. That's all. So
Yeah.
two more participants wants to ask questions if Mahesh, sir, because we are running short of time. So can we allow them?
Yeah, what question we can take?
Okay, okay.
Yeah, I can see the next speaker, Dr. Subbiah.
Dhananjay, I have. Yes.
Yes, sir. Yeah, is audible?
Yes, you are.
So thank you, sir. So when you discuss about electrospinning process, when you're going to make that nanofiber, you mentioned that you are giving it their repulsion, they are making a repulsive force each other. That's why that boblet converted to fiber. So my question is that, is there any voltage limit till that it will repulse, and after that it will be break, or nanofiber will not continuously flow? So is there like this?
Yes, so as I mentioned while explaining electrospinning, the voltage which we generally apply is something of the order of 10 to 20 kilovolt. Okay. Now, if you apply less than that, of course, the threshold voltage has to be achieved so that the electrostatic forces overcome the surface tension. That is one. Second, if you increase to even further higher than 20, yes, what will happen? There will be too much of repulsion. There will be too much of instability. So fibers will not be even reaching to the platform. Okay, they will be breaking. They will be so sometimes this particular trick, I would say, is used sometimes to create the small nanofibers. Of course, they are having different applications, but sometimes otherwise, if you see, there is a long continuous nanofibers production. But if you want to generate very small fibers, and if you want to break the fibers for a purpose, then you do this. Yes.
So, at the last application, as you discussed about the nanofiber on the CMEMS, CNF on CMEMS, you saw that that nanofiber convert to a single nanofiber and they make within the group. So how is that much accurate in the? So is it depend on the needles? Yeah.
Yes, no, I mean, so first is the deposition time. If you just allow it for a few seconds, and it will go only to the top of the post. There is a reason because the distance to the top as compared to the base is less. So first it will approach to the tip of the electrode. Second, to solve this inconsistency in this approach, because this deposition time may not be a very good controlling factor, Professor Mark Madhu's group has come up with the idea of near field electrospinning. So in the near field electrospinning, when the distance is very small, something less than 1 centimeter even, there you can precisely control deposition because there you have a much better automatic control in terms of fiber deposition. So that's a specific, or I would say, a very nice extension of general electrospinning that is termed as near field electrospinning, by which you can create the similar field. Field is similar, which is, let's say, 10 kV you are applying and distance is 10 centimeters. So field is 1 kV per centimeter. Now the same 1 kV per centimeter you can achieve when you have a distance of 1 centimeter and the voltage of 1 kV. But now you have a better precise control on the deposition by the automatic moving the stage. So that's how it is achieved. There is a nanolectors paper on this near electric field electrospinning.
The last question.
Better idea.
Sir, when you convert this single wide nanofiber, they are parallelly on the MEMS. So is there any chance that you can make vertically on the MEMS or between the MEMS?
No, you mean vertically deposition?
Yeah.
No, you have to change the system. I mean, right now, let's say it's a horizontal system. The fibers are coming from in the horizontal manner. But if you can of course change the whole system in a vertical manner, and then you can do the electrospinning, and then you can achieve that.
So is it possible?
Yes, it is possible.
Okay, thank you, Jay. Thank you.
Yeah, thank you very much, Professor Sharma, for excellent talk.
Thank you, Mahesh. Thanks for this opportunity. Thanks. And for taking your time. Yes, nice to see you, but sorry for taking your extra time.
Yeah, you have actually put a place for a carbon fiber electrode, which I wanted to talk, but maybe I will skip today.
Okay.
Okay. Sure.
Okay. Thank you. Thank you, everyone. Bye.
Thank you. Thank you.
Thank you, sir.
Yeah, Nipun, can we start?
Moving on, I would now like to welcome and introduce our next speaker to the audience, Dr. Subia Alvarappan, who is now Principal Scientist and Associate Professor at CSIR Central Electrochemical Research Institute under Academy of Scientific and Innovative Research, ACSIR India. So far, he has graduated over 30 researchers, including PhD, MSc, MTech, and BTech students towards their thesis. He also mentored over 6 postdoctoral researchers and research associates. Prior joining CSIR CECRI, he worked in the United States from 2006 to 2013 at various institutes, including University of Iowa, Florida International University, and University of South Florida. He graduated with a PhD from Macquarie University, Sydney, Australia, and was a recipient of IPRS fellowship from Australian government. He published over 88 research articles in the research area of electrochemical biosensors, photoelectrochemical sensors, biofuel cells, electrosynthesis of quantum dots and nanomaterials. He has one US patent to his credit. He is also the recipient of JSPS Invitational Fellowship during 2019, University of Tsukuba for 1 year, and selected as a fellow for Royal Society of Chemistry during 2020. He is also the member of INEAS, ACS, MRSI, and Society for Advancements of Electrochemical Science and Technology. So with this, I would like to request Dr. Subbiya Alvarappan to please deliver today's talk. Thank you, sir.
Yeah. Thank you very much for the introduction. And I take this opportunity to thank Dr. Mahesh and his team for organizing this, excellent workshop, especially, dedicated to sensors. And today I'm going to, give you an overall view of what we are doing at our research lab, and also trying to introduce some of the novel concepts that are actually emerging in the field of, biosensors, especially in nano biosensors. Okay, so I'm just going to share my slides here. So please make sure you could able to see that.
Yeah, slides.
So can you see my slides? Yeah. All right.
Yeah.
Thank you.
Please
Yeah.
do.
So basically, as the introducer said, like I'm from CSIR Sikri, and it is one of the 38 research labs under the battalion of CSIR. And what we do here is everything on electrochemistry. Okay, so we have 7 different research divisions, and I belong to a division called Electronics and Electrocatalysis division. It is one of the division that actually do basic research in electrochemistry. So the key strengths of our division is we work on 3 broad domains, namely biosensors and bioimaging. So here we specifically concentrate more on biosensors, and also we have also done some work on bioimaging, but the main emphasis is on biosensors. And another strong strength of our division is on electrocatalysis, and then on bioelectrochemical systems. So in the domain of biosensors, especially, like I work on enzymatic and enzyme-free biosensors, immunosensors, and also on aptasensors. So there are also my colleagues, some of my colleagues also work on molecularly imprinted polymer-based sensors or electrodes for biosensing applications, with special emphasis to environmental pollutants, for the detection of environmental pollutants. So I do also work on photoelectrochemical sensors, which is considered as a hybrid sensors. You use both the optical as well as the electrochemical strategy to detect some of the very important biomolecules. Okay, so as far as electrocatalysis is concerned, yeah, we work on all the bifunctional, trifunctional, and monofunctional nanomaterials for important fuel cell applications. Energy storage applications, such as initiating a very good oxygen evolution reaction, or oxygen reduction reaction, or hydrogen evolution reaction. And there are also a few researchers who also work on CO2 reduction and nitrogen reduction reaction for the manufacture of ammonia. Okay,
Yeah,
so regarding the bio.
Excuse me, Dr. Subbiya, can you do the presentation mode? Your slides
are not visible. Okay.
No, it's visible, this one, but yes,
okay.
Now yeah, perfect. Yeah, thank you.
All right. Yeah. So on a bioelectrochemical system, so some of the researchers also work on understanding the electron transfer reaction in biological molecules. Even I have done some of the work on understanding how to achieve the direct electron transfer on a nanomaterial when you bring in a big protein or a peptide or directly onto a electrode surface. So and also by doing so, we also investigate the other thermodynamic and kinetic informations of this biological electron transfer reaction. And one other important research work that we also work on, membrane and membraneless microbial fuel cells. So these are emerging as a alternate conventional system for energy applications. So these are the key strengths of my division, and also my key objective is on biosensors. Okay, so the objective of my group is to develop a miniaturized, selective, sensitive, rapid, and affordable biosensors, especially operating on electrochemical mode. Sometimes what we do is, if the material is optically active, it has a very good fluorescent properties, we also try to explore them if it is going to detect less amount of, that is more sensitive, it is going to be operate in a more sensitive manner in a optical mode as well. So though we work on electrochemical biosensors, we also try to exploit some of the optical properties of these nanomaterials and try to use them as optical sensors as well. So some of the key target analytes that we have worked already are include high density lipoproteins and low density lipoproteins, triglycerides, cholesterol, urea, biomarkers such as human chorionic gonadotrophin or immunoglobulin G, cancer antigen 125, and also we have also detected some of the important DNA mutations that gives you an early warning or early indication about the development of some important syndromes such as Down syndrome or Parkinson's, Alzheimer's, Alport disease. Okay, so some of the sensors have also been used to detect destructive heavy metals like cadmium and mercury in environmental in lake water also, and also in other tap waters. So we also demonstrated some of the sensors for the detection of bacteriophages, pathogens, and rotavirus. Okay, so this is the overall objective of my research group, and some of the target analytes that we have detected so far has been actually listed in this particular slide. But however, today I am going to categorize my research talk. Whatever that I am going to present in the allocated time into three major categories. One, I am going to explain something about microelectrodes. Okay, so microelectrodes are otherwise known as ultra small electrodes. Okay, so that we actually use that for real-time applications. The second one is a little bit on carbon-based nanomaterials. So mostly I also work on carbon-based nanomaterials. Okay, so on carbon nanotubes, graphene, and graphitic carbon nitride. So these are the three essential carbon-based materials that I actually work. I employ them as a biosensing platform for the detection of biomolecules. Okay, so I'm going to touch a little bit on all these three important carbon-based materials, and also a little bit on two-dimensional nanomaterials. So how to use other than carbon-based nanomaterials? What are the other materials that you can actually employ for biosensing application? And then these transition dimetal chalcogenides. Okay, so how to actually use them as in the bulk form and transfer them into its constituent quantum dot. So based on this, so I'm going to split up my talk into these under these three categories. Okay, so sensors are nothing but this is a word that is commonly, we all know about sensors. Okay, so it is existing in the literature for over 150 years, and this is the word actually taken or borrowed from the sense organs. So what is a sensor? It is going to sense something. Okay, so that's what we call it as a sensor. So this is anyway the broad terminology that is actually borrowed from the in the medical literature called like sense organs. Okay, so a sensor, in a chemical terminology, we can define a sensor as a device that can quantitatively or semi-quantitatively converts some useful information. Okay, so useful information regarding the presence of a chemical species into an analytically useful signal. Okay, so this is the broadest definition that actually IUPAC recommends to use, for any reference towards a sensor. So a subset of a sensor is otherwise known as a biosensor, okay, which has a receptor made out of a biomolecule. So biosensor is nothing but a subset of sensor that is going to have a receptor which is nothing but a biomolecule. Okay, so this receptor can be either made out of an organic or an inorganic material that has a specific interaction with one or more analytes. Okay, so in some cases biosensors, the same sensor can also able to detect more than one analyte. Okay, so that we call it as a multiple sensing. Okay, so or like say for example, if you have 3 glucose, cholesterol, and you have like something called dopamine. Okay, so if a sensor could able to detect only one, we can claim that as a very specific for that particular analyte. But sometimes like graphene, like I'm going to show some of the examples here. So if you have a graphene and you have one or more analytes, so it has a property to detect all these 3 together. So we call it as a specific and sensitive sensor that could able to discriminate, okay, all the 3 analytes individually. Okay, so a biosensor can detect one or more analytes at any given time. Again, the other important constituent of a biosensor is a transducer, and this transducer is nothing but an electrode platform. Okay, the nanomaterial that we are going to use. So this actually is an important component that is going to convert the chemical information, okay, that actually you gather it out upon on a receptor and you translate that to a measurable analytical signal. Okay, so this is how, like, biosensor emerged from sensor, and these are the important components of a biosensors. Okay, so biosensors can be classified based on many different strategies. Okay, so one is based on the biocomponent, the other one is based on transducer. Okay, so based on the biocomponent, so biosensors fall under different category, namely like an immunosensor, which actually works on the principle of a definite interaction between an antigen and an antibody, and an enzymatic sensors, which based on the enzymes catalytic activity. And like you can also have a biosensor. You can modify the transducer, I mean the receptor surface, by means of a DNA or a phase, and you call it as a DNA sensor. Okay, so these are the categories with which you can classify the biosensors based on the biocomponent. Similarly, based on the transducer, that is the operating principle, biosensors can also be classified. Say for example, if it works on the principle of optics, I mean like based on either the change in fluorescence or a change in absorbance, so you call it as a optical biosensors. And in optical biosensors, we have different categories, namely surface plasmon resonance based sensors and fiber optic biosensors. Similarly, if it works on the electrochemical principle, then we call it as a electrochemical biosensors. And these electrochemical biosensors, they can also be categorized under different names, like an amperometric sensors. Okay, so and also potentiometric sensors, and also as a conductometric sensors. Okay, so other than these 2, there is also there is also a category where you can actually classify the biosensor based on the mass. Okay, based on the antigen and antibody interaction, the mass actually varies. So such kind of sensors are called piezoelectric sensors. Okay, so there is no definite rule that you need to actually follow up to classify them. Say for example, if you use an electrochemical sensor, but that also works on the principle of specific interaction of an antigen and antibody, you can also call that as an antibody based biosensor. Also, you can call them as a electrochemical biosensor. Okay, but it depends on the convention with which the researcher use. But these are the broad classifications, okay, of biosensors, that is commonly in use. So when we say biosensors, okay, so there are certain categories, I mean, there are certain important parameters that one has to look before, translating these, biosensors to industrial applications or real-time application. The first one is the linear range. Say, for example, like you make a biosensor and you actually do one or two analysis. Like, say, for example, like from 1 millimolar concentration, it could able to detect 5 nanomolar concentration, it could able to detect, and 25 nanomolar concentration, it could able to detect. Okay, then you can claim that this is a very excellent biosensor. No, it has to have at least 1,000 times. I mean, like the concentration that you use, okay, has to be at least like 1,000 times on the left and onto the right. Okay, so on either side, so there should be it should actually, the biosensor should be able to actually give very decent results within this broad linear range. So that what we call it as a high linear range. Okay, if it is not going to detect on either side, then obviously the sensor that you make is of no use. And again, it has to be at least selective. Okay, so if you are going to detect only one, it's okay. But if you are going to detect more than one analyte in a very challenging environment, it has to actually able to detect at least 2 in a given 3 analytes. Okay, if there are 5 analytes, it could at least able to distinguish 3 of them. Okay, so this we call it as a selective biosensor. And also, these sensors has to be stable for over a period of time. Okay, at least these days 2 months it should exist. The response that you measure on the very first day, maybe 10% to 12% decay in current or increase in current is acceptable. Okay, but not more than that. So it should be stable, and also it should actually provide a very rapid response. Okay, say for example, if a molecule is undergoing a redox reaction, say for example an oxidation reaction at 0.3 volts. Okay, the moment you apply that 0.3 volts onto the electrode surface, you should be able to give the response immediately. Okay, so that we call it as a rapid response. So these are some of the critical aspects of the biosensors that one has to consider before translating the laboratory research to a industrial based one. But taking into consideration, maybe like not all the sensors can provide all the 4 at a given time. Okay, so there should be a little bit of a trade-off, at least like a 3, you have to have 3 of them like together when it goes as a package, if not 4. Okay, so these are some of the common essential things or characteristics that one has to know when you actually use these biosensors. I mean, translate these sensors. So where do we use biosensors? From almost today, these days, we use biosensors almost in all the places, from, say, for example, from Homeland Security to sports regulatory boards and to other agencies that can actually detect drugs of abuse. Okay, we all know, like, the freshness of a fruit or a vegetable or any plants can also be detected with the help of biosensors. Okay, so the presence of food, I mean food spoilage, the presence of bacteria, the presence of virus, okay, so all go with biosensors. So you can use biosensors by appropriately tuning the surface functional groups, or modifying, or you actually functionalize that with the specific aptamers. I mean, like, you can make biosensors for to detect any kind of microorganisms. Okay, so thereby you can also use these to estimate the or to understand the freshness of a given food sample, whether it is a packed food or a beverage, or a the level of caffeine or the level of tannin in tea. Okay, anything. Say for example, like the presence of lactic acid in milk. Okay, if there is an adulterant in milk also, you could be able to distinguish with the help of biosensors. Even in the fertilizers, the amount of nitrogen, phosphorus, the essential nutrients, nitrogen, phosphorus, potassium. Okay, so whatsoever that is given in in a sample of a fertilizer can also be detected in the by using biosensors. Okay, so you can use them almost all the places. Say for example, in healthcare, typically we use biosensors for the detection of urea, glucose, alcohol, like breath sensors. Okay, that comes under, you know, like gas sensors. I mean, like, I'm not going to touch about the gas sensors today, but regarding the other things like cholesterol, DNA mutations, that can give a you know, indication about various disorders at an early stage. So all these are you know, some of the important critical things that one can detect with the help of biosensors. Okay, so when you want to make a biosensor, so as we said in the earlier previous slide, as we seen in the earlier slide, you need to have a transducing platform. Okay, so transducing platform is an important you know, thing while you construct a biosensor. So this transducing platform is nothing but a electrode, and this electrode can be made of any number of materials. Okay, so here I'm going to just give you a brief introduction about nanomaterials modified electrodes. Okay, so what are nanomaterials? So in nanomaterials, in principle, refer to any material. Okay, so it not necessarily, you know, one material, it can be of any metal. Okay, any non-metal. Okay, so which has a size domain within the range of 1 to 100 nanometers. So this can be a diameter, or this can be a radius, or this can be a its length in the case of a rod. Okay, so this is just a, you know, very basic slide that actually shows where this nanometer regime actually falls. Okay, so there are many examples for nanomaterials. Okay, so that we are going to see in the upcoming slides, in the next slide. So the first reason is, why do you want to use this? You know, this is a very fundamental slide that actually, you know, describes like why do we use nanomaterials. Okay, say for example, you can see 3 different types of cubes here. Okay, so with 3 different surfaces. Okay, so here when you see the very smallest one, okay, 1 meter by 1 meter by 1 meter, so when you look at the surface to volume ratio, okay, so when you calculate the surface area and volume, and you divide surface area by volume, you have 6 surface or 6 sides per meter. Okay, whereas a little bigger one, which has a 2 meter by 2 meter by 2 meter, has only 3 surface or sides per meter, and the still a bigger one has only 2 sides per meter. And therefore, when the size decreases, okay, so dramatically you increase the surface to volume ratio. And why the surface to volume ratio, high surface to volume ratio, is very, very important, because when you use this for a catalysis or on an electrochemical catalysis, okay, if a biosensing reaction is based on, or if a detection is based on catalytic property of an enzyme or an antibody, okay, so obviously you need to have more surface. Okay, so therefore you can have more antibodies present, or you can have more enzymes present, and therefore the number of enzymes, there will be a more number of enzymes, so its activity is going to be very much more. Okay, so obviously you need to have a very high surface to volume ratio. So therefore nanomaterials are in you know, like you cannot ignore them as a you cannot ignore them. Okay, so for while making these transducing platforms. Okay, so the other important you know, reason why we are behind nanomaterials, or that it's one of its exciting optical properties. Okay, because as we know, like, you know, like we see gold. Okay, only it exists in yellow color in bulk. Okay, so there is no different color that you can see for this gold. Okay, so whether you buy in a jewelry shop or when you know, mine it, okay, so it comes as a yellow color. But when the size of the gold varies from, you know, 10 nanometer to 2 nanometer to 1 nanometer, okay, so actually you can see a different color change. Okay, I mean, this is because of the quantum confinement. I mean, like many of you might have been already studied about this. Okay, so here in the case of a nanomaterial, the energy levels are quantized. Okay, so you have a confinement width, thereby when you decrease the size, you actually, you know, like vary the color. I mean, vary the color of the fluorescence. I mean, the band at which it emits. Okay, the fluorescence. Okay, so it varies, so therefore you get a different color. Okay, so this is one of the exciting optical properties of the nanomaterial. So similarly, gold, you consider gold or platinum in bulk, it is not a magnetic system. I mean, like, it is not magnetic. It does not exist any magnetic properties. But when you shrink the size, okay, so it is going to have a different magnetic property. It can be either paramagnetic or ferromagnetic, but all it depends upon the magnetic moment of the adjacent neighboring nanoparticles. So therefore, when you actually shrink down the size, okay, so you have more magnetic moment acting upon the individual, I mean the adjacent atoms, and therefore its magnetic property is greatly deviated from the bulk. Okay, sometimes you know, like, you can also exploit this in biosensing, which I'm going to explain in the later section of my talk. Okay, so similarly, in a given for a given specific surface area, okay, you have a bulk material on one side, on the left you have the nanomaterial. Okay, so the catalytic property is dependent upon the number of catalytic sites actually present. Okay, so in a given surface area, if you compare the bulk size material with a nano material, okay, if you take copper, you consider the copper nano material. Okay, so if you take gold, you consider the gold nano material. Okay, in a given size. Okay, so when it is when the size is shrinked, you have, in a given space, you have more number of nano particles, and thereby, you know, like, the number of catalytic edges also increases, and therefore it can act very effectively. And it gives a very you know, very strategic and very excellent electrocatalytic properties or normal catalytic properties than the bulk material, and therefore you know, like, nano materials are very, very significant in many applications. Similarly, say for example, if you want to store some kind of a gas like hydrogen or oxygen, okay, so it can be easily purged because with the diffusion distance, okay, the diffusion distance in the case of a nano material is going to be very, very short than in its corresponding bulk material, and also the rate at which the exchange rate. So you can charge and discharge at a very faster rate, and therefore the exchange rate is also very, very rapid in the case of a nano material than its corresponding bulk material. So for all these reasons, you know, like, nano materials are very, very important, or you know, small dimension materials are very, very important in biosensing as well as in electrocatalytic applications. Okay, so nanomaterials comes in different flavors. So we also have a you know, inorganic nanomaterials and organic nanomaterials, micelle, liposomes, you know, some kind of proteins, DNAs. You can also consider this as a organic nanomaterials. Okay, so these are the you know, different types of flavors in which, like, you can make these nanomaterials. And carbon nanomaterials are so special because I will explain that in the later slide. Are very so special, at least in this you know, slide, because I work on all these different types of carbon based nano material. So first I am going to you know, start with my defining something about neurotransmitters. So neurotransmitters are nothing but some of the simple organic molecules that plays a key role in neural communication. Say whatever you do, okay, so the sense, you sense, the taste, okay, so everything depends upon the neural communication. Okay, your memory, okay, so everything, okay, so your motor movement, that is when you bend down or when you wake up, okay, everything, okay, everything related to the motor nerves and your thinking, all are interconnected with this neural communication. So detecting these neurotransmitters or monitoring the amount of neurotransmitters is always a key issue. Okay, so these are the only 5 neurotransmitters that are available. This plays a key role in our day-to-day, every day-to-day you know, mechanism. Okay, so dopamine is an example of a simple neurotransmitter, and we also have serotonin, histamine, norepinephrine, and epinephrine. Okay, so these are the 5 important organic molecules that are classified as neurotransmitters, which plays a very key role in our day-to-day life. So I have defined neurotransmitter. So why is it very important? Okay, so the depletion of some of the neurotransmitters, say for example, dopamine, can lead to Parkinson's disease. Okay, so Parkinson's disease is associated with a motor nerve dysfunction. Okay, so defect in motor nerves leads to the depletion of dopamine, and therefore you develop a Parkinson's disease. Similarly, if you have excess secretion of dopamine, okay, it leads to mental disorder called schizophrenia. Okay, so that way you need to balance the amount of dopamine secretion and as well as the release into the extraneural regions, okay, at an appropriate level. And therefore, monitoring or taking note about the amount actually secreted is very, very important. Okay, so if you balance a very good level of dopamine, okay, it will help you in good appetite, happy mood, and good sleep. Similarly, serotonin depletion, it leads to obesity and depression. Similarly, the excess secretion of serotonin, it leads to cardiovascular problems. Okay, severe cardiac arrest can occur if there is a too much secretion of serotonin. The reason for it is beyond the scope of this presentation. However, I would like to just give you a brief overview of this kind of important neurotransmitters role. Okay, so now what is neurotransmission? So actually, when you look at this slide, so you have a two kidney bean shaped structures. The one on the left is called the presynaptic terminal, and the one on the right is called the postsynaptic terminal. Okay, so you have a small circles embedded as T inside. Okay, so these are the pockets. We call it as a granules of the pockets, by virtue of nature they actually secrete the neurotransmitters. Okay, so they are actually all aligned uniformly alongside the wall of the presynaptic terminal. When you apply an impulse, okay, by means of a mechanical stimulation, by using a very sharp tipped pin, or by means of an injection, okay, so these small vesicles, they fuse with the inside wall of this presynaptic terminal, and it throws off its chemical components, which are nothing but neurotransmitters. That is actually shown on the red color on the right hand side. Okay, so these neurotransmitters are released. So the distance between the presynaptic and the postsynaptic terminal is called the synapse. Okay, so this region is very, very important, because the concentration of the neurotransmitters released will actually stay there. Okay, so monitoring the concentration there in that synapse, which has a length of only 100 nanometer to 2 micron, is very, very critical. Okay, so we need to devise a platform which can be actually poked in this particular region, so that you measure the concentration of the neurotransmitters released. Okay, and you have small squares on either side of this pre and postsynaptic terminal. Okay, the small square represented as R. These are nothing but receptors. Okay, so when these chemical constituents that goes into that synapse, some of them just stay there, and a few of them go on the attach itself to the receptors. Okay, so when it gets attached to the receptor, okay, these receptors actually gives the sense. Okay, so it is related to through the millions of other neurons that are present adjacently, and it is processed in your brain, and you actually feel that as a sense. Okay, a normal sense actually has these big complicated mechanism. Okay, so when you put an electrode in between these two pre and the postsynaptic terminal, that is in the region of synapse, so these neurotransmitters released. Okay, when you apply a potential to that electrode and keep the electrode very close to this synaptic region, so these chemical molecules or these neurotransmitters undergo a redox reaction at the electrode surface. Okay, thereby you see a signal. Okay, that is shown in the bottom of this slide in a pink color. Okay, so this is how you actually measure the concentration of a neurotransmitter in a real system. In a real system, a neurotransmission is a very, very critical event, and monitoring this neurotransmission is a very great challenge. Okay, so why do we prefer very small dimension materials or small electrodes? Okay, because when you have a small electrode surface, then only you could able to keep the surface very, very close to the neurotransmitters, because the size of the neuron, as I said, the synapse anywhere between 100 nanometer to 1 micron. Okay, so if you want to access the chemicals or the neurotransmitters within that synapse, you need to have a very, very tiny small probe, and therefore we are interested in actually making electrodes that are very, very small. Also, the amount of sample, that is present in that particular snap will be in microliters. Okay, and therefore when you use a conventional classic carbon electrode or a conventional gold electrode, which is of like 2 millimeter and 5 millimeter in some, diameter, obviously like you couldn't be able to get any signal. All goes as a noise, and therefore you need to make the surface very, very small to access all the useful information even in that very, very small volume. Similarly, all these events, these synaptic event is a rapid event. Okay, so the entire neurotransmission will end in less than 10 to 50 microseconds. So you need to apply a very fast scan rate. Okay, applying a very fast scan rate in a conventional electrode, you don't get any signal at all. Okay, because of that very high double layer capacitance in the order of like milliamps and amps. Okay, so whereas in the case of microelectrodes, when you access the microelectrode, the double layer capacitance will be in the very, very small, in the order of 50 to 100 microamps, or in sometimes like less than microamps. Okay, so these are all the reasons why we want to go for a very small electrodes or depositing nanomaterials on these very tiny surfaces. Okay, so here I'm going to show you some of the interesting design of ultra small electrodes. Okay, so initially what we do here is a quartz capillary was pulled down using we have a capillary puller. Okay, so by means of a mechanical force, we actually pull out a capillary, a quartz capillary. So once you pull out the quartz capillary, it have a shape like this, like as shown inside these two lines. Okay, you have a very conical tip on one side and a broad back on the other side. So what we do is we keep this pulled capillary within a Pyrex tube, and we will pass acetylene from the backside of this tube and nitrogen from the opposite side, that is towards his nose. Okay, we flow this for 2 minutes, and then we pyrolyze the acetylene coming through the backside of this particular quartz capillary. Okay, as a result of which acetylene undergo pyrolysis. Okay, acetylene undergo pyrolysis, and as a result, deposits of carbon are seen on the shank and also on the inside of the capillary. Okay, just by increasing the flow of nitrogen, okay, over acetylene. Okay, if you increase the pressure of nitrogen moving towards the nose size, actually you can actually make a disc electrode. Okay, so you press the acetylene within the tip, and thereby when you pyrolyze, carbon is getting deposited as a disc, which is shown on the SEM on the right hand side, and the left one is the conical tip. So this tip is actually the region where carbon is getting deposited. Therefore, by adjusting the acetylene and the nitrogen flow, okay, you can either get a disc shaped electrode or a cylindrical electrode which has a carbon deposit. Okay, so this is actually a very decent view of the electrodes that we have made. Once the carbon is deposited on the tip as well as the shank of the capillary, we actually fill the backside of the capillary using this pulled Pyrex tube by means of a graphite powder, and then we insert a tin annealed copper wire for a electrical contact and seal the broader end, the backside, using a araldite or a quick fix. Okay, and then you leave it under the laboratory atmosphere for 1 month or 2 months. It is not going to affect the performance in any way. So the length of the carbon deposited on the surface, okay, is in the order of 20 microns. Okay, and the diameter is roughly around like 2 micrometer. Okay, so this is actually a very elaborated decent view of the cylindrical or disc shaped electrode that we made at this particular experiment. Okay, so when you go and look at the finer details, you can actually see the carbon surface here. Okay, so the electrode tip is nice and it has no crack or it has no dent on any of the tip. So this electrode, this particular electrode, pyrolyzed ultra small carbon electrode, is ready for use. Then what we do is we then use a very standard electrochemical redox probe like hexamine ruthenium 3+ to assess the surface characteristics of this electrode. Okay, so we get a typical sigmoidal voltammogram like this. Okay, see, when you see a voltammogram in conventional electrode, it is going to be a peak shaped voltammogram. Whereas in the case of a very small ultra micro electrodes of this type, you see actually a S-shaped voltammogram. Okay, and you see between the forward and the reverse sweep, the capacitance is very small. Okay, the capacitance is very small. Okay, therefore this electrode is a nice electrode. I mean, whatever electrode that we have designed is a perfect, has a very perfect seal, and everything is perfect for further analysis. Okay, so this is the, so actually you can see that the current, the limiting current here is only 13 nanoamps. Okay, so I mean, like getting these kind of electrodes, you know, like is very difficult. I mean, designing this electrode without any dent or any breakage is always a critical challenge for real-time applications. Okay, so and you can go the, I mean, you can increase the scan rate up to 1 volt per second. You are not going to see any change. Okay, it is going to be the same at all times. Similarly, we have also determined the radius and the length of this electrode by means of SEM and also by means of an electrochemical strategy. I mean, we do an analysis and we have an equation called quadral equation where you can actually plug in the various parameters and the limiting current. You can actually estimate the actual radius and the length of the electrode that you have designed. So in our case, there was not much deviation between the radius and the length that was visually estimated based on SEM results and also those based on quadral equation. In both the cases, so you can see the radius of our electrode as 6 micrometer approximately, and the length as 79 micrometer. Okay, and when you look at the double layer capacitance, since as I said, like it does not give any noise. Okay, so it will give only the signal. You can actually measure only the signal. Okay, the signal to noise ratio of this particular micro electrode is very beautiful. Okay, so in this pyrolyzed acetylene, you have a capacitance of 5 microfarad per centimeter square. Okay, so whereas in other cases in hydrogenated glassy carbon electrode, you have something called 20 microfarad per centimeter, and in the case of a conventional glassy carbon electrode, you have 35 microfarad per centimeter square. So the double layer capacitance here exhibited by this particular pyrolyzed carbon electrode is only 5 microfarad per centimeter square, which is very important while doing the in vivo analysis. Similarly, since we are interested in the detection of dopamine, we employed this electrode to detect dopamine. So dopamine, actually the redox reaction involved here is the conversion of dopamine into dopamine hydroquinone. Okay, so this electrode actually is very perfect fit for the detection of dopamine, as it showed a very good S-shaped voltammogram here with a minimum background, meaning the distance between the space between the reverse and the forward sweep is very small, and therefore the signal is very great here. Okay, so our electrode, whatever that we have designed here, can be used for the detection of dopamine, and it is very vivid or very clear from this particular experiment. So the next question is that, so whenever you want to detect dopamine in the neuronal region, it does not actually exist as dopamine. Okay, always ascorbic acid is always present as a coexistent in the neuronal region. Okay, if it is present as an ascorbic acid, then it is not a problem because our electrode is very specific to only to dopamine. However, what happens is, so as is shown here, so this sigmoidal shaped voltammogram is due to the conversion of, that is, dopamine is getting oxidized to dopamine orthoquinone. Okay, so that is why you see this S-shaped voltammogram. Once it is getting converted into dopamine oxyquinone, the ascorbic acid that is present as an interferent or a coexister with the dopamine, that has a tendency to react with this dopamine orthoquinone and convert that back to dopamine. So at all the time, when you increase the concentration of ascorbic acid, okay, more and more dopamine orthoquinone will get converted back to dopamine. And say, for example, if you have only 1 millimolar of dopamine, and if you have 0.1 millimolar of ascorbic acid, the signal that you get for the detection of dopamine will be equal to 5 millimolar of dopamine, because the oxidized product of dopamine always reacts with the ascorbic acid, and all of them gets converted back into dopamine, and this dopamine is getting detected at this particular electrode surface. Okay, and therefore whatever you measure here is not exactly the actual dopamine. It is the oxidized product, getting back to the dopamine. Okay, so this is one of the critical challenge or critical problem that you always envisage when you detect dopamine in the presence of ascorbic acid. So in our case also, we have seen that when you increase the concentration, keeping the dopamine concentration same, but you vary the concentration of ascorbic acid. Okay, so you see change in the peak, the distance between the baseline and the limiting current. Okay, the limiting current keep on increasing while you increase the concentration of ascorbic acid, and therefore this electrode has some kind of interaction with the ascorbic acid, and therefore you should come out with a strategy to modify this particular electrode so that you detect only dopamine. So how that I am going to explain in the next slides. Okay, so again, so now the first problem is the oxidation product of dopamine goes back to dopamine in the presence of ascorbic acid. The second problem is that when you keep this electrode in the laboratory atmosphere for about 2 to 3 months, or at least for a month, okay, you do an analysis towards dopamine detection when you prepare this electrode, and you store this electrode for a month, and again you do the analysis, there will be a decrease in the signal. Okay, there is a fall in the signal about 21%, which is also is above the defined limit. So you should have maximum 10 to 12% is acceptable. Okay, but it is about 2 times the allowed desirable limit. So this is the problem number 2. When you keep the electrode in air, okay, that is in the laboratory atmosphere for a month, you actually see a 25% fall in the signal. Similarly, when you access this dopamine in the neuronal region, you always have biomolecules like proteins, peptides, and other kind of biomolecules. So these molecules has a tendency to go and stick on to the electrode surface, and thereby it forms a layer around the electrode, and thereby it blocks the diffusion of the dopamine or ascorbic acid, whatever that you are going to detect. Okay, so when you actually do the real analysis, so we have actually made a dopamine, we have used this electrode to detect dopamine, and then we add a peptide deliberately into the dopamine solution, and then use the same electrode to detect dopamine. Actually, you see a 33% decrease in the signal towards the detection of dopamine. Similarly, we also used a peptide. Okay, so similarly we use a model protein which is bovine serum albumin, and we added to the cell, electrochemical cell that contains dopamine, and then we did the analysis, and in this case we witnessed a 62% decrease in the signal that we actually anticipate for the detection of dopamine. So in all these cases, these electrodes didn't perform well. Okay, so these are the other problems associated with this particular small, ultra small electrodes. Then when you bring in both the protein and peptide together into the dopamine system, okay, you see we witnessed about a 70% fall in the current. So obviously one cannot imply, though this electrode is very useful to the detection of dopamine, when any of these peptide or proteins are not present, it is okay. But when you want to go take it into the real system, okay, so it has to actually protect this protein and the peptide. It has to actually stop this protein and peptide that is getting absorbed to the electrode surface, but it is not actually doing so, and therefore you see a drastic decrease in the observed limiting current when you have a protein and a peptide. So in this case, we witnessed about a 70% shortfall in the signal. And if you store this electrode inside a protein and peptide or in BSA for about 3 weeks, you make a very nice electrode and you store it. You keep the electrode with the top inserted down into a cuvette that contains BSA for 3 weeks, and then you do the analysis. So in this case, you get actually a signal which is insensitive. Okay, you have a signal. It is not a S-shaped curve. Instead, it is a rapid going and coming down. Okay, like a typical linear fit. Okay, so when any of your electrode shows this kind of a trend, it actually is a clear indication that the electrode surface is not sensitive to that particular material. Okay, so once you keep the good electrode inside BSA for 3 weeks, so its response is actually it becomes totally a insensitive surface, meaning the electrode lost its sensitivity due to the change in the surface chemistry, due to the adsorption of proteins and peptides onto the electrode surface. Okay, and therefore, why this electrode fouling happens? Because as we know that since we are working only on the carbon surface, okay, so carbon has a different surface. It has steps, it has kinks, it has, so these are the reactive surfaces present on the edge plane. Okay, the basal plane of carbon is always a free surface. Okay, only the molecules can go and adsorb on it. Okay, and it cannot undergo any kind of catalytic activity. It doesn't have any electrocatalytic activity, or it doesn't actually help in electron transfer. Whereas the edge planes are the planes where you have a number of functional groups like a carbonyl group or a quinonic moiety or carboxylic acid group, or sometimes a ether group. Okay, so all these groups are very, very profound. I mean, they love to interact with the amino group on the proteins and peptides. Okay, so when the edge planes being exposed, these proteins and peptides has a tendency to react with them, and then it gets buckled up, or it forms a layer on the electrode surface, thereby preventing the analyte, that is in this case dopamine, from the solution to the electrode. Okay, it blocks the diffusion. Okay, and thereby you get a very insensitive signal in the case of when you add a protein or peptide to a system that contains dopamine. Okay, so as a result of a consequence of electrode fouling is that you will witness a suppression or distortion in the voltammetric results, or you sometimes it gives you a very irreproducible voltammetric data. Okay, so actually based on our results, we concluded that our electrode has undergone a severe electrode fouling. Okay, so this is actually the scenario where you can actually see the different kind of steps, kinks, and terrace that is present on the edge sides of the the carbon surface. You take any carbon system like a carbon nanotube or a carbon nanofiber, or you take like a graphene. Okay, you see all these terrace, kinks, and steps. Kinks and steps are present in the edge planes, and they are the main reason for the electrocatalytic activity, or the catalytic or the rapid electron transfer of the the analyte that you are going to detect. All the reaction occurs mostly at the kinks and the steps. Okay, you also have dangling bonds, but these dangling bonds will never interact with any protein or peptide. So you need to come out with a strategy so that you modify the surface on the kinks and steps. But there are many known strategies, like you can use a naphthalene or cellulose acetate or agarose. Okay, you can actually like deposit these thin films on the surface. Okay, what happens is that when you actually immobilize these naphthalene or cellulose acetate or chitosan or agarose onto the electrode surface, what happens is that based on the the charge of these layers, okay, it actually evicts the other oppositively charged analyte to only to penetrate, but thereby it repels the same charged species. Okay, that is the only thing that these naphthalene or cellulose acetate can do, whereas it cannot come down, it cannot brings down the fouling to a greater extent. So, like we worked on this problem for a long time, and then we come out with a strategy to hydrogenate the carbon, this edge, that is the edge planes. Okay, so when you do the hydrogen termination, what happens is most of the hydrophilic groups are actually removed. I mean, is actually modified by means of hydrogen termination. So we use a hydrogen plasma strategy where we terminate the reactive functional groups like carbonyl groups and quinonic moieties by means of hydrogen termination. Okay, so this is a simple setup where we use that we use for hydrogenating. So this is not only used for hydrogenating the ultra small electrodes. If you have any system, okay, if you have even a bulk material also, you can use the same strategy to actually, like terminate the functional reactive carbonyl groups by means of a hydrogen termination. So once you terminate the carbon surface by means of hydrogen, then we actually measure the capacitance, whether this is going to, we would like to compare that with the unmodified surface, unmodified physically small electrodes, whether we also get a similar kind of capacitance. Otherwise we are disturbing the signal to noise ratio. Okay, so when we look at the compared the capacitance value, so this hydrogenated pyrolyzed carbon actually performed better than the pyrolyzed acetate. So in this case we get about only 2 microfarads per centimeter. The capacitance here is only 2 microfarad per centimeter square, and therefore like this is an excellent system that you can go ahead and do the in vivo analysis. Okay, so here so how do you know that the surface functional groups are actually modified by means of this hydrogen termination? So we have a system called ferrocene. When you do the analysis, when you do the cyclic voltammogram in this particular ferrocene system in 1M perchloric acid as a supporting electrolyte, okay, you see two different voltammograms here, one before hydrogenation and the one after the hydrogenation. Okay, so after hydrogenation the response rapidly came down because this is a sensitive system only to carbonyl groups. Okay, when you have more amount of carbonyl groups, this Fe2 plus interacts with that carbonyl system and then it gives a response. Okay, and therefore when the system is not terminated with hydrogen, you see a greater limiting current, whereas after hydrogenation the number of carbonyl groups being terminated with hydrogen, there is no active carbonyl groups there, and therefore you see a very drastic fall in the limiting current. So therefore from this experiment we confirmed that we have diminished the number of surface carbonyl groups. Again, when you want to this potassium ferricyanide system, this couple is 3 minus 4 minus FeCN6 3 minus 4 minus. This is a system that is particularly sensitive to the monolayer adsorption. Okay, when your surface is when your surface has a monolayer adsorption, that you terminate that with any say for example, if you modify, in this case we modify the electrode with the hydrogen termination. Even if you have a cellulose modification, you have a chitosan modification on the electrode surface, before and after modification, when you do this analysis, you see a decreased limiting current after modification, because this particular system is sensitive to the surface layer. Okay, if there is any kind of layer is present, it actually shows a very small it gives a response in such a way that it is drastically less than the system before modification. So we call this as a surface layer sensitive system, whereas the system that we discussed before, that is Fe3 plus ferrocene, is sensitive to the carbonyl groups present, whereas here this is a layer sensitive system. So by this also we could able to confirm that we have a hydrogen terminated layer on the surface of this pyrolyzed carbon. Okay, so therefore from these two important critical experiments, we demonstrated that hydrogen termination has been rapidly done in our system. So now we use this hydrogenated ultra small carbon electrodes to detect dopamine. Okay, so we kept the we immediately made the electrode and we did the analysis. On the same electrode we kept it in laboratory atmosphere for 3 months, and again we did the analysis. So here there is no steep change in the observed limiting current. So the change in current density is only 4%, which is well within the allowed limit. Similarly, we stored this electrode in BSA for about 3 weeks. Okay, so in the previous case, we don't even see a response towards dopamine detection when you store this electrode for 3 weeks. Okay, so in this case, when you keep this electrode for 3 weeks and then you do the analysis, that is the hydrogenated electrode, again there is only a very small decrease, that is 5% decay. Okay, similarly, when you add peptide to the dopamine system and you do the analysis, the change in the current density at this hydrogenated electrode is only 3%. Okay, when you add a protein to it, you see only a 1.2% change. When you have protein and peptide together and you do the analysis, you have only 4% decrease. And thereby it clearly demonstrated that hydrogen termination, okay, improved almost all the electrode fouling properties, retaining the that is the signal to noise ratio much better than the normal pyrolyzed carbon electrode. And using this hydrogen terminated electrode, we actually detected dopamine up to 1.5 nanomolar concentration. Okay, so from this we could able to conclude that, okay, so this hydrogen termination resulted in a really ultra small electrode system that you can use that for the real-time analysis. Okay, now the other problem that we discussed earlier is when you have ascorbic acid present along with the dopamine. Okay, so when you keep the concentration of dopamine and when you increase the concentration of ascorbic acid, so you see a increased current for dopamine. Okay, because the oxidized product of dopamine reacts with ascorbic acid and then it converts that back to dopamine, and thereby the actual concentration of dopamine is more than the actual concentration that you are supposed to detect. But in this case, when you do the analysis only in ascorbic acid using this electrode, you don't see any signal, any sigmoidal shaped voltammogram. Okay, this clearly says that this hydrogenated surface is highly insensitive to this ascorbic acid, and therefore the oxidized product, even this ascorbic acid converts them, it does not going to have any significant change. Okay, so therefore when you do this particular analysis, okay, you see the dopamine concentration as same even in the presence of ascorbic acid. Okay, when you increase the concentration of ascorbic acid, again here you see the same sigmoidal voltammogram that corresponds only to the detection of dopamine, and the presence of ascorbic acid has no significant effect on the detection of dopamine. So this is actually a real-time experiment that we have performed. Okay, so this is actually a aerial view of a the brain of a mouse. Okay, it was cut open by a veterinary physicians. Okay, and we also have a group of psychologists who helped us actually to locate the actual position where you want to actually poke the electrode, and you do the real-time analysis. Okay, so the one on the left is the analysis, the real-time analysis that has been done to detect dopamine, okay, using the normal pyrolyzed carbon electrodes, ultra small electrodes, while the one on the other, on the right hand side, is the one that you actually detected in the presence of using the hydrogenated electrodes. So the electrode underwent a fouling of about 52% while detecting this dopamine in real-time system in real rat brain. Okay, that is with the pyrolyzed carbon electrode on the left. On the right, you have only 11%, which is associated with the hydrogenated pyrolyzed carbon electrodes, and thereby we demonstrated that. So this system is a really interesting system that you can actually use them for any number of analysis. Okay, so the advantages of this hydrogenation in biosensing is that it actually modified the total surface carbonyl groups. Okay, and then it exhibited a very stable response even after 3 months of storage. Okay, now again when you go back to the it is also very resistant, okay, towards the fouling effects, and also it exists, you can use this for the real-time analysis. Okay, so this is the case with the ultra small electrodes of carbon-based carbon-based and carbon-based electrodes with the hydrogen termination. Now I'm just going to switch on to graphene. We also have done some work on graphene based transducing platforms for a similar kind of application, which I am actually going to explain to you in the upcoming slides. So one important useful property of graphene compared with the other nanomaterials, that is carbon family is that. So it has a very flat surface. It's being a two-dimensional material, it exhibits a very great, excellent conductivity. Okay, so whenever a material has a very excellent conductivity, it is important material for biosensing application and also for electrocatalytic application. Okay, so that's the reason why, there are many research works that have been performed on graphene for biosensing applications. Okay, so when you actually look at the ability of the electrons to conduct electrical current, it is actually 100 times more in graphene than in any normal semiconductors, like you take silicon or anything. So graphene exhibits 100 times more mobility for the electrons, which we really need it for biosensing system. Okay, so this is actually like a very traditional slide where it says that if you have a in the graphene system, you have a two smooth cone shape structure that actually meets at a point. Okay, so this is the reason for the ballistic transfer of electron from one end of the material to that is on the over the long distance in a two-dimensional flat system. Okay, so there are many different methods for the synthesis of graphene. Like any other nanomaterial, you can follow a top-down approach or a bottom-up approach. Okay, so the bottom-up approach includes like anything like arc discharge method, chemical vapor deposition, chemical synthesis, epitaxial growth, and all these things. And top-down approach is nothing but different kinds of exfoliation, like whether it can be hydrothermal or like any other exfoliation or a scotch tape peel off method. So you can have any type of method, but in our work, like we actually employ only the bottom approach. Okay, so again, the other important the reason why we employ graphene for biosensing application is that, so when a biomolecule comes and sit on the electrode surface, you need to actually tailor the surface by means of different functional groups. Okay, so graphene is the only carbon-based material that has been researched numerously for many different types of ionization. Say, for example, you can do a acid reflux or acid cutting. Okay, and you can terminate the graphene by means of a carboxylic acid group. Okay, you can do any type of Grignard type, addition. Okay, so you can terminate the halogens on the graphene surface. You do a ozonolysis, you have a O termination on the side. Okay, you can also do a oxidative aromatic coupling where you can terminate the amino groups there. Okay, you can also wrap a polymer onto it. Okay, so any kind of it is the only carbon material that has been actually worked so long for different kind of functionalization. Even carbon nanotubes, only like 2 or 3 different types of functionalization is known for carbon nanotubes, and it itself has many different problems. Okay, it also comes with the intrinsic impurities, which actually restricts its usage in carbon nanotubes application in biosensing application. Whereas, like all these graphene system that you use is free from metallic impurities, and therefore you can functionalize the way that you want, and then you employ them as a transducting platform for several biosensing applications. So the traditional chemical synthesis we follow, and we got graphene in our work, and like from the Raman is a signature that it actually says that you have a that could peak. So, and also the number of layers that we have, you can vary depending on the reaction that you employ. Okay, so based on that, like we made this by following a traditional chemical synthesis, we obtained graphene, and then we tested this for its electrochemical property using potassium ferricyanide system and also with the hexamine ruthenium system, and it exhibited a better response in this both redox probe, and we compared its performance with the carbon nanotube. Okay, so in both the cases, it outperformed the single wall carbon nanotubes performance on these 2 redox system. And then we employed this graphene for the detection of dopamine alone, ascorbic acid alone, serotonin alone, and then we also put all these 3 together, and graphene could be able to actually detect all these three in a single run, meaning it has the ability to detect all the three. Okay, it is selective individually to all these three, and it could be able to resolve all the three peaks in a given run. Okay, so the reason for it is it has a different types of steps and kinks that are specific towards a particular analyte, and it also have a very plentiful sp2 domains that actually accelerates the electron transfer. Okay, so therefore from this we could be able to conclude that this system is highly useful for the detection of many analytes, even though they are in one analysis. And again, like we also used this system, that is a graphene based transducting platform to achieve a direct electron transfer. When you have an enzyme or a peptide or a protein, okay, achieving an electron transfer is a very challenging issue. The reason being is, so in all these, say for example, here you have hemoglobin, you have chlorophyll, and you have urease. All these are either you can call that as an enzyme or a protein, and it depends on you how you call it. Okay, so in all these cases, the central metal atom. So in the case of hemoglobin, you have iron. In the case of chlorophyll, you have magnesium, and in the case of urease, you have nickel. So all these central metal atoms are deeply buried inside the chains. Okay, and therefore, see, these only the central metal atom are the active redox centers. When the electron transfer has to occur, the potential has to be felt by this metal system. Thereby, the electron transfer will occur. And therefore, when you have these kind of woven or wound up structures like this, okay, it is always a difficult task when you immobilize them onto a electrode surface. Okay, it is very, very difficult to create a electron transfer, and you don't see a significant peak or a sigmoidal shape when you do a voltammetry. But whenever, but in this case, like after the invention of nanomaterials, when you put this into, when you immobilize these proteins or enzymes onto the nanomaterials, due to its high surface to volume ratio, at least at one point, so this material is intact with this particular metal center, and therefore when the potential changes or the potential is scanned, okay, so that is felt by the metallic system, and thereby the electron transfer occurs. Okay, and therefore after the invention of this, after these nanomaterials started progressing, direct electron transfer of enzymes, that is enzyme based biosensors, started growing. Okay, so here in this particular case, okay, so in this particular graphene, so it also has an excellent conductivity, and this 2D flat structure, okay, high enormous surface to volume ratio actually acted as an active connector of the redox center of the enzyme to the bulk electrode surface. Okay, and also the presence of edge plane defects, okay, is a catalytic center where actually this direct electron transfer occurs. So these are all the reasons for graphene to be employed as a very good transducting platform to achieve a direct electron transfer. So we have actually tested this with a cytochrome C. Okay, we used a graphene electrode and immobilized cytochrome C on the electrode surface and try to look at its electron transfer property. So the plot A here corresponds to the direct electron transfer achieved in a classic carbon electrode. So you don't see any signal here. Whereas we have a graphene system, you see a nice voltammogram here, and this actually confirmed that this high surface to volume ratio and the sp2 domains, edge defects, and the everything, all these parameters work well for the to achieve the direct electron transfer. Not only this, so we also tested this in FAD, conversion of FAD, flavin adenine dinucleotide, to hydrogenated flavin adenine dinucleotide. Okay, so this is again a very bulky system where you need a kind of a high surface to volume ratio material and an active electrocatalytic center to actually initiate this particular reaction. Okay, this is actually used for the detection of glucose. Okay, this particular enzyme, this particular reaction is a key while you detect glucose. Similarly, so we can also do the direct electron transfer on the electrode surface, and also you can modify the graphene electrode surface by means of any kind of polymer, okay, for an increased loading of these enzymes like glucose oxidase, and then you can do it for, you can use them for various analysis for glucose detection or cholesterol detection or for any other urea detection, okay. Similarly, we have also varied the number of graphene layers, okay, appropriately tuned the methodology so that you get only 1 or 5 to 10 number of layers or 25 to 30 number of layers, and then try to immobilize glucose oxidase and use them to detect glucose and see how the number of layers plays a key role in glucose detection. But to our surprise, okay, when we tested this with a 3 different layered graphene material, in all the cases we almost saw the same response. From this, we could able to see this. I mean, the reason for this is, though there is an increase in the number of graphene layers, the enzyme is going to go and sit only on the basal plane. It is going to have a wrap only on its alongside its surface, and thereby when glucose go and interacts with this glucose oxidase, only the surface gets exposed, okay. And therefore, whether you increase the number of layers in graphene, it is not going to have any critical effect, or it is not going to exhibit any better sensitivity in the case of glucose detection, okay. So this is another significant work that we have done so far. And also we have used this graphene based electrode to detect DNA mutation, okay. So DNA mutation is something like is very significant in clinical aspects. With this DNA mutation, you could able to detect any number of diseases like Parkinson's disease, Down syndrome, Alport syndrome, anything, okay. This is just based on the way in which the DNA strands keep itself, align itself on the electrode surface. When you have a complementary sequence, it forms a very perfect duplex, and it have a perpendicular alignment on the electrode surface, and that way you have more surface for the diffusion of the redox probe. Whereas when you have a mismatched sequence, okay, so it does not form a perfect duplex. Instead, it is getting scrambled on the electrode surface. Thereby, the redox molecules cannot go to the electrode surface, okay. The scrambled structure actually blocks the diffusion, and thereby you see a very decrease in the current density, peak current density. And based on this, we could actually able to comment if the DNA is or not, okay. So this is another significant work that we have done so far, okay. Again, graphene, okay. So we try to see, we know that graphene is a 2-dimensional structure, but by using a cross-linking glutaraldehyde procedure, we actually try to make up a 3D kind of a graphene, and then we employed this 3-dimensional architecture to detect dopamine and other many other we also use them to achieve oxygen reduction reaction and nitrogen reduction reaction. So in all these cases, we could able to conclude that when you have a 3D woven structure of graphene nanoribbon, also you have a better performance, okay. So I'm not saying that 2D graphene is not good, but we just made a wild attempt. If you have a 3D architecture, whether it is going to inhibit or it is going to be the same. But surprisingly, we actually got a very good response in this 3D type architecture towards dopamine detection or towards the oxygen reduction reaction. Then we also worked on sulfur doped graphitic carbon nitride and this nanomaterial, and we also demonstrated this particular material is suitable for the detection of a few cancer markers like IgG, HCG, and carcinogenic antigen CA125. Not only this, I mean, so this is an electrochemical detection mechanism. Okay, so where we can go down up to 6.25 international units per ml of CA153. Okay, so this is the desired level. If you have this, you can conclude that the person is having a cancer. Okay, so with this we could able to use this sulfur doped graphitic carbon nitride as a excellent platform as an alternative carbon material for the detection of nanomaterial, for the detection of Ca125. Similarly, it also had excellent optical properties. Okay, so based on its fluorescence intensity, we also detected this Ca125. Okay, so the same biomarker is also detected in the optical mode, and the amount that it can detect goes up to the same, like 6.5 units per ml. So in both the cases, we demonstrated that this sulfur doped graphitic carbon nitride is a better system to detect a cancer biomarkers. Also, we worked on some kind of magnetic bead based assay. This is also a biosensor. So here what we are going to do is we make we purchase these magnetic beads, okay, and then we surface functionalize that using a usual EDC NHS coupling, and then we further functionalize that with a Ca125, that is an antibody that is specific to a Ca125 antigen. Okay, and then we actually tag that antibody with a horse radius peroxidase, which is actually going to be our electrochemical signal tag. Okay, we make this and then we put them inside a blood that contains this Ca125. Okay, so what it actually does is, based on the antigen antibody interaction, the modified magnetic beads actually gets pre-concentrated with the Ca125, and then we remove them with because they are magnetic beads, you can actually remove them out of the vial, and then you put them, you isolate this Ca125 from the entire body fluid or from the given sample, that is whether from the blood or plasma or from serum. Okay, you actually pre-concentrate using this, and you exclusively separate the Ca125 from the blood, and then you do the analysis in a normal buffer. So by this we could able to increase the sensitivity up to like 50 times better than the one that you actually do in a normal serum or in the blood. Okay, so this is another interesting thing that we have done. Similarly, we also work on some of the electrosynthesis strategy to make quantum dots from the bulk material. Okay, this is a room temperature technique. You don't need to apply high pressure or high temperature. Okay, just you have to have a working electrode that has a bulk material on it. In this case, bulk WS2, and you have a platinum quasi reference electrode, and you apply a potential of 2 volt for about 24 hours. Okay, you dismantle all the bulk system into a tiny WS2 quantum dots. Okay, so this is one of the significant work that we also done in the recent past. Okay, so we use a single step electrosynthesis strategy. Only one step. You have these electrodes and you have the bulk material on the working electrode, and you apply a potential of 2 volt in the electrolyte, that is propylene carbonate. Okay, so you actually dismantle the entire system, and you end up after 24 hours you end up in getting nice fragmented WSU dots. Okay, similarly the same strategy, you can also synthesize phosphorin quantum dots from the bulk phosphorus. Okay, so here in this case you apply a negative potential, that is applied potential here is -2 volts. Time duration is the same. Okay, reference and the counter electrode are also the same. The electrolyte is also the same. So by this also we have actually demonstrated that the electrosynthesis is a very easier, and also the room temperature technique. You don't have to go for a very high temperature or a special need of make a high pressure kind of things. Okay, so this also we have demonstrated. So these are some of the surface characterization of these platinum phosphorin quantum dots. So now we have also made this nitrogen doped phosphorin quantum dots. So here everything is the same. The only thing we changed is the electrolyte. So in this case, so in the earlier case we have only propylene carbonate. So in this case we used acetonitrile because we want to have a nitrogen system so that it gets intrinsically doped into the phosphorin quantum dots. Okay, so the change here is only the electrolyte. Okay, because you change the electrolyte, the time duration is also reduced dramatically from 24 hours to 2 hours. So in this case you get also this nitrogen doped phosphorin quantum dots, and these are some of the important characterization that we have done with them. Okay, so these are the conventional methods and the materials that we actually use for the detection of the biomolecules for biosensing application. But research in United States or around Canada or in UK is going tremendously on biosensors. Okay, so you can have any kind of biosensor. Say for example, you can have a tattoo on your skin. Okay, that could be able to actually, based on the sweat released, okay, based on the friction, you can actually monitor many changes in the in your body. Okay, and it can also be transmitted to your physician to actually monitor your health from a remote system. Okay, so there are tremendous ways of research that is being actually, one of the recent research here is on micro nanomotor. So these are the kind of biosensors called, we call this as an ingestible biosensor. You can actually swallow them. Okay, so it is made for a particular type of destruction of a cell or for a particular drug delivery. You can actually, these are all also called as ingestible. That is, you can swallow it and it will actually excrete after doing its targeted action. Okay, so this micro nanomotors is a very, very recent invention in 2004, but it actually picked up its it is being rapidly researched only from 2017 onwards. Okay, so I'm just going to conclude in 2 or 3 slides. So this is actually consists of only bimetallic fragment. It have gold and platinum, or you can also have nickel and platinum or nickel and copper, anything. Okay, so all these materials have an autonomous non-Brownian movement. Okay, so this can operate in different type of mechanism. You can also make them to propel by means of, by applying electricity, by means of magnetic propulsion, by means of ultrasound, or self electrophoretic propulsion. Okay, so all these are the different mechanisms by which these nanomotors or micromotors can move. Okay, you can use this for environmental cleanup, oil spillage, removals of toxins, okay, destruction of organic and inorganic dyes. Okay, so for the detection of anthrax or any kind of biological warfare agents, and also for bacterial killing. This is not only going to destruct them, it can also carry it on its surface and take it to a remote place and can destruct all these. Okay, so this is one of the important research area that is actually progressing in the last 2-3 years tremendously. So here actually one of the researcher actually made, this is not my work, so this is from Aishman Sen's work I'm quoting. So they are doing this research in Penn State University, Pennsylvania. So we have a P dot zinc micromotors. This actually moves in the gastric acid. Gastric acid is in the bile. Okay, so it actually moves from one place to the other place. So it can move from the, when you ingest it, you take it as orally, it can actually go all along your intestine, and it can target the diseased place, and it can deliver the drug, and it can get excreted in 12 to 14 hours. Okay, so again similarly, so these are some of the images that I am showing, that a nickel platinum based bimetallic nanomotor has been made actually, and this is tested for detecting some biological warfare agent. We call it as globic G spores. Okay, so these are very rapid spores. They multiply rapidly, exponentially. When it gets you drop one pore, within 5 to 10 minutes it multiplies rapidly, and therefore it can actually totally pollute the total environment, and it is a life-threatening spore. Okay, actually in a lake water, so these are some of the research work that has been done in the lake water. So how these nanomotors can go and carry these spores to a remote location and destroy them. Okay, so these are actually oncoming research area. Okay, so that you can actually use these kind of nanomotors not only to sense but also to destruct environmental as well as biological warfare agents. So I take this opportunity to thank all my postdoctoral researchers, undergraduate researchers, PhD students, and my collaborators. Mahesh is also my collaborator. We have recently published one paper on hydrogen sensors detection using WST quantum dots, and still like we are collaborating. And I also thank all my funding agencies for giving me a lot of opportunities to work on all these different areas. And thank you all for listening to me. And it is a very lengthy talk, I know, but I have no other option. Thank you very much.
Yeah, thank you, Dr. Subhaya, for the excellent talk. Nipun, can you take few questions from the chat box?
Thank you, sir, for such a nice talk. The first question is from Sumit Kale. He's asking why ISAM surface used to bind biomolecule, and how can we use it for simulation of FET based biosensor using nano gap cavity?
Well,
That's
I never nano gap cavity. So these are all terminated system. I mean, your electrode is fine. Okay. So you have an electrode and you have a electrode modified with a particular antigen or an antibody. Okay. So when you have an antigen or when you have an antibody, it binds with its appropriate antigen or antibody. Okay. So you have a redox molecule or a redox moiety tagged to that antigen or antibody that is going to actually translate the signal. Okay. So I never work on gaps and I don't have any idea of how it can actually use it to fill in. So I would like to ask why he wants to detect them in the gap. Because you have a surface, you have a defined surface where you have the electrode material. Okay. So when you want to detect an analyte, that analyte goes and interacts with that particular surface. It doesn't actually goes and sits inside the gap. So why is he so curious to detect them in the gap?
So shall I unmute him?
Yeah.
Yeah, please allow me some.
Hi.
Sir?
Sumit, can you? Sumit
yes,
Kale?
yes.
Yes, sir.
Can you hear me?
Yeah, I can hear you. Yeah.
Please go ahead.
Sir, actually, I want to design a FET based biosensor in which how we are detecting biomolecules, that we are creating a nano gap, a cavity in that biomolecule in a FET based biosensor. So for that purpose, I am asking you what is the use of this self assembled monolayer surface like that?
See, I mean, whatever that I have discussed today, whether it is graphene-based sensor or hydrogen terminated ultra small electrodes. So I always do the analysis in a defined space. So you have the surface, okay? You have the electrode, or you have the where you have the material. Okay, so these analytes, they actually go either diffuse by themselves, or you do like a kind of channel flow. You force them to go towards the surface, and as a result of which, these are all being redox molecules, they undergo redox reaction at the surface. Okay, so I monitor only what happens on the surface. I have no idea like what it will go and do it in the gap. Frankly speaking, like I don't have any gap in any of my reports.
Okay, sir.
No. I think basically he's asking in the field effect transistors because their sensing mechanism is different. So at the gate, basically they have to create some cavity, and then basically because of the dielectric, they get the change in the current.
Yes.
Mahesh. Only thing that I can anticipate is if you use any kind of biomolecules, okay, when you use like any kind of biomolecules, okay, that is going to be whether it will get denatured or based on the Hi. Hello. Can you hear me?
Yeah, we can hear you.
Yeah, the only problem that I see here is when you want to work with an antibody or antigen or an enzyme, the only thing is that you should not get denatured when you work. Okay. Other than that, if you could able to trap everything within that cavity, and if that is going to give you any signal, it's fine. You can use it.
thank you. Yeah, Nipun, any other question?
Yes, sir. Manish from the audience also wants to ask question. I will unmute him.
Yeah, please. Yeah.
Manish. Hello, Manish. Can you hear me?
Yes, sir.
I guess he's not.
Hello.
Speak loudly. We can hear you.
So Dhananjay is there. Dhananjay also wants to ask some question. Dhananjay, you can ask your question meanwhile.
Yes, sir. So when you discuss about the stimulus effect by that sensor, but how the stimulus will affect mechanically or electrically, you told how it will be start in the slide number 4 you show that things.
Stimulation, right?
Yeah.
Electrical stimulation, you can electrically stimulate the cells. Yeah. You can have you can have a stimulating electrode. Okay, so that we have something called like Parkinson's atlas. Okay, so the psychologists, they are very like trained in that. They can actually move that stimulating electrodes towards that particular presynaptic terminal, and you apply a train of electrical pulse. Okay, so that will actually stimulate that presynaptic terminal. The moment it gets stimulated, it keeps on going all along.
Okay, sir. Thank you, sir. Next is you add the graphite powder after that electrode is formed. Why need to keep the graphite powder in the slide number 8 and 9? In the diagram, you show that after sending acetone this side and nitrogen front side, after close the end, you use the graphite powder. Why? What is the reason for that?
No. I get your question. Can you repeat it back again?
Actually, during the formation of the electrode, you after gap at the back side, you end the things with the graphite powder. What's the need
One
of
second. One second. I'll go back to that slide. I'll go back to the slide. You can ask me the question.
Yeah.
This one?
Yes.
Yeah. Tell me. Yeah. What is the problem? Yeah. What do you want to know here?
How this graphite powder you put there, or it automatically formed during the synthesis?
No. So you have so this is the tip, and you have a tapering side like this. Okay. In the previous slide, you have the back end, right? This is open, right? So you actually fill it using, you have a very small, borosil kind of a glass where you can actually pack it like this, and you can put it inside. Okay, like a like a small ground thing. You have a capillary inside it. You tip it like this on a graphite powder. You pack it, and then you put it inside. So it will go and pack here, and then you seal the end. Okay, so once this you see the front nose face, right? That is the pyrolyzed and deposited carbon. In order to have the electrical conductivity, we need to backfill that with the graphite, so that the electrical conductivity, you take the conductivity all along. Okay, so for that reason, on the back side of it, you fill that with the graphite powder. That is using a small like a capillary, which is pre-filled. You tip it on graphite powder. You take the graphite powder, and then you put it inside. So like this, you can fill it.
Okay, sir. Next, last maybe. So can you make it for non-invasive detection?
What kind of detection?
Non-invasive detection. Instead of using invasive, I want to use.
I mean, like you see, if you want to only quantify system outside the cell, see, this is especially like people want to detect them on the cell on the real time. Okay, yeah. These are non-invasive detection I am showing here. So whatever dopamine that you detected here, so this is a non-invasive detection only. Okay, so we have a dopamine actually extracted from there, and then this was actually dissolved in a buffer, and we do it in a regular laboratory experiment. So this is the one, is a non-invasive experiment. If you want to detect the sample non-invasively also, you can use the electrodes, no problem. Yeah.
Okay, thank you, sir.
Sir, there are more questions. The first question, yes, the first question from Manish. He's asking what are the latest nanotechnology applications available in managing salt-affected soils and poor quality waters?
What is it? Poor quality waters. What is it?
Yeah. He's asking what are the latest nanotechnology applications available in managing salt-affected soils and poor quality waters?
No, I don't have any idea. See what kind of you can use many kind of you can use this nano some of these nano materials you can actually functionalize and then you can actually deposit it as a membranes on a salt rejection. So many of the nano materials are suitable for salt rejections. Okay, so you can make a membrane that can actually reject a salt. That is for desalination purposes. There are many applications. Other than that, I don't know. I don't have any idea like where you can use these materials.
Okay, thank you, sir. There is another question like why does the UV vis absorption spectra increase with time for an antibody conjugated with gold nanoparticles when reacted with cells?
Well, that depends upon the nature of the antibody, right?
Okay. One last question is there, sir. Mr. Shahnawaz is asking why you have applied negative voltage for the synthesis of phosphorine quantum dots.
Well, so that particular reaction occurs that is thermodynamically favorable only at that potential. Say for example, so here in this particular system, so this dopamine gets oxidized at 180 millivolts. Okay, so if you bring in serotonin, it gets oxidized only at 220 millivolts. Okay, so we cannot claim like why that is getting oxidized because that particular oxidation is facile, is thermodynamically favorable only at that particular potential. Say for example, instead of this pyrrolized carbon electrode, you use a platinum electrode and you do the same analysis. Okay, so you don't get the oxidation potential at 180 millivolts corresponding to the conversion of dopamine into dopamine hydroquinone. Instead, you get it at somewhere close to 68 or 69 millivolts. Okay, so it all depends upon they are intrinsic properties of a material, and the oxidation and the reduction potential depends upon the the balance in the conduction band. Okay, that actually and the thermodynamic nature of the molecule as well when they both interact. Okay, so this can vary from say for example like WS2 we have also made a MOS2 quantum dots, so you can apply up to like a plus 3 volts only, it gets fragmented. For material to material, it actually varies. There are a lot of things that actually plays a role in it. Say for example, instead of using propylene carbonate, you use some other electrolyte. Okay, so in what that is in this case, like we use acetonitrile when you want to dope nitrogen. Okay, instead of 24 hours, the reaction time reduced to 2 to 3 hours, right? So these are all intrinsic properties that you cannot fix that in one go. These are based on several 50s and several 25 or several hundred experiments by the researchers. Like we actually pick a most favorable and suitable one that is needed for that one. So it actually varies. The same thing. Say for example, instead of see in this case, so I use this sulfur doped graphitic carbon nitride where the UV absorption increased after interacting with the antibody. Instead of this, if you use a graphene quantum dots or carbon nano dots, okay, it can go into a shorter wavelength region also. Okay, so that is the intrinsic property based on the particular quantum dots and also based on the antigen antibody interaction. Okay, so I don't know whether I don't have any clear answer for this other than this particular parameter because thermodynamic features as well as the nature of the electrode. Okay, so the electrode has different conduction and the valence band and the arrangement of electrons. Okay, so all these play a very important and key role in actually predicting which happens when.
Thank you, sir. Thank you for answering all our queries. May I request Professor Mahesh sir to kindly conclude today's session with his closing remarks.
Yeah, so thank you, Dr. Subhaya, for accepting our invitation. And really, this one, it was an excellent talk, and I have enjoyed his slide. This one, we got the new ideas in the area of the biosensing. So thank you very much. Yeah.
Thank you.
Thank you.
Thank you so much for the invitation. very happy, here on this ATAL 2021. Yeah, thank you so much.
Yeah, thank you. Yeah, thank you, Nipun, and all the participants. If they have any general question, they can ask this one. They have, if any question or they want to speak something, you can raise your hand if they have any feedback. So tomorrow we have this one again 4 talks, and tomorrow we will cover this one optical sensors also by using the optical fiber, how we can make the different type of the sensor. And another is the flexible sensor. So morning talk is on the flexible sensor. Then second talk is on the optical sensors. And in the evening, again, we have on the nanomaterials. What are the properties? So I request participants, whatever doubt you have, you can ask this one. And interact more with the speakers. We have excellent speakers this all 5 days. Yeah, thank you. Thank you all. Yeah, thank you, Dr. Subhaya. Yeah,
thank you.
Yeah, thank you, Nipun and team.
Sure.